the kisses of the sun were sweet, I didn't blink, I let it in my eyes. Like an exotic dream, the radio playing songs that I have never heard, I don't know what to say. Oh, not another word, just la 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 la. It goes around the world, just la 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 la. It's all around the world, just la 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 la. It goes around the world, just la 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 la. It's all around the world, just la 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 la. La 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 la. La 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 la. La 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 la. It's all around the world, just la 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 la. It's all around the world, just la 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 la. It goes around the world, just la 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 la. It's all around the world, just la 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 la. It goes around the world, just la 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 la. It's all around the world, just la 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 la. La 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 la. La 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 la. La 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 la. It's all around the world, just la 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 la.
Lay low, hit the sun, everybody have a real good time, real good time.
I'm hearing voices in my head, there's no way to escape. Da-da-da-da, they got me. Anytime, anywhere, my mind in the air. Da-da-da-da, surround me. They surround me. Surround me. Anytime, anywhere, my mind in the air. They're waiting for me, they're calling on me.
Lay low, hit the sun, everybody have a real good time, real good time.
Surround me.
Yeah, we cool, yeah, we drunk, lost my mind, and baby, I feel high, I feel high.
They're calling on me.
Lay low, hit the sun, everybody have a real good time, real good time.
Surround me.
Yeah, we cool, yeah, we drunk, lost my mind, and baby, I feel high, I feel high.
They're calling on me. I'm hearing voices in my head, there's no way to escape. Da-da-da-da, they got me. Anytime, anywhere, my mind in the air. Da-da-da-da, surround me.
Lay low, hit the sun, everybody have a real good time, real good time. Yeah, we cool, yeah, we drunk, lost my mind, and baby, I feel high, I feel high.
They surround me. Surround me. Anytime, anywhere, my mind in the air. They're waiting for me, they're calling on me.
Lay low, hit the sun, everybody have a real good time, real good time.
Surround me.
Yeah, we cool, yeah, we drunk, lost my mind, and baby, I feel high, I feel high.
They're calling on me.
Lay low, hit the sun, everybody have a real good time, real good time.
Surround me.
Yeah, we cool, yeah, we drunk, lost my mind, and baby, I feel high, I feel high.
They're calling on me.
All I want is to dance with you now, is to dance with you once again. Da 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 da. All I I want is to feel you so close, just to be with you till the end. Da 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 da. We might be oceans apart, but maybe you can hear it's the sound of my heart. Da 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 da. All I want is to dance with you now to the beat of your love again. It feels like dum 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 da 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 da. Da 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 dum 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 da 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 da. Da 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 dum 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 da 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 da. Da 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 dum 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 da 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 da. It feels like dum 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 da 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 da. Da 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 dum 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 da 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 da. Da 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 dum 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 da 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 da. Da 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 dum 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 da 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 da. All I want is to dance with you now, is to dance with you once again. Da 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 da. All I want is to feel you so close, just to be with you till the end. Da 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 da. We might be oceans apart, but maybe you can hear it's the sound of my heart. Da 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 da. All I want is to dance with you now to the beat of your love again. It feels like dum 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 da 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 da. Da 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 dum 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 da 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 da. Da 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 dum 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 da 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 da. Da 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 dum 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 da 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 da. Da 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 da. We might be oceans apart, but maybe you can hear it's the sound of my heart. Da 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 da. All I want is to dance with you now to the beat of your love again. It feels like dum 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 da 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 da. Da 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 dum 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 da 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 da. Da 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 dum 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 da 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 da. Da 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 dum 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 da 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 da. It feels like we go all or nothing, all or nothing. Why not make it count for something? All or nothing, all or nothing. Fight for something we believe in. If we never stop hoping, we'll never be broken. Even if the heart aches, we go all or nothing, all or nothing. Why not make it count for something? When the city lights are calling at night, and you lay in bed, you're thinking your life. Will it ever stop the worry in my mind? You will fight. If we're running away from the problems we see, keep giving up on our hopes and our dreams. We got the power to be who we wanna be. You see, we go all or nothing, all or nothing. Why not make it count for something? All or nothing, all or nothing. Fight for something we believe in. If we never stop hoping, we'll never be broken. Even if the heart aches, we go all or nothing, all or nothing. Why not make it count for something? We go all or nothing, all or nothing. Why not make it count for something? All or nothing, all or nothing. Fight for something we believe in. Passing every red light, I know I'm in over my head. A rebel and I don't hide. Remember all the words that you said. Even if the love was hurting, I'll be your you can make me let go. Forget about the world for a while. You had me at hello. I'm drowning in the blue of your eyes. Even if the love was hurting, I'll be yours. I'll be yours again. I can feel that fire's burning. Give me more. So tell me, would you feel my love? 'Cause I can never get enough. So tell me, would you feel my love? Yeah, I can never leave 'cause I need it, that feeling. Let me feel your love. Let me feel your love. So tell me, would you feel my love? 'Cause I can never get enough. So tell me, would you feel my love? Yeah, I can never leave 'cause I need it, that feeling. Let me feel your love.
I want you for the dirty and clean. When you're waking in your dreams, make me bite my tongue and make me scream. See, I got everything that you need. Ain't nobody gonna do it like me. We are burning at a high degree. And you make me feel like it burns and it hurts. Baby, this part of the rush. This is us. What is love? Baby, don't hurt me. Don't hurt me no more. What is love? Baby, don't hurt me. Don't hurt me no more. What is love? 'Cause I'm wet when I'm wet, I'm popping like Adderall. Baby, dive in my beach and go swimming. Let's go deep 'cause you know there's no limits. Nothing stronger than you when I'm sipping. I'm still gonna finish, I'm drunk, I ain't had enough. One day you hit and you close, telling me lies and it's killing me slowly. Yeah. What is love? Baby, don't hurt me. Don't hurt me no more. What is love? Baby, don't hurt me. Don't hurt me no more. What is love?
10th International OTEC Symposium. We'd like to start things off with welcome from the Ocean Thermal Energy Association, the overall organizer of the OTEC Symposiums. And to give that welcome, we'd like to ask Professor Ikigami, the ex-co-chair of our organization.
Bon dia, good morning, ohayo gozaimasu. So, on behalf of the OTEA EXCO meeting, so as a chair, so I would like to express, express my gratitude. So, first I would like to appreciate Sobena and University of Rio de Janeiro, especially we would like to express appreciate Professor Joel and Professor Shinohara and Professor Estefan and Professor Nishimoto. They are organized specially so to be success our symposium. So, and I'm very glad to the many participants this 10th OTEC Symposium. So 10th OTEC Symposium, this symposium is a very anniversary. So let's start the next stage to the OTEC. So from the Brazil, so as I express potential of the OTEC, Brazil is a huge potential. So Blue Amazon. So please accelerate the commercialize from the Brazil and from this conference. Please enjoy this conference. Thank you for attention.
So thank you, Professor Ikami. Our next speaker is me. So I'm going to be presenting our third keynote. My name is Benjamin Martin. So I've been acting as the moderator of this symposium under the Ocean Thermal Energy Association as the Secretary General. So I handle all of the day-to-day operations of that organization. But I also work for Xenesis Inc., which is a leading heat exchange manufacturer for OTEC and specifically thermal temperature difference applications, not just limited to OTEC, but other applications as well. So I'll talk a little bit about the company and specifically today about OTEC economics. Yes. Okay. I'll try and speak a little bit slower. We are limited on time though as well. So yes, my title is OTEC Economics, Takeaways from the OES Technical Report. So that was also included twice in yesterday's presentations. Okay. So a little bit about Xenesis Inc. So we cover two main areas. So we do power generation system engineering, the process design, and the design of not just OTEC, but small binary power generation systems. We also do manufacturing for them, installation for waste heat recovery, for hot spring power generation, those kind of interesting applications. We also manufacture and design what we call XP plate, all-welded plate heat exchangers. These are specifically built for low temperature applications, and we continue to research and develop to apply them to multiple unique implementations. As you can see, they tend to be smaller, so we can be fit in compact areas, places like risers where if you need to save space and things like that, they're very applicable to those kind of applications. We have a factory in Imari, which is part of Kyushu down here. And so this is where we manufacture all of our heat exchangers. We've been in operation since 1989, and we can supply and have a long track record of various implementations. Some examples, we supplied most of the equipment for the IOES, the Institute of Ocean Energy, Saga University, and their research experiments. We've done discharge thermal energy conversion, which is waste heat power applications. Of course, we supported and contributed to the OTEC demonstration in Okinawa Prefecture. We also have worked with mini-scale discharge thermal energy and recently hot spring thermal energy conversion as well. Okay, so diving into the core of today's discussion, it's the IEA OES Technical Report. This was published this year in March, and it updates and kind of is looking to extrapolate what's the economics of OTEC. How do we get from where we're at today to commercialization? What are the challenges and maybe some hints towards how to go forward? This was a dual-authored report, both myself and Dr. Vega of the University of Hawaii previously. We come from very different backgrounds in terms of he has a lot of offshore experience and he's working towards large scale. Whereas in Japan, we're working more on small scale onshore applications. And so there's a little bit of divide. And of course, in the OTEC community, there's a little bit of divide and different opinions on this as well. But we tried to come up with a way to integrate and understand the overall situation in terms of OTEC development. So IEA OES is a technological collaboration program under the International Energy Agency. And so it's limited to members, countries within IEA who are interested in working on ocean energy. And specifically, this study was led by a task focused on OTEC, and the countries collaborating included Korea, Japan, China, France, and the USA. So where are we at? So this is deep water intakes around the world. There's more than you probably thought. There are 38 places with 45 deep water intakes already around the world. And so this started in Hawaii in the 1970s. First one was installed there, but after that success, they've continued developing. Now there are 3 intake lines in that one country alone. In Japan, we have 15 sites with 18 pipes. There's 8 intakes in South Korea, 5 in Taiwan, and 8 in India. They've mostly been working on LTTD, which we heard the presentation yesterday, which is low temperature thermal desalination. And 3 in French Polynesia, and this is mostly for cooling, for seawater air conditioning. So hotels, and more recently, a whole hospital has been converted to deep seawater use for this kind of process. And of course, for OTEC, as many of us know, it's not a new idea. It's started as science fiction, written by Jules Verne, 20,000 Leagues Under the Sea. Science fiction inspired a French physicist to start looking at this. And so over the years, there's been step-by-step development. As offshore technology has matured, as materials have matured, it's become more and more viable, and we've seen more and more interest. And this interest is not just by country, but now among many, many countries, because many, many countries have access to the ocean. We see them using more ocean water resources through the intake pipes. And now it's a matter of scaling what we've already done and applying that to the needs we have that are continuing to grow. Most recently, in Japan, we've used our demonstration to enable long-term operation. We've had our demonstration for more than 10 years now. 10 years of operation and maintenance. We understand the costs and use well. IEA OES also supported an initial white paper on OTEC, looking at the technology. Where is it today? How's it looking? This was back in 2021. So this kind of started the discussion on where is the OTEC technology, but then the question is, okay, then how do we pay for it? And so that's where our paper and this report comes in today. So the whole report is available for free on the website of IEA OES. But I wanted to share just some kind of interesting takeaways from this as we developed it over the course of about 1.5 years. So in terms of government and policy, we are seeing more and more interest in OTEC and more governments putting it into their policies, and that helps kind of create a framework for individual companies and organizations to work under. So the state of Hawaii has included OTEC in its definition of renewable energy since 2001. And so that's encoded in the Session Laws of Hawaii, which is the state-level government laws that they have. Turks and Caicos included in their Island Vision in 2019. Kumijima Town, where we're located, included OTEC in its Energy Vision 2020 as a kind of backbone for its strategy to get to 100% renewable energy by 2040. In 2020 to 2040 Philippine Energy Plan includes OTEC. Sao Tome and Principe's National Renewable Energy Plan includes global OTEC's proposed plants. And in 2020, the government of Malaysia included OTEC in its national energy policy. And in 2023, the government of Mauritius included setting a 1 megawatt OTEC plant in their budget newsletter. So there's a lot of momentum. More recently, we've heard that Malaysia has included, several states have included it in their policies as well. So this continues to grow, and it's helpful for supporting, because if you ask for funding for a project, and the first thing you'll go to the government legislation and see, is OTEC even included in the definition of renewable energy? And if it's not, it'll be very difficult for OTEC to be included under one of their government schemes or the support agencies and things like that. The biggest thing we had to do with this report is, what's the levelized cost of energy for OTEC? Now this is difficult because unless you have built an OTEC plant, it's hard to understand the costs. So in order to understand the costs, we can do things like studies. What Dr. Vega chose to do was take off-the-shelf parts, put them together, and then calculate the cost for that. Now, some of the components you can get quotes for. Some of the costs are well, standard, but they're not really optimized for OTEC. So you're going to have to use more of them, or 10 times more expensive than you would expect in a commercial application. So what we did is we included his costs, but we also included experience from Japan, where we've actually built our OTEC facility and then have applied that to costing similar designs or specialized parts for, say, heat exchangers that we built for OTEC, and applying that to a range of costs to give an overall idea. Now, this is just a desktop study, so we didn't have funds to go and actually pay a bunch of companies to design and build an OTEC facility, which would probably reduce costs here. But what Dr. Vega does do really well is understanding the levelized cost of energy in a conservative manner. So we're looking at including inflation, including inflation costs and interest costs throughout. So it's relatively conservative calculation methods. And from this, from both 10 megawatt up to 100 megawatt, we have a range of expected costs for both closed cycle and open cycle. And through this, even with, unfortunately, high water prices for open cycle, we see that it is generally considered to be more expensive. And so it's not something that we should really probably be prioritizing as a development for OTEC in general, but it can be useful, for India, for specifically places that need a lot of water and may need to approach it. So for Japan, we consider offshore 10 megawatt to be potentially around 21 cents per kilowatt hour. A lot of these costs are much higher. And you'll see that some of these are with different heat exchangers. And so we'll dive into why some of these numbers kind of change, because if you're using off-the-shelf heat exchangers, then of course they're going to not be applicable to OTEC. Maybe you need many more of them, and so then the costs get quite high. And of course, how much does interest affect the levelized cost of energy? So when they asked us to understand the cost of energy, they want to put apples to apples. OTEC and PV, which is cheaper? Of course, PV. But what is included in the PV cost? Is it land? Is it shipping? Is it the full manufacturing capacity? Or is it just the result of tens of years of worldwide development and the final product of a subsidized and cheap energy? Whereas OTEC, we're struggling because we don't have that level of support and development and subsidy to kind of develop this and bring the cost down. But there are unique benefits of OTEC in terms of providing fresh water, energy, and food for local communities. So there's potential for achieving low interest rates, for helping and finding concessionalized loans and things like that for specific applications. So there is potential to reach kind of this lower interest rates, where if we are thinking about OTEC and comparing OTEC to other technologies with a more understandable interest rate, then it can be competitive. But if we start talking about commercial OTEC at the first stage, the first plants that we're doing, of course, you're going to be at much higher interest rates. Doesn't make much sense. So that's something we have to be a little bit careful about. Is when we're talking about OTEC as a commercialized plant, that doesn't necessarily mean we have to use commercial interest rates. And that won't make sense until further down the line when we have more plants in the water and the costs have come down. Another thing we looked at, and this is specifically for Dr. Vega's application for OTEC costs, is how much would a change in his estimates affect the overall cost associated with OTEC? And one of the things that comes in here is the conservative aspect of these estimates. So if you're very conservative, and of course you get a higher cost per kilowatt hour, then when you're comparing with other technologies, it doesn't look as good. So ideally, we want to be as cheap as possible, but also realistic. And so you see this big red line that's way more vertical than all the others, and that is maintenance. So how much do we understand the actual maintenance cost of OTEC? And most places around the world have no idea because they've never done it before. So they use like a random number like 5%. And that has nothing to do with the actual situation. And so that creates situations where it dramatically increases the cost for no good reason. And so what we've done in Japan is then take the operation and maintenance over 10 years, understand the actual costs involved with operating a facility. We've automated the operation and maintenance as much as possible. So if we turn it on, it operates. If there's a problem, it lets us know, and we can go and maintain it. But somebody isn't sitting at the OTEC facility 24/7, and that reduces personnel costs, it reduces operation maintenance costs. There's very few moving parts. We have the turbine and pumps. The rest is static. There's no high temperature. There's no very, very low temperature. So there's very limited thermal stress on these components. And the components that are used for seawater, if we select titanium for our heat exchangers, if we select materials correctly, this can be significantly reduced. And so, unfortunately, in this report, again, we see a big variation is because this offshore maintenance cost is unknown because hasn't been done yet. And so this is what the demonstration, this is what I think Brazil can really help with, is understanding what would be the maintenance and operation cost for an OTEC facility offshore. And that's what the demonstration next step for, I think, OTEC development needs to be to move offshore, is bring this number down to a reasonable, understandable level so that we can more easily justify the lower costs, lower LCE, levelized costs of energies that we can achieve. Of course, we can do this onshore. We have the experience, we've already done it, so we can give a relative figure for onshore OTEC. But for offshore, even our company, we haven't done this yet. So in the report, I wrote about half of it, and I focused on onshore OTEC. And so for onshore OTEC, we of course have the long intake pipe that increases the cost, the capital cost of the overall facility. But we also get lots of benefits, and this is a slide that Professor Ikigami showed, that if we can separate the infrastructure from the benefits, then this makes each component then available to compare directly as a business with their counterparts. So then OTEC becomes the capital cost of the OTEC facility itself over the time of its use, and then it has benefits such as sales of electricity. And that's very easy to compare to PV. And that also becomes competitive from a private sector. So even at the small scale here, then we can introduce it as a business. But that would require then the intake facility to be established either by government or by a partnership that can offset those costs through sales of seawater over time. And so this is not something that can be done everywhere, but it can be a huge contributor to places like Fernando de Noronha, where there is needs for these applications, where if there's a way to either reduce the cost of the intake or subsidize it, then that can allow for all these other industries to come in on the private sector scale. And so for this kind of report, then how do you quantify the potential benefit, the potential offset of that cost or the potential benefit for this infrastructure investment? Because every location is different. On our island, we bring in $25 million a year in revenue. We expect to expand that intake capacity and expand that benefit. But until you actually have those businesses operating, there's some risk involved. Do they use all the water they expect to use? Do they run into development problems? They build a farm, maybe it take a few years to get to full capacity. And so those all become very difficult to quantify. And so for this report, we proposed a specific kind of way forward. So for operation and maintenance on onshore OTEC, we used direct data from this research facility, the 10 years operation of the 100 kilowatt OTEC demonstration in Okinawa. And then we were able to calculate all of the costs associated to get to a total annual cost and then a cost per kilowatt hour. So the cost per kilowatt hour for an onshore OTEC facility of 1 megawatt scale is expected to be about 3 US cents per kilowatt hour. 3 US cents per kilowatt hour means that as long as we are selling for above 4 cents per kilowatt hour, we can cover the operation and maintenance costs for the OTEC facility. Of course, that doesn't include the capital costs, so we'll talk about that more later. So in this report, we looked at what are the different ways we could do OTEC right now as a project. And one is ODA, Official Development Assistance. So some rich countries that maybe have OTEC technology or have been working on it for many years don't necessarily have the resources locally to take advantage of it. This is something that's happened in Korea. It's happened in the United States, where in the United States, it can be used in Hawaii, maybe Puerto Rico. We heard from Andrea Coping yesterday, they're looking at it for Guam. they're not looking at it in New York because they don't have the temperature difference. They're not looking at it in California because they don't have the temperature difference. In Japan, we can't do it in Hokkaido. We can't do it in Tokyo. We can do it in Okinawa, though. And so this is something that, as the world is looking at more needs for renewable energy, but also higher concerns of seawater level rising, of the impact of rich countries and their effect on the developing countries, this is a way that we could potentially start contributing to carbon dioxide mitigation and adaptation and global warming mitigation and adaptation. So there is some interest for countries to support these kind of activities. And that means there's funding for supporting these kind of activities. So if a company or a country comes in and says, we'll give you an OTEC plant, we'll cover the capital costs, what's the cost to the country? Because it's not necessarily going to be free. You still have to buy the electricity, and then you have to set a price for that electricity. So we understand the amount of power a 1 megawatt facility could produce, and say, even if they want to bring in the OTEC facility, the pipe is still going to need some operation and maintenance costs, right? So the pipe, we're pumping water, there's some costs associated with that. So even if you give everything free, the operation costs for the pipe and the pumps and the OTEC facility need to be covered. So we can pay for every $100,000 paid from OTEC power production to a seawater intake, a separate entity, say, it will cost about 2 cents per kilowatt hour. And that means that to cover the operation and maintenance costs of the OTEC facility, we can pay up to $600,000 per year to the intake facility and still have a 16 cents per kilowatt hour operation cost. So for ODA, there's a wide range of applications that this can be applied to, reducing the cost of energy for these locations, but also still creating a viable business model for deep ocean water use. There's lots of other ways we can start implementing OTEC as well. We have PPAs, subsidies, larger subsidies, and so this starts kind of affecting the levelized cost of energy we can expect for OTEC. Now, this doesn't include the intake pipe. We've taken the intake pipe out. That's a separate infrastructure project. If we're just bringing OTEC in under these different scenarios, what does that start looking like? So power purchase agreement, just buying, including the capital cost of the OTEC facility over the lifetime of the loan or the agreement. If we're looking at a short-term 20-year loan, it's difficult to be competitive if you're including the whole power cost. But extending that just another 10 years, because we expect an OTEC facility to be viable for up to 40 years or more. So if you use it for, say, 30 years, then you're at less than 20 cents per kilowatt hour. You're cheaper than diesel. There's enough profit there for the power company to buy it and still sell it to the local grids at less cost. And so there's significant benefit, even at the mid-level of a PPA. With a little bit of subsidy, 30%, all of these then are significantly reduced. So at our initial stage of development where we're at in OTEC, a small, 30% is not small, but some subsidy can significantly accelerate the implementation of onshore OTEC. A larger subsidy, of course, would make it very profitable for the developer who's trying to do this, but then significantly reduce the cost of energy for the domestic market that would be using it. So if you're looking at reducing costs and doing it renewably, this is one way we can do it and significantly accelerate implementation. So this is a little bit hard to see on the LCD, but all the different strategies, all the different kind of things we look at and the corresponding costs associated with that. This is in the report. You can look at it at the back. So we have the operation maintenance cost. We have the different kind of things. We looked at carbon credits. I mean, carbon credits don't add a whole lot right now, and there's not like an international consensus about how to do this. Individual countries have ways of doing this, so we looked at those and tried to create a couple different scenarios. But almost all of these are below 20 cents per kilowatt hour. So we're saying that if we can figure out how to do the intake, be it as a separate infrastructure, separate business, new technology, whatever we have to do to get there, OTEC itself, compared apples to apples, OTEC and other power generation systems, can be done. So let's figure out how to do the intake. So in Japan, what we've been working on recently, we have a JICA, which is the Japan International Cooperation Agency, supported feasibility study working with Palau which is a country near the Philippines in the Pacific Ocean. So we're helping to develop what we've already done in Kumijima and see how we can apply that to this location, a new region. Of course, there's different needs, there's different demands, there's different culture, and so we have to look at all of those aspects. The environmental impact assessment, we're doing all of that. And so this is the first kind of artist rendition of what we're proposing for this location in Palau. And JICA has created a video for us to highlight this at the last COP. So we'd like to show that video, and that'll end my presentation. Can you show the video?
In developed countries, it is expected to accelerate even further with the economic growth of emerging nations, leading to intensified competition for resources. Global issues such as CO2-induced climate change are becoming even more severe. As the search for a stable supply of alternative energy continues, an innovative method of power generation is beginning to take shape on a small island in Japan. Unlike variable renewable energy sources like solar and wind power, which are affected by weather conditions, this method can provide a stable supply of electricity 24 hours a day. Not only is it environmentally friendly, but it also has the potential to contribute to local economic development. This clean, alternative energy source is OTEC. With climate change advancing, and energy security becoming a critical issue, highlighted by the invasion of Ukraine, JICA recognizes that energy transition is now an unavoidable challenge for all of humanity. However, neither the current technology, nor forcing developing countries to abandon fossil fuels, is a realistic solution. There is a need for affordable methods that do not hinder economic growth. Developed nations have a responsibility to ensure that developing countries can fully benefit from next-generation decarbonization technologies. At JICA, we aim to provide support that aligns with each country's circumstances and fosters economic growth, embodying Japan's unique spirit of compassionate assistance. One such initiative is being carried out on a small island in Japan, Kume Island, located about 100 kilometers west of Okinawa's main island, with a population of around 7,000. On this island, an experimental introduction of OTEC, a rare power generation system in the world, is currently underway.
海洋温度差発電は海の温度差だけで発電する環境に優しいエネルギーというのが大きな特徴です。24時間安定して発電できるというところが一番大きな特徴でありますし、世界中から期待されている要素です。再生エネルギーの中で地熱エネルギーと同じくベース電源になれる非常に重要なエネルギーの一つだ。利用できる温度差が20度と非常に小さいですので、この効率をどう上げるか、経済性をどう上げるかというところが大きなハードルでした。重要な熱交換器、プレート式熱交換器の形状や特徴が他の国と大きく違います。これは日本オリジナルの熱交換器で、海外の熱交換器に比べて非常に性能が高いというふうに評価されております。で、2つ目にいろんな産業への貢献ができることも海温度差発電の大きな特徴です。世界中に電気と水、また持続可能な社会を求めてある地域がたくさんあります。そういうところに一日も早くこの日本で育まれた海温度差発電が実現することによって、より持続的な社会が加速度的に推進されるというふうに確信しております。
In the evaporator, where liquids with a low boiling point, such as ammonia, are contained, warm surface seawater is applied to the liquid, causing it to evaporate. The resulting steam drives a turbine, generating electricity. After passing through the turbine, the steam is sent to a condenser, where it is cooled by cold deep seawater, turning back into a liquid. The liquid is then cycled back to the evaporator, and the power generation process repeats. Generate clean energy continuously without emitting CO2.
再生可能エネルギーというのはまだまだ
全然今のような主力電源になるとは思われてなかった時代なので、大手のそういう熱交換器メーカーも開発をなかなかやってくれない。かなり小さい温帯を使うので大量の熱交換器を使うと。しかも片側が海水が通るので腐食性がすごく高い。でもう片側がアンモニアですとか、それから代替フロンのような低沸点の媒体ですね、そういうものを使うので今までにないような熱交換器を作らなきゃいけないと。パラオの場合は冬場ほとんど下がらない28度とかをキープし続けると。久米島の場合は22度ぐらいまで下がると。最適な海水温っていうのはどこに合わせておくか、バランスを取るっていうのは設計としてはかなり難しくなっております。ただし作ってしまった後の運用が難しいかというと実はそんなことはなくて、一度動き出したらずっと人が見てなきゃいけないとか、そういう形ではないです。特に最近もうすでに気候変動で地球の環境が変わってしまっている、水産とかそれから農作物とかそういったものが不調になってきているという現実があります。でそれに対して単純な CO2 削減だけではなくて気候変動適応ができるっていうのがまず大きいです。特に当初の海が近い島ですねっていうのはもともとその化石燃料資源も持ってないし、温暖化の影響を一番受けている地域ですので、そういったところに対してこの海の水からエネルギーもできるし、食料とかそれから飲み水とかも生産できる、そういったところがゲームチェンジャーたり得る技術だと考えています。
Kume Island, with its favorable terrain and infrastructure, has been a hub for OTEC research and development for over 20 years, driven by Genesis and Saga University, which has been researching for more than 50 years. This collaboration between the two, along with OTEC's greatest strength, is its stable supply. The temperature of deep and surface water remains stable throughout the year. Unlike wind or solar power, which are subject to environmental fluctuations. This deep seawater, which takes about 2,000 years to circulate globally, is not exposed to sunlight, meaning photosynthesis by phytoplankton does not occur. As a result, inorganic nutrients are not consumed, leaving the water rich in minerals. Furthermore, the water is free from organic material and man-made pollutants. The water quality is not only stable but also exceptionally clean. Even after being used for power generation, the water quality remains unchanged, making it useful for a variety of industries. The Kume Island model is not only a clean baseload power source, but also contributes to local industries, providing secondary benefits to the region. This is the Kume Island model. These benefits span across a wide range of sectors, from primary industries like fisheries and agriculture, to secondary industries like food, beverages, and cosmetics, as well as initiatives in education and tourism. The model even includes environmental improvements such as coral farming.
世界初の挑戦となる牡蠣の完全陸上養殖に取り組んでいます。本当にとにかく安心安全な当たらない牡蠣を作りたいということで、事業をスタートしたんですが、有識者の先生方にご相談をしたところ、皆さん口を揃えて、そんな馬鹿げたことはやめなさいと。もう無理そんなことはと。もし本気でやるんであれば、可能性があるのは久米島でしょうねと。亜熱帯の日差しと海洋深層水で植物プランクトンを作ることによって非常に安価に大量の餌を作り上げることができています。もう海外では昔から空港や駅の中にはオイスターバーがあってですね、食文化として根付いてきたものです。今世界中の海域養殖が大きな影響を受け生産量が減り、日本へも輸出の要望等々が来ているというふうに聞いています。豊かな海に戻してあげるまでの間、こういった技術で何としても文化を守り続けたいなと考えています。例えばパラオへの展開、微力ながら関わらせていただいている中で、こういった日本の技術、そういったものをどんどん島嶼地域に展開することで、次の世代の子どもたちに引き継ぐことが必要だというふうに考えています。
目に見えないような、顕微鏡でしか見えないような植物プランクトン、これは微細藻類と言ってますけども、これがもう一つの資源であるというふうに考えていて、それに注目して今事業を作ろうとしております。もともと薬を作る会社だったんですけども、そこに頼らない製薬会社を目指そうという、食であったりとか教育であったりとか、美容であったりとかウェルビーインと言われる広い大義で総合的に健康を作っていこうと。微細藻類育てる時に深層水を使う すごく価値があるところとしては、一つは栄養が入ってるっていうところが一つ。あと深層水自体がすごく綺麗なので、育てたい藻以外の他のものが入っていないっていうのがすごく大事な育てる際の必要なことなんですけど、それが担保できているっていうことで、あとはガラスチューブで夏がすごく熱くなってしまう性質があるんですけども、深層水の冷たいエネルギーで冷やすっていうこともできるので、産業化させていくにあたっては理想的な資源、一つの新しい農業ができてきたというふうに我々捉えているので、生産して研究して商品開発してっていうのを自分たちだけでやってるよりかは、その一般の人たちにも知ってもらう機会を増やすっていうことが結局はその市場を作っていくっていうことにつながっていくと思うので、単なる研究というものではなくて、観光農園と同じようにその観光の藻類農園というのを今作ろうとして観光と絡めようとしています。
平成27年度時点で海洋深層水関係売上高が約25億円、雇用者数が300人と算出されております。日当たりの取水量が1万3000トン、規模拡大を図った時に18万トン、その時の経済効果としては約80億円と推計されています。2000年に海洋深層水研究所が開所して技術移転が行われて、そこからさまざまな産業が起きて、化粧品であったり海ぶどう、車エビの養殖、魅力のある仕事の創出っていうような施策を打つには、非常にこの海洋深層水事業は魅力的だなというふうに感じております。
In both energy and industry, the Kume Island model, with its collaboration between government, industry, and academia, is an ideal energy transition strategy that revitalizes the local community. To expand the Kume Island model, JICA invited Palau for a site visit and conducted on-site surveys in 2023 to begin gathering information and conducting assessments. Palau is a beautiful island nation, home to the Rock Islands and Southern Lagoon, both UNESCO World Heritage Sites that attract divers from around the world. However, like many other island nations, Palau has few industries outside of tourism. It relies heavily on diesel power generation, and most areas depend on rainwater for drinking water. We suffer from water shortages during droughts and other natural disasters. If the Kume Island model were introduced, Palau could not only secure a clean baseload energy source, but also develop industries, such as seafood and leafy vegetable production. Moreover, with efficient desalination, the model could provide large amounts of drinking water during droughts, contributing to the nation's security. The Kume Island model has garnered attention from around the world, with 69 countries having visited for study so far. Even now, inquiries continue to come in from other island nations and United Nations delegations, highlighting the growing interest and demand for this model.
One of the challenges of OTEC is the initial cost. If this cost can be reduced through innovation, OTEC can reach the practical stage. That means every island country can enjoy the OTEC. Many island countries have same challenges. Energy cost is high, industry is limited, and water shortage due to drought. The Kumejima model can provide not only electricity but also industry and drinking water. Annual sales of deep sea water business such as aquaculture in Kumejima are over $20 million. If such an industry develops in island countries, it could add value to the tourism industry. We understand developing countries cannot accept carbon neutrality without growth. Energy must be affordable. Invasion of Ukraine makes energy supply unstable and expensive. Japan has a responsibility to ensure so that developing countries can enjoy the benefits of next generation decarbonization technology. Our goal is to realize both carbon neutrality and stable supply of affordable energy with developing countries. We have three pillars. First one, energy transition policy and plan will be formulated, updated, and implemented. Second, next generation decarbonization technology will be developed and installed. Third one, regional power pool will be promoted. Power development and expansion of international power grid. So we have several promising technology, for example, e-fuel, nuclear fusion, space solar power system, and OTEC. Many developing countries are expecting the new generation technology in Japan. JICA strongly supports empowerment of researchers and joint research and development between developing countries and university in Japan.
So sorry for going a little over time, but now we have a coffee break in the back. So if we can go to the back room and have a small break, and then we'll come back shortly after for our next symposium group.
yeah. Pull up in the rinse in my brand new whip and go. With a full eclipse and the moon lit like whoa. Everything blurred, mixing all that smoke with the gray goose. Fanny baguette on the bar top, both my hands on you. Take a picture of my figure.
Okay, welcome back. This is our next official session in our second day. This is session 5, focusing on projects, ocean thermal energy conversion projects. Our next speaker is Ocean Thermal Energy Driven Activities in Malaysia from Dr. Satya Bama, Director of the UTM Ocean Thermal Energy Center in Malaysia.
Okay, shall we start or just wait? Start, eh? Start. We are running behind time also. Eh? Okay, thank you, Benjamin. So I'm Satya. My full name is Satya Bama T. Tirunyana. Please call me Satya. All right. And I come from UTM Ocean Thermal Energy Center. Okay, recognizing the project members, leaders, directors of our work in Malaysia, and of course our close partner, Institute of Ocean Energy, Saga University. All right, so we are there. All right, so this is the outline. So you already heard about, what is ocean thermal energy, conversion, and, the marine renewable energy, whereby wind is not a marine renewable energy, even though, it is close to the ocean. You already know that, and projects in the world, not many I have details on world projects, you already heard a few earlier, and our activity in Malaysia and also the way forward. The ideas that we would like to put forward, so whether it's going to materialize is depending on how we push things. I'm trying to push the button here. Okay. Got it. So this is, you already saw OTEC facilities onshore, offshore in the world. So just a quick recap. Some I've left out, I think, because I also realized in the Mauritius, in the La Reunion and the French Polynesian, and so on, they have lab activities and so on. So from the older one, I think this is, year 2000 or so, the NIOT is here. And then Saga University in their Imari, IOES, the institute. Then followed by the Kumejima, the 100 kilowatt. Then the Hawaiian 105. Then the Korean, the floating type there, 2019, which is supposed to, prove 1 megawatt. Unfortunately, due to pandemic and so on, not able to. Then in China, which you don't really find that many in the public domain, but something floating on OTEC. Then we are the youngest in Malaysia here. 3 kilowatt, but it's very, very important to have one. In that extension and way forward, there are also industries. Shipping company, I think Prof. Ikegami also mentioned yesterday, Mitsui OSK line. It's a shipping. They are supposed to be the world's largest shipping company. Right? Why a shipping company is working on OTEC? That's a question we ask, right? So think about it, why? Okay, but they have their reasons why. So that being said, supported by the METI, of Japan under the NEDO project with Genesis, they have been embarking and trying to do a feasibility of 1 megawatt in Mauritius. So also acknowledging our OTR. I said it yesterday, please join OTR, it is still free of charge. All right, membership. So then bringing us to the world, this map you have already seen many, many times, yesterday and also today. But putting Malaysia in perspective, highlighted in green. So that is where Malaysia is located. And looking, diving a little bit more into Malaysia where, as you already know, we need deep sea water, right, for OTEC to work, all right? the peninsula Malaysia, which is connected to Thailand, we don't have deep sea water around that area, all right? So that's where we go to the East Malaysia. And we have Sabah, and we have Sarawak. I think you saw the same map in Prof. Ikegami's slide presentation. So a little bit overestimation, yeah, is the 26 gigawatts overestimation. But if you want to underestimate, we have also another figure, 12 gigawatts. All right, some papers we have already published to show how we did the calculation and, with the water mass, you can check it out. And approximately, yeah, we take like 1,000 meter depth. However, the shorter, the better. So that is why we need a feasibility, a scoping, to go to the site to check how far is it, and how deep. The shorter, the better. For this Sabah, we have done some work, and it's approximately like 600 to 700 meter depth is sufficient, yeah, to get that 5 degrees C or 7 degrees C. To have the delta T of 20 degrees C, right? That's what, the greater the better, of course, but at least. Okay, so that is there. And yeah, this is what I was saying. So temperature profile and other profiles are profound for OTEC. And these are the sites such as Tawau, Sipadan, Kalumpang, Layang-Layang, Bangi, we have already checked. Desktop study, yeah? Then surface seawater being 27 degrees C or so, with a depth of 600, you can get that 7 degrees C. So we have a delta T of 20, yeah? Then the salinity, yeah, DO and so on is also profound, it's good to go. Water mass is sufficient for us to generate the 26 giga or 12 gigawatts, yeah? Then this is a fundamental of closed cycle OTEC, which you already saw, but just to recap, yeah, putting things in perspective, the surface seawater going into the heat exchanger, also known as the evaporator here, evaporates the working fluid. And that working fluid in a gaseous form turns the turbine, and the turbine is connected to a generator, generates electricity, right? The working fluid, in the gaseous form comes to the heat exchanger called the condenser, and the cold 5 degrees C or 7 degrees C cold water condenses the gaseous working fluid back to liquid, and this cycle goes on, right? So unlimitedly, because primary source of energy has stored the energy in the ocean, and 70% of the earth, or the world, world is ocean, right? Of course, you need deep sea water. So that being said, we from UTM Ocean Thermal Energy, learning, in the process of course, we have been learning for the past 5 years, now we're moving on 6 years from Saga University, and putting effort. How can we design a better and efficient OTEC system for Malaysia context? Yeah? So, of course, to date we know that the best efficient working fluid is ammonia, right? So we also need people, talents, working on ammonia, to, if at all some incident happens, what are the countermeasures that needs to be done? You need people with such talent. We need to groom them, you see. So that is there. We already know stable power supply 24/7 by OTEC. So OTEC and its spin-off, we have learned a lot. I just said we learned a lot from Kumejima's model and so on, right? But we can't copy and paste it in Malaysia. Yeah, we have to localize. So that process takes some time. And funding is required, of course. Yeah, and people must come with passion to do that. So I anticipate the same for Brazil in, the way forward, yeah, for you. So just sharing a bit, this is also, a slide from Prof. Ikegami and his team. So OTEC not only combating the energy issues, also access to clean water, food supplies, rare earth mining, SWAG, and data center cooling. Just to share with you, in Malaysia, but in Johor actually, it's the peninsula, lots of data centers are coming in, now. It's taking place somewhere near to Singapore. But we are also thinking there's no deep sea water down. Maybe Indonesia you can go, but that's another idea. But that being said, data is money actually, right? There's and Google and so on, data centers are mushrooming. So how can we, that meaning energy also would explode. So energy is also a very, very crucial yet important for us. And renewable energy is what we are talking about, right? So, and many more. Yeah, why did we put many more? Is we are still exploring. What is best for Malaysia? Yeah? Of course, you saw this earlier in the video, and Kigami Sensei, and also Benjamin also. So we can't copy and paste it in Malaysia. So we are still in the midst of identifying what is the best local model, and we would like to call it a learning process from the Kumejima model to Malaysia model. That's actually supposed to be the end, of our project, which we are still working on. Yeah. Right, so of course, sustainable local community empowerment is very important. We empower, we engage, we listen to them. Not only we talking a lot and not listening. Yeah. So then, for what? For energy, water, food security. Yeah. So then, the research that we are doing, right? For the past 5 years, another one. Next year, March is going to end. So it's called the Science and Technology Research Partnership for Sustainable Development SATREPS program. It's a mouthful, but that's what it means. So sustainability is in the core. So whatever we do, okay, how are we going to sustain? Project ends. That's another thinking we are having now. 5 years, 6 years done project. How are we going to sustain our plant that we have? What are the things that we must do? Yeah, we are quite a huge group actually. Almost 60 our members, from many universities and also institutions. Funding, as you can see there, by JICA. You saw the video earlier, right? They have funded, and JST. And then Malaysia is a little fortunate that the Ministry of Higher Education gives a little bit of matching, that is what we use to move and do our project work, project activities. And IOES, Saga University being the leader on the Japanese side, and University Technology Malaysia is the leader on the Malaysian side. So we saw the OTEC just now, right? Trying to explain to you how it works. That is called the closed cycle OTEC. And then in this SATREPS, you can only get SATREPS when you have some novelty in your technology. That is properly patented by Saga University and the company's NSCs. So what have they patented? This is what they have patented, which is the hybrid OTEC system, whereby it is the combination of the closed cycle and the open cycle. Closed cycle to generate electricity, open cycle to produce desalinated water. And we have tested it. Yeah, we are very happy to announce that we have tested this side, electricity, 3 kilowatt plant, but we got about 3.5 kilowatts, okay? We are safe. We are not below, right? We are okay. And then we have also produced the desalinated water. But there was a little bit desalination process, a little bit hiccup, which we are doing the maintenance and improving so that proper desalination is out. That's why I'm unable to say so now, so that is there. All right? In the middle there, as you can see, I told you technological novelty. For SATREPS, I repeat again, because many of you maybe want to apply for SATREPS. Novelty must be there. So what is novel can you think of? So the Japanese properly thought about it, and as I said, they have patented it, right? So that's the technology novelty, which is combining, the hybrid, they call it the hybrid heat exchanger, evaporator and condenser. Surface seawater going into the chamber, which is already vacuumed, and that immediately it vaporizes. Flash evaporation takes place of the surface seawater, and that water becomes H2O, gaseous, and passes through the hybrid evaporator there. That vapor is still warm enough to evaporate your, what you call on the other side, okay? We didn't use, okay? We wanted to use ammonia, all right? Due to certain reasons and, our learning process also, we have found out that it's best to go with R134A, So we are using the Freon, R134A. And we got that 3.5 kilowatts, So to date, after when maybe by in a few more months, we will need to validate and confirm that this is the most advanced OTEC system to date, yeah, the hybrid one, which we yet to do. All right. Under the SATREPS project, this is another sharing also. We have we were quite ambitious, and to have 10 over projects, 10 projects. So that's where you have 60 over members, as I said earlier. All right. So which starts from the facility, the building itself, and to operate and to run the 3 kilowatt of hybrid OTEC. Then we also included with the Japanese iced, they call it, to calculate the LCA, right? When you want to compare, okay, you have solar, how good is your OTEC, right? So the LCA, so we have some figures and doing that into, LCA analysis, to see the carbon footprint. Then we also have to check. Yeah, somebody asked yesterday, I think, the water quality, before and after the hybrid OTEC. How is the quality? To check that, to really confirm that OTEC is, not so bad for the environment. Okay, all right. So then 3 kilowatt, the turbine. Okay, we are still in the midst of developing, and this is done back in UTM. Most probably in January we will plug it in and run. Okay, you may be thinking, why did I say we confirm 3.5 kilowatt without the turbine, right? Okay, that's the isentropic power. Yeah, with the pressure and with the temperature and the flow rate, we have confirmed, through the simulation that 3.5 kilowatt is, there. When you plug in the turbine, having the turbine efficiency, okay, what is going to be? We have to check that out. Then, of course, we have some aquaculture members also, in our team. So they are doing some, seaweeds, seaweeds, and also some oyster. But this oyster is not the Japanese oyster; it's the Malaysian oyster. We have a species in Malaysia which they want to test and see. So this type of ideas, localizing is very, very important, and Then, of course, another team also doing on the water quality, and then the working fluid, I did say ammonia and we are using freon, but what if we have a nanofluid? Yeah, many of you all from the engineering, you may know, have heard about nanofluids. So even lesser delta T, what if you get a working fluid that can work even less delta T, right? A smaller delta T. So that's the idea for number 10, and then putting all this in a business model kind of thing is number 10. So you have to plan and think, in such a way, and of course your big consortium with 60 over members, I said earlier, has to be managed. Yeah. So that being said, pandemic was also a little bit hard on us, but maybe not as others. Yeah. So that's why we usually this project 5 years, but we got one more extra because of that. Yeah. And next year is going to end. So the construction of the building or the facility, and then bringing installation of the HOTEC, which came from Japan. Yeah. Why is this so slow? Okay. Okay. So you saw The photo on the other side is when the HOTEC, the hybrid OTEC, was in Imari, in Kyushu. Then our building completed. Actually, before completion, we had to bring it. We can't prolong, the delay. So somehow, when it's all happening there, we try to install. Yeah, we have an overhead crane also to assist us on that. Installation completed. So as I said earlier, I would like to repeat. Designed and developed by Saga University, IOES, and Genesis. Yeah, so that's there, and the test and commissioning or the training, handover done just October. Now we are in December, right? So 2 months ago. That's why I don't really have much data to show on the running part, but we have run it on ourselves own, and we are confident of running it. Running the system. So then, as I said earlier, the working fluid, is R134A, and we have confirmed, 3.5 kilowatts, isentropic power. So next is just to put in the turbine and then do more work. All right. Then technical evaluation, we really want to, because some things we had to change to really confirm the desalination and so on. So will be done. The surface seawater, from the Teluk Kemang, this is called Port Dickson in a state called Negeri Sembilan, about 100 kilometers from Kuala Lumpur, right? By next year, March, because the project will end next year, March. So in that extension, Shell was also interested to know what OTEC is all about, and they gave us, they had some interest to know. So with the seed funding, we started to also work with them, and successfully completed and submitted the report, and waiting for their comments. No comments yet, hopefully no. So that is there with Shell MRE. Okay. This is a university in Sabah. Okay, this is the time when we went to Sabah. So some engagement with the local people and so on. Of course, not only the local people, the energy industry in Sabah, the environment, the economic development in Sabah, the university and the community. We went to some villages and asking them what's their problem. Of course, they are doing rainwater harvesting and so on. Water is a problem, energy is a problem, which eventually food is also a problem. All right, so this is some engagement, photos, I know, already time. So, you may have, so about 20 kilometers from the east of Sabah. Then if we have on land, there's a small reef, here. So on land, then we can tap the seawater, the deep sea water within less than 10 kilometers. All right. So I'm coming to the end. This is a map to show the bathymetry. So if we have the on land here, this is 20 kilometers. So this is less than 10. We can tap the deep sea water. Okay. In Sarawak also there are some potential. We yet to go and really check out. So this is on that desktop is about 55 kilometers. Which is, let's say we have some corals here, then we can be much more easier, and some on land OTEC. Okay, I'm coming to the end. This is to prove that 1 megawatt OTEC, 1.3 megawatt OTEC. We can get a net of 1.1 megawatt. Some details, you can check with me later, because I'm running out of time. Okay, the way forward, I think we saw this. If at all we can have on land or offshore floating OTEC, then we can, produce green hydrogen and green ammonia. Okay, this is another idea by Petronas. The supply chain is already there, but they put renewable energy. So we are proposing, why not include what you call OTEC in the renewable energy? Why? Because we have the potential. Oops, it's not coming. Okay, we have the enactment which was highlighted earlier. Sabah recognizes. So this is quite important. Sabah, the state recognizes. Malaysia as a whole recognizes solar, but good that Sabah has recognized OTEC as a renewable energy. So that will even help us to really move the project forward. So if at all for Brazil, oh God, it's not working. Okay, so this is a blue economy. Of course, for Malaysia, we have put that. As I said earlier, I would like to repeat. We can't copy and paste from elsewhere. You need to localize, so you need to do more engagement and really, see what is the priority that you need to align well. Okay, this is how the stages or the phase. I think somebody asked also, what's the next phase? Okay, we are actually coming from academia, so everyone, we've got our forte or our job to do. So as academia, we want to do research, talent development, and so on. Business, we leave it to the business people. Okay, thank you. That's all.
Thank you, Dr. Satyam. Unfortunately, no time for questions, so we're going to move right on. The next presentation is from Mitsui OSK Lines. They've asked me to present on their behalf, so I will take over. We're gonna having technical difficulties again, so we're gonna skip my presentation and go to the next one, which is from NIOT, and then we'll try and recover that on the way back. So the next presentation will be from V. Samson Pakajias Raphael. He's a scientist at the National Institute of Ocean Technology, India, and he'll be presenting his video, which is Design and Development Status of Open Cycle OTEC Plant at Kavati Island.
Good morning. I am Samson from National Institute of Ocean Technology, India. My title of presentation is Design and Development Status of Open Cycle OTEC Plant at Kavati Island. So, in NIOT has developed a technology called low temperature thermal desalination. In this process, we use the available temperature gradient between two bodies or two flows to develop, to produce fresh water. Since India is in tropical region, we have a warm seawater available at 28 degree temperature, around 28 degree. Whereas if we go 350 meter deep, we can get around 12 degree temperature, cold, deep sea cold water. Using this temperature gradient, 16 degree, we can generate fresh water. The another one scenario is all coastal power plants discharging huge amount of warm seawater, which is available at 9 to 10 degree above ambient. Since this process, LTD has a less maintenance issue and it is very easy to operate, NIOT put a lot of plants in this process. So the principle of operation of this process is flash evaporation. In this process, the warm seawater is exposed to the sudden pressure drop below is saturation pressure. So the available sensible heat is converted into latent heat of vaporization. A portion of the warm seawater is converted into vapor. The remaining water loses its sensible heat, and this goes as a brine. So this process is very fast. It is called flash evaporation. In this process, we need 3 pumps. One pump is for supplying warm seawater to the flash chamber. Another pump for supplying deep sea cold water to the tube side of the condenser. And we need a freshwater pump to draw the potable water against vacuum. So, and for maintaining the entire process, we need a vacuum system. In this process, we supply the warm seawater into the flash chamber. Since we are maintaining the pressure vacuum below its saturation pressure of the feed warm seawater, a portion of the vapor is converted into vapor. Portion of the warm seawater is converted into vapor. That vapor goes to the cell and tube. So in the tube side, the deep sea cold water is flowing. So the vapor converted into distillate, and it is potable. So because it is salts free, it is potable. So this, using this principle, we put our first plant in the year 2005 at Kavaratti. This is the view of the plant. Here, this is the bathymetry. You can see around 12-degree water is available at 350 meter. Here we used the rectangular type flat chamber, and we use the 2-pass cell and tube condenser. So the challenges in this plant is, here we have to around 650 meter long HDP pipeline in the shore and towing to the pipeline to the deep sea and deploy the pipe. And also we constructed a sump caisson and we towed the sump to the respective place, and we constructed trestle in the offshore for transferring this deep sea cold water from the sump to the plant building. NIOT successfully completed this task. So now using this principle, principle and using the experience what we gained in the Kavaratti plant, we put 7 more plants in the Lakshadweep group of island. The problem with this plant is we are powering these plants using the local grids that is operated by the diesel gensets. But now NIOT is focusing powering these plants using open cycle OTEC principle. In this principle, instead of 12-degree deep sea water, we are drawing 8-degree deep sea water from deeper depths, and the extra temperature gradient available that we are utilized for the turbine expansion. So the whatever vapor produced in the flash chamber drives the turbine and generate power. After turbine expansion, the vapor goes to the cell and tube condenser. So in this open cycle OTEC plant, the critical task is site selection, because we need a deep sea cold water at around 8 degrees C. So NIOT conducted extensive temperature measurements in and around Kavaratti Island, and the picture shows that the temperature is available at a depth of 1,000 meters. The 8-degree temperature is available. The another one major task in this site selection is the bathymetry of the island, because this bathymetry decides the cold water temperature, cold water pipeline length. You can see the bathymetry of the Kavaratti. Around 3.8 kilometer long HDP pipe is required. And also we conducted temperature dilution contour using Karmic software. And we observed that the deep sea cold water dilution takes place at around 64 meters from the discharge point. So we carefully selected the plant site, which is 330 meters away from the existing LTT plant. So the another critical task is temperature distribution, because the plant performance depends upon the temperature distribution of the components. That means the sharing of temperature gradient available between the warm seawater and deep sea surface seawater. Here we shared 8.6 degree for turbine, that is 44% of the total temperature gradient. And we share 3.2 degree for flash chamber and 3.7 degree for condenser. And the remaining goes for the terminal temperature approach and losses. So using this temperature temperature difference, we using basic heat and mass transfer calculation, we calculated the warm water requirement, cold water requirement, and the turbine work. Here the warm water is around 240 kg per second is required for 100 meter cube per day capacity plant, and cold water requirement is around 210 kg per second. And this plant turbine produce around 67 kilowatt, and the parasitic power required for this plant is around 63 kilowatt. This is the status of the project. Here we already fabricated the flash chamber, and the flash chamber fabrication is all over. And condenser fabrication is in progress, and the turbine components manufacturing is under progress. And also we sized the vacuum system and pumps, and the procurement of pumps and the vacuum systems are under progress. So the challenges and in this project is we have to design the pipe configuration, towing and deployment methodology, then designing the large low pressure turbine because here the volumetric flow rate of the turbine is very high. So NIOT successfully designed the turbine, and we selected the high efficiency pumps, seawater pumps, and also the vacuum system. And also you can see the picture, the temperature gradient available for between 20 meter and 1000 meter is around 22 degrees available in the Indian coastline as well as in the islands, Indian coastline of the islands. The major islands in India is Lakshadweep and also the Andaman Nicobar Islands. In this islands, the tourism plays the vital role. So here we need a heavy demand for fresh water. So this is so in all the islands, the potential for putting this type of plants is available. And also for mainland application, the closed cycle OTEC is the viable option. And also by making the spin-offs like the deep sea cold water still its leaves at 12 degree water, so that water we can use for air conditioning in resorts. And also the deep sea cold water is rich in nutrients that we can use in marine aquaculture. Using these spin-offs, we can make the OTEC plant future viable. Thank you. Any questions, please?
Thank you for the presentation. It was interesting to hear about India's recent updates. So we're going to switch back to the MOL's presentation, and hopefully that will go forward. Okay, so I'm going to present on behalf of Mitsui O.S.K. Lines. They're one of the world's largest shipping companies. We're one of their technology partners working on OTEC in Japan and abroad. So this presentation will cover a few basics about MOL, their involvement in OTEC, the current projects, and roadmap for going forward. They have a video. Unfortunately, we had a little bit of a technical issue with that as well, so you can feel free to visit their website or their YouTube pages that have some graphics on OTEC as well, but we'll skip that for now. So one of MOL's recent missions is working from the blue oceans. And they want to sustain livelihoods and ensure a prosperous future from the ocean resource. Okay, so their efforts are to develop a variety of social infrastructure businesses in addition to traditional shipping. Meet evolving social needs, including environmental conservation, with innovative technology and services. MOL Group aims to be a strong, resilient corporate group that provides value to all shareholders and grows globally. So it was established in 1884. It's 139 years old. I wish I was 139 years old. That's impressive. There's more than 8,000 company employees, 44 group bases, almost 800 vessels in their fleet, 509 group companies, and they are aiming for net zero in 2050. So that's a lot of parts to get to this goal. So it's a big company, 500 companies, but in kind of a small scale containerization. They have container ships, cruise ships, ferry and coastal, tugboats, terminals, logistics, and real estate. So why OTEC for MOL? So within MOL, we have a headquarters group called Wellbeing and Lifestyle Business. And it was established as a new sales group to carry out business related to well-being and lifestyle of all stakeholders. So through the various initiatives that we just mentioned, ferry, tugboats, cruises, delivery services, foreign workers, travel, the overall group vision is looking at that resource of human resources and how to then bring that towards the goals in the future. So one of those activities is utilizing deep sea water and ocean thermal energy conversion as a way of working towards the renewable energy goals and decarbonization goals for the company. So the social infrastructure business based on deep ocean water aims to promote industrial development, create employment, and achieve low carbon and decarbonization, and ultimately contribute to urban development through further utilization of deep ocean water. It will support sustainable development of regions and foundation of a circular economy starting with deep ocean water. So the company aims to expand into this new business area, such as agriculture, tourism, and business to consumer, utilizing deep ocean water in collaboration with group companies, thereby expanding non-shipping business fields and realizing well-being societies. They're supporting activities in Palau, Mauritius, and in Japan itself. So a few kind of project overviews. We are mainly working to realize 1 megawatt OTEC. Demonstration tests of larger heat exchangers for 1 megawatt OTEC are underway from fiscal year 2022 to 2024 with support of the Ministry of Environment of Japan. 1 megawatt OTEC's technical issues regarding power generation will be resolved, and plan to develop and research how to intake large amounts of seawater reasonably with Xenesis. So in order to establish the Kamijima model, which we introduced and heard about from several different presentations, we're also looking at future activities, such as in studying the intake and piping for Mauritius in fiscal year 2024. And we are continuing a pre-feasibility program by utilizing METI program. In Palau, JICA has started research on the Kamijima model deployment, and in Malaysia, considering of a pre-feasibility study with the government of Sarawak and Sabah. So the main partners that Mitsui OSK is working with is Saga University in Japan and Xenesis, and the project in Kamijima is under the collaboration of the Ministry of Environment. And that's taking place on Kamijima itself. In Mauritius, OTEC site selection has already been done, and so under a NATO-funded pre-feasibility study, and we're now looking at more detailed design and development of that project. For Palau, it's a direct government JICA project that Xenesis is working on, and Mitsui OSK Lines is looking at maybe future support in terms of expanded applications. One major task, and we heard about yesterday, one of the questions was the environmental impact. So, of course, we have a general consensus that OTEC can be a benign implementation, but because it's a newer application, we have to provide that data. So one of the things we do, and one thing we're looking on Kamijima, is as we look towards expanding intake 10 times the current implementation level, ensuring that there will be no negative implementation, we can grab their baseline data. What does the situation look right now? So that as we move forward, we can do simulations and understand the potential impact and mitigate any potential impact as we implement, and then show that any results based on the original data, we can show that there was no negative impact. So they established a study committee, including experts, and study meetings have been held about 3 times in this year. We are doing simulations on temperature and nutrient diffusion. We did a coral survey looking at the current situation. What does the corals look like now? And if what kind of impacts could there be or will there be? Compilation of domestic laws and regulations, because this is something that isn't necessary. There's no handbook for how to do OTEC in the world. And so it's something we maybe need to do in the future, but currently we have to deal with each individual laws. So we have a meeting of the review committee to get a wide range of opinions from both local and specialists as we approach this issue. So this is just some images from the coral surveys that we did, examples of areas where there was very dense corals. We would want to avoid that potentially, and areas where there's maybe just mostly sandy ground and some boulders. And so these help us identify, the paths for pipe routing and things like that we should, take into consideration when both the construction and long-term operation for discharge and these kind of nearshore activities. So going forward, you've seen this before as well. We're here at the demonstration page. We've completed 10 years of operation. In Japan, we're working at a small-scale onshore OTEC. We're working towards that. We now have a 200 kilowatt facility already established here on Kumijima. So that's already being expanded towards a 1 megawatt. We're taking steps through that way. But ideally then, in the future, this will bootstrap us off to large-scale floating OTEC, which can then support larger-scale implementation, but also create potential for target areas like Mauritius, Palau, and other tropical states and remote island regions. So very brief, okay, we're running short on time, so I'll end my presentation there, and we will move on to the next session. Thank you. Okay, so we will skip our next break and go right into our next panel. So just give us a few minutes to prepare for panel 3. This will be the technological advances on OTEC. So I'm going to ask Professor Joel to join us, Professor Ikigami, Roy Robinson, and please come up here and we'll make some space for you as panelists. Okay, so this is a panel on technology development for OTEC. Where are we at? Where are we going? What do we need to do for OTEC to happen? So I'll be your moderator, Benjamin Martin, working from the kind of technical side here. And so I'd like each panelist to introduce themselves and then provide just a short comment on where you think OTEC is right now. Are we ready or do we need more time? Start with Professor Ikigami.
Thank you. My name is Yasuki Ikigami, Institute of Ocean Energy, Saga University. So I think is mainly OTEC most important OTEC technology is 3 key technologies. One is a heat exchanger. Second is a platform. Third is intake tube. So first is a heat exchanger. So because very low temperature, small temperature difference, we need more huge heat exchanger area than fossil power plant per kilowatt hour, per kilowatt. So, so we can improve dramatically the heat exchanger because heat exchanger configuration and material, so they are possible to decrease the cost. And floating, so floating is a very costly, 20 or 30% of the total OTEC floating system. So, but I think, by the way, I think Brazil or another countries has a huge potential of the technology floating regarding the oil industries. So this platform technology is very important. I expected Brazil's technologies. And the third is IntecTube. IntecTube is mostly 30 or 40% is a total floating OTEC system. So now there are many challenges in the world now. So 2 or 3 technology I expected dramatically decrease the IntecTube cost or material on or mooring method. But it's now I cannot open some technology because 2 or 3 expected technology of the IntecTube. So, but now not open the technology. Thank you.
Good morning. I am Joel Salles, a professor at the Federal University of Rio de Janeiro, and also I'm the director of Laboratory of Waves and Currents from COP, our postgraduation and research institute at the university. I agree with Professor Ikegami. I can talk more about the floating part for a offshore OTEC to become a reality, as Benjamin has mentioned. I think that in terms of technology, it is already there. We have seen yesterday the presentation from Daniel from Petrobras. Petrobras is a symbol in Brazil about what the country can do, not only in terms of possibilities, but also in terms of being able to show what we already have done. So it's already a reality in terms of a lot of challenges. Since the first time I met Professor Ikegami, we talked about this beautiful synergy that can arose from our interactions between Japan and Brazil. Japan, with its 50 years experience on the generation of the energy using OTEC, and Brazil with our maybe also 50 years experience on exploring oil offshore. So if we can achieve a smart interaction, I think we can overcome the main problem nowadays that I believe that we have for the OTEC community, which is high uncertainties, because we don't know how much it will cost. So it's very difficult to, like you saw yesterday, the presentation from them. It's very difficult for us to ask for money since we don't know which amount of money we actually need. So I think that's the main challenge for floating OTEC. We have to reduce the uncertainties. And I believe that the way that we can do is to look at, as I said in the opening ceremony, if we look at the oil industry, the Brazilian oil industry, they are not the bad guys. People from the research, the renewable energy area need to understand that. The oil companies, they are not the bad guys. They are our, actually, they are our vector that will allow us to do the energy transition. And they have the resources and they have the know-how. Okay, so if we are able to understand that and talk to them and see what they need right now, so I think we can help. We have a lot of things, good things that come out of the OTEC technology. So I think that if we do that in a smart way, maybe not starting with the 150 megawatt, but maybe we can start even with the 30 kilowatts or 100 kilowatt. We know that there are some needs already in the oil industry for very low power applications. And if you do that, we have a lot of good outcomes from it, because we are going to show to the world that OTEC is a real technology, and we are also going to reduce the uncertainties, because if you have something already working on, we can reduce the engineering costs, because the industry, especially offshore industry, they are very, of course, they do a lot of innovative and disruptive things, but at the same time, they are very traditionalist and conservative, because they work with very dangerous assets in terms of lives and environment, and very expensive things as well. So if you do that, like I believe the Japanese show to the world, that is a nice way of doing things. If you do that with small steps, but very precise and very strong steps, I think we can achieve our 600 megawatt park, OTEC park, or maybe gigawatts. So I think that's it.
My name is Roy Robinson, for those of you who don't know me. My OTEC system is somewhat different than most of the ones that you're going to see out there. I'll get to that later in the day. But even then, and my background, just so you know, I'm a marine engineer. I have an MBA. I've spent 40 years working in offshore energy, mostly in oil and gas. 10 years ago, I switched over to renewable energies of all kinds. I'm a firm believer in integrating all of them together. One of the things I fight against is, honestly, isolated conferences like this, because Wave Energy has a conference, and Tidal has a conference, and OTEC. But you need to put them all together, including the wind. But where the technology development areas of OTEC are, and Dr. Akami said it correctly, heat exchangers would be top of the list, because even my system needs that. Large, low temperature, low pressure turbines that are organic cycle. The sizes that are available don't meet what we're going to be able to do very shortly. But that doesn't mean we cannot develop now. One thing I caution to the people that ask me about this, if you're going to build a floating system, an offshore floating system, if it's going to make money, if it's going to be profitable, it has to be of a large size. And by that I just mean in terms of its megawatts. It's a simple matter of how much money you can make versus how much it costs. And no matter how small you make it, a lot of those costs don't change. A little bit more on my background is I do a lot of cost estimation and valuations and asset valuations in oil and gas. So I can look at systems, I can look at processes and pretty much have an idea of how much they're going to cost. And then I can tell you how much revenue you're going to have to make. And you're not going to get there at 1 megawatt or 2 megawatts. It's going to have to be 20 or 50 or 60 or better, even 100. Even in places where there may not be the demand for it, like some of the SIDs, you can then create other demand if you have that spare power. And so my focus has always been on trying to make low-cost energy using any systems I can. We went into OTEC because I've been studying OTEC, quite honestly, since 1972. And when I started my company in 2016, I was surprised at how things had gotten better, but it hadn't really advanced. We were still trying to redesign the same system that they did in 1973. My partner and I started from scratch and redid all that, which we'll get into again, like I said, later. Because the two problems we saw with making it low cost was the big water pipe, the cold water pipe going down, and the low thermal efficiency that you can't get around, right, if you're going 25 to 4. There are ways around that. But regardless of that, the technology that needs to be developed is the heat exchangers, the turbines, and then anything else we can do to make the floating systems more efficient. And he mentioned moorings. There's some ways to do that with renewable energy that don't work in oil and gas. Things we don't need is platforms. We know how to build offshore platforms. They've survived hurricanes, they survived the North Sea, they can take ice, all kinds of things. You're not going to have a problem with a platform to hold up your OTEC. The only problem you're going to have is paying for it, because they're expensive.
Okay, so we're hearing heat exchangers. Well, we've been working on it in Japan. platforms may be covered, or Brazil has that experience. Pipes, maybe depending on how you're implementing your system, and turbines depending on how you're doing that. So then if the goal, I think we all understand the goal is big OTEC, economies of scale, that's the goal. How do we get there? Economically, technology, there's a lot of different aspects we have to work on. What's your perfect next project for OTEC? I'll start with Joel. What would you want to see? What's the next step that we can do tomorrow? Here's their pitch. What do you want to see OTEC to work on in terms of technology, or in terms of to make us move forward?
I think the main issue right now is with the cold water pipe. So we already actually have some initiatives. One of them is going to be presented on the next keynote speaker, Martin Brown. So we have this GIP where we go to the industry and ask their opinion about how can we get a very big and very long cold water pipe, because that, I think, is the main part of the cost for the floating OTEC. Of course, there are other options like a RISE proposal. Yeah, that changed a lot the pipe. But anyway, trying to answer your question, I think that tomorrow we should, at least myself, I'll go back to the problem with the connection of the cold water pipe with a floating system. Of course, if you can also try to work together with the thermodynamic team, every degrees Celsius that they can gain in terms of the delta T, it helps us a lot on the length of the cold water pipe. And also another thing that we should do, which Rise also has a very nice picture in these presentations, is that maybe we can think out of the OTEC box and think about how other energy sources could also help us in terms of the pump power, maybe even with the parts of the cycles, we can, like solar energy, try to see what can be done, and other sources like small wind turbines and so on. But every small kilowatt that we can gain in the OTEC cycle may signify less cost. So I think those two things, the pipe with the connection, and what can we do to help on the Rankine cycle in terms of external sources.
Professor, 次のどういう授業をしたいOTECを進めるために。
So I think there are no technology issue for the online type OTEC. So now we need the floating OTEC demonstration. So using a big size intake tube. So this is now challenging for long time operation. So 1 week, 2 weeks is okay, but long time operation for the hurricane, for the typhoon. So now in Japan is already success is a Takumi project. Is 5 years of continuous operation. So using 1 meter diameter of the material of the steel, so 10,000 ton per day deep sea water project. So this floating system is very unique for the specialized OTEC. So, but unfortunately, the not operations are OTEC, only deep sea OLA system. So I want to challenging the long time operations OTEC as a floating type using advanced floating technology. So intake tube and mooring system and platform, new platform. Yeah, thank you.
Well, ideally, my next project would be to get funded and go out and actually build one of mine. All of the technologies that are in my different way of doing OTEC exist. There's no science project in it. The turbines exist, the piping. I don't use a big cold water pipe. I have a heat transfer pump, a big heat transfer pump, and I'm using two smaller pipes to take the heat from the surface to the seabed. So that gets rid of his cost problem. The next thing that happens is that also takes the heat that was 23 degrees and turns it into anywhere from 50 to 70 degrees. So that gives you more driving potential. Yes, putting things on the seabed is expensive and complicated, but that's what oil and gas have been doing for 40 years, and the subsea factory concepts are well established. They don't have turbines down there, but they have compressors, which is basically the same technology. So the modification of a turbine to be put on the seabed is not a problem. Has a side benefit of that ammonia is totally safe when it's down there, if you want to use ammonia for your organ fluid. Even that, and even with my OTEC, which I really see as a radical change and a way to go forward, if I was given a blank check, if Elon Musk came to me tomorrow and said, hey, we want you to go build one, it wouldn't just be OTEC, right? Because the cost of a floating system doesn't change by what you put on it much, right? If I add 1 cubic meter of space, I can carry a ton extra of anything. And to add a cubic meter of space into a hull of any kind of vessel only takes a little bit of plate steel. It's almost free. So you think of what can I do if I have OTEC, if I have this wonderful OTEC system, it's going to be there, it's going to be floating. Why wouldn't I put a turbine on it? Why wouldn't I have wave energy on it? Why wouldn't I host aquaculture? Why wouldn't I do mineral recovery? All these things, because that's how you end up making it be profitable. At the end of the day, any of these renewable energy systems, if they need to be subsidized to go in, or if they need to charge people 25 cents or 35 cents a kilowatt hour wholesale, they're not going to get us where we want to be. Our goal, and we think we pretty much have gotten there if we could get the funding to build it, is to produce continuous renewable energy power at the cost that you would get today from hydropower or from gas plants. I mean, that's what we're shooting for. So if I was fully funded, I could go build one of mine. I think there's some more engineering work I should do to make it better. I'm sure I can make it better. And it'll always be getting better. But the technology focuses that we talked about, there's going to be lots of improvements in the turbines once we start to build these. There's going to be lots of improvements in the heat exchangers once we start to build these. But until we do that, and until we show that there's a profit and a market, the research in there is going to be slow.
So then how do we start building it, right? So what can we do to start building? I think in Japan, we've built 200 kilowatt OTEC facilities. So we got funding, we've done the full-scale heat exchanger. But it doesn't have a turbine, it's not full OTEC. So that's, I think, one of the problems we've had with OTEC is we keep doing parts of it. How do we bring it all together? And so I think, this is an opportunity with bringing this international group together is to discuss that. How do we bring these parts that we've all worked together to build into a single system?
I will say that the place that I think has the most potential to do that, and don't get me wrong on this, the right set of skills are here in Brazil. All of the skills they need are here in Brazil. The only thing they don't have in country as much as they have in some others are those OTEC research centers. But in terms of a willingness to do things a little bit differently, and in terms of a willingness to spend some money to create systems that are unique and new, Brazil is one of those countries that I've seen do that. The States is not quite as friendly to that unless you can show them a clear path to profit. So once somebody cuts that path, then the U.S. will jump in. But Brazil is uniquely placed in that they have all of the offshore oil and gas experience, which is why I came into the renewables, because I wanted to bring that experience in. And they have the funding and the technical, the shipyards and the things that they would need. Japan can do it as well. But Japan they don't have the experience in building large offshore structures that they have here in Brazil, right? They're very good engineers at building ships and all that, but when it comes to developing offshore oil and gas and energy and the moorings and all that, oil and gas has got that solved, right? I mean, it's not a question. There's ways to make it less expensive if you're doing renewable energy versus oil and gas, but that's not going to be the problem. That's not what's going to hold it back.
Just to add some thoughts. If we look at the wind turbines right now, they are also very, very high cost assets. But as the society understands that it's something that is worth putting some money on, the wind energy nowadays, they have a lot of subsidies. So when we compare the costs nowadays, it's kind of unfair comparison because they already have a lot of money from the taxpayers that do not appear clearly on the LCOE and so on. So if you come back to Brazil and if you see again the oil companies, they are all talking about their all carbon credits like strategies. So I think it's a big opportunity because even if we have a very expensive, non-profitable structure, if the companies understand that this is a necessary step to their decarbonization targets, even if it is a higher cost, non-commercial, I think they still understand that at the end of the day, it is worth investing on it. So, and as I said, after we start doing, the price may go down, as we have seen with solar panels, for instance, like 20, 15 years ago, which was very expensive. Nowadays, it's like you can put on a house without any asking for any bank debt and so on. So I think that's one good opportunity, because it's not only about electricity. We have seen that very nice video from the Kumejima model. So we're talking about a whole environment around it, and something that it's very difficult to put a price on for oil companies is the price of their image. So sometimes if you just do something that the society doesn't like very much, nowadays with internet, all the news goes worldwide in seconds. Maybe your share price can go down a few percentage points, and then you lose like, I don't know, billions of dollars. So it's very difficult to put a price on it. So I think our objective as a OTEC group is to try to bring to them and to society that it's not only at the end of the day just a matter of see if we are green or red, but what we have around it in terms of a meaning. So I believe that one of the things and as I said, the wind energy, people are already doing that, and the solar energy also, we can see a very nice curve of costs going down with the experience and so on. So,
okay, I'll open it up to the audience if anyone would like to ask an additional question. Yes, please.
Hi guys, thank you very much. I'm Daniel from Petrobras Research Center. Yeah, you know me from yesterday. I was just wondering, it can sound like a silly question, but I would like to hear your opinion. Like, yeah, we are already there in terms of technology. That's what I got from you. So, I mean, remote islands are clearly a very, reasonable scenario for application of OTEC. And why don't we see like multiple megawatt scale OTEC planned or installed in such places, since it's already available right now?
It's true. Yeah, so using this technology, so we can realize and contribute it for the small island. But actual purpose of the OTEC is floating, 100 megawatt OTEC is we have to realize as soon as possible. But I think is many investors, many governor doubt still the OTEC technology because it's not yet commercialized. So if we commercialize 1 megawatt scale, so I think it dramatically is changing the situation. This OTEC commercialize. One case, 10 years ago, so not operating the OTEC in the world, but 10 years ago, from the 2013, Kumejima OTEC plant is started. Everybody can feel the realized OTEC technology. So investor or the governor, in Japanese investor governors are accelerating the invest. So now we are challenging the 1 megawatt scale. So if we commercialize now Kumejima or Palau or other countries, so we can show the OTEC technology. So we can get easy to the funding because existing technology we can apply, but OTEC initial OTEC cost is very high than another energy. But long operation OTEC energy is very cheap, very cheap. But only initial cost, but totally energy cost is very cheaper than another renewable energy, I think so. But I think my image, OTEC technology now is a space technology. So first, one country reached to the moon, so everybody challenged to the moon. So first, as soon as possible, I think realize OTEC commercialize 1 megawatt. So everybody challenging the floating OTEC, I think so. But this is goal is of 100 megawatt to get cheapest energy using renewable energy, I think so. So if you are Petrobras challenging the 10 megawatt OTEC, so very accelerated. Yeah, fast who shows possibilities. Yeah. Now, I don't worry. Kumejima or Palau, 2 or 3 years, I will commercialize. I expect it.
What scale are you willing to invest in? 100 megawatts is a huge project and a big cost where no one has invested yet. But if we are at 1 megawatt now and it's expensive, then it's a smaller capital cost, but even that doesn't make the business sense that would drive a private company investment generally. And that's the big hurdle. How do you overcome the valley of death of any technology deployment from initial research to operation?
There's a fundamental problem. You asked why they don't have them deployed everywhere. And I'll use it this way. Conventional OTEC, the fundamental things that make it expensive that Joel was talking about, the low temperature difference in the large diameter cold water pipe that needs to be 1,000 meters deep, you can't get around that. And that means your power is going to be expensive. Even by the measure of the island states, the power is going to be expensive. That's why they haven't done it. I mean, Lockheed spent $200 million doing a really detailed design, almost sold it to the Chinese, and as soon as the Chinese got into the books and figured out how much it was going to cost, they said, no, this isn't going to happen. That's why we didn't go that route. We went to a different route, and our cost will be about half. And if you integrate the platform, as I mentioned, then it goes down even more. It'll cut another 50% off of that. That's the reason why you don't see it deployed in all these islands. But being totally honest, if I was funded, I could replace the stuff on the Rona. I could give you 10 megawatts within 5 years at cheaper than what they're spending now. Once you've done that, every island state in the world will be knocking at your door.
One more question, or
my question is, now Professor Ikegami talked about 3 challenges for present status of OTEC. My question is, in near future, is possible to become cheaper technology or not?
Yeah, I think it's true. I expected as soon as possible the decrease the cost, especially the intake tube or flat platform is now is the most expected decrease the cost, because some company or some universities are now challenging to realize decrease the cost. I think so.
So I'm Satya here. Yeah, I think time is also there, not limited. We are limited. So the way forward, and like Roy and also Joel, of course we are in Brazil, so OTEC in Brazil. Of course Ikegami Sensei, your collaboration here. So way forward, OTEC in Brazil. How do you visualize, or what's your idea like? Joel?
I think my answer has 2 parts, and more or less reflects the organization of the symposium. So we have Professor Shinohara here. One of it is that we have our Kumejima Island, or Kume Island, which is Fernando de Noronha. I think that's a very nice model, because it's a piece of a paradise, and right now they are burning diesel in there. So, yeah, and they are thinking about other solutions, but all of them, you have seen yesterday a picture of a part of the island. It's not a big island, so a part of it was already had the trees cut down to put solar panels. And so they also have floating solar panels, but it's on a very nice small lake that they have in there. So you have a lot of interaction between the panel and the life. Yes. They used to have a wind turbine in there, but I talked we went there on that committee, okay, this year, and we talked to the local people. They just hated the wind turbine, because there are a lot of other things that we don't think on the beginning of the project. For instance, the noise is terrible, and they don't like also the view with that big turbine on it, and so on. But at one day, there was a storm, and then it came a lightning and destroyed the turbine. And people were commemorating, celebrating, think that God did that too. So it's a case. Yeah. So why not? Okay, it's very expensive and so on. But again, if we think on a more higher level overview, for instance, we could have our Kumejima model on Fernando de Noronha Island, they produce no food in there, only very small things, and they have good soil. But the local population, they prefer to work on the hotels and so on, driving that small cars for the tourists and so on. So if we can change the culture of the place, they can produce a lot of high prices products in there. It's a very famous island worldwide. So it could be a model, a very nice model. So I believe that one of my almost dream, but a very, very feasible dream. And the other part is, as I said, I think we have to take the opportunity of the offshore industry in Brazil. If you look at our history, when we first found oil in Brazil, onshore, a lot of people didn't believe that we would be able to pick up the oil onshore. And when we found out offshore, the price was even worse than OTEC, I think, because how much it will cost. And nowadays we can do very nice with a very low price for each barrel at places, world record places like 3,000 meters water depth. If we thought about it maybe 60 years ago, that would be a dream, not for 100 years in the future. So I think, as I said yesterday, I say all the time, in Brazil we have a lot of good opportunities. Not always we are able to take them, because we have other problems as well as a country, as people. But when we decide to do it, we do it very well. So I believe that those two strings are pretty possible to do it.
And on that note, the other thing they have is by having all those offshore developments and platforms, a lot of those, if they develop an OTEC system, can actually be converted into green energy systems, repurposing those platforms for those purposes. If nothing else, they can cut down their power by putting OTEC systems around or on them. Again, one of the advantages of my system versus some is that it's topside requirement. The part that's on the surface is very, very small. Most of it's on the seabed. So they can put this on their FPSOs. They can put this on existing platforms, or better yet, if they're doing a new development, if you plan a new development to turn into a renewable energy system, and I've already consulted the oil and gas companies about this, if you start from the beginning with that in mind, you design your pipes so that they can carry hydrogen, you can design your system so that they can put power in as well as out. All of these things can be done for a very small cost on the scale of things. One of the problems with trying to make conventional OTEC less expensive is, as he mentioned, is that the technologies are already there and they already are mature. So it's not like solar panels. All right, the cost of a mooring is not going to go down by a factor of 100 in 10 years. Cost of a mooring is what the cost of a mooring is, right? The cost of steel, yeah, it goes up and down, but it's not going to change that much. The cost of the big pipe, somebody might come up with a better way to do it, but for now, it's pretty much a mature technology and it's really expensive. And that was my area in oil and gas, was designing pipes. So can I design you a 14-meter diameter pipe going down 1,000 meters to bring cold water up for 100 megawatts? Yes. Can I do it at a cost that 100 megawatts would pay for? No. But in Brazil, they have the unique opportunity of both the largest area of OTEC potential in the world, easy access to deep water, needs like Noronha, but then also these massive offshore oil and gas fields that can make use of it as well. And even if they have hurricanes, you'll see on my slides, I actually use the Gulf of Mexico as an example. The Gulf of Mexico is another place where they could be using these. And hurricanes are not a problem. Okay, our systems are not going to go with a hurricane. In 40 years in the Gulf of Mexico, they've lost one floating platform to a Cat 5 hurricane that passed over, and it was a design flaw. It wasn't really the hurricane. The guys, when they built it, decided to save some money.
Okay, so we are out of time. So round of applause to our panelists and to the audience for your questions. So just to cap, the technology is there. There's new technology coming on board. There are challenges ahead, and so finding ways of collaborating may be the one way to move forward. So we look forward to continued discussions in the afternoon. It's time for lunch, so please be back at 1:20. 1:20, and we'll start our next session soon after.
She called me her buzzer. Everything on my last she pushed and she moved me. Don't feel like the old me. For minutes, days of baby. I was there, I never really love me or like me. For minutes, days of buzzing. So if you're really feeling something about ocean, it's not me. She called me her buzzer. Everything on my last she pushed and she moved me. Don't feel like the old me. For minutes, days of baby. I was there, I never really love me or like me. For minutes, days of buzzing. So if you're really feeling something about ocean, it's not me.
The kisses of the sun were sweet, I didn't blink, I let it in my eyes. Like an exotic dream, the radio playing songs that I have never heard, I don't know what to say. Oh, not another word, just la 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 la. It goes around the world, just la 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 la. It's all around the world, just la 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 la. It goes around the world, just la 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 la. It's all around the world, just la 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 la. La 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 la. La 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 la. La 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 la. It's all around the world, just la 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 la. It's all around the world, just la 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 la. It goes around the world, just la 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 la. It's all around the world, just la 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 la. It goes around the world, just la 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 la. It's all around the world, just la 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 la. La 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 la. La 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 la. La 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 la. It's all around the world.
I'm hearing voices in my head, there's no way to escape. Da 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 da, they got me. Anytime, anywhere, my mind in the air. Da 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 da, surround me. They surround me. Surround me. Anytime, anywhere, my mind in the air. They're waiting for me. They're calling on me.
Lay low, hit the sun, everybody have a real good time. Real good time.
Surround me.
Yeah, we cool, yeah, we drunk, lost my mind, and baby, I feel high. I feel high.
They're calling on me.
Lay low, hit the sun, everybody have a real good time. Real good time.
Surround me.
Yeah, we cool, yeah, we drunk, lost my mind, and baby, I feel high. I feel high.
They're calling on me. I'm hearing voices in my head, there's no way to escape. Da 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 da, they got me. Anytime, anywhere, my mind in the air. Da 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 da, surround me.
Lay low, hit the sun, everybody have a real good time. Real good time. Yeah, we cool, yeah, we drunk, lost my mind, and baby, I feel high. I feel high.
They surround me. Surround me. Anytime, anywhere, my mind in the air. They're waiting for me. They're calling on me.
Lay low, hit the sun, everybody have a real good time. Real good time.
Surround me.
Yeah, we cool, yeah, we drunk, lost my mind, and baby, I feel high. I feel high.
They're calling on me.
Lay low, hit the sun, everybody have a real good time. Real good time.
Surround me.
Yeah, we cool, yeah, we drunk, lost my mind, and baby, I feel high. I feel high.
They're calling on me.
All I want is to dance with you now, is to dance with you once again. Da 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 da. All I want is to feel you so close, is to be with you till the end. Da 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 da. We might be oceans apart, but maybe you can hear it's the sound of my heart. Da 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 da. All I want is to dance with you now, to the beat of your love again. It feels like dum 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 da 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 da. Da 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 dum 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 da 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 da. Da 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 dum 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 da 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 da. Da 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 dum 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 da 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 da. It feels like dum 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 da 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 da. Da 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 dum 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 da 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 da. Da 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 dum 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 da 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 da. Da 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 dum 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 da 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 da. All I want is to dance with you now, is to dance with you once again. Da 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 da. All I want is to feel you so close, is to be with you till the end. city lights are calling at night, and you lay in bed rethinking your life. Will it ever stop the worry in my mind? You will find if we're running away from the problems we see, keep giving up on our hopes and our dreams. We got the power to be who we wanna be. You see, we go all or nothing, all or nothing. Why not make it count for something? All or nothing, all or nothing. Fight for something we believe in. If we never stop moving, we'll never be broken. Even if our heartaches, we go all or nothing, all or nothing. Why not make it count for something? Passing every red light, I know I'm in over my head. A rebel and I don't hide. Remember all the words that you said. Even if the love was hurting, I'll be yours, I'll be yours again. I can feel that fire's burning, give me more. So tell me, would you feel my love? 'Cause I can't ever get enough. So tell me, would you feel my love? Yeah, I can never leave 'cause I need it, that feeling. Let me feel your love. You can make me let go. Forget about the world for a while. You had me at hello. I'm drowning in the blue of your eyes. Even if the love was hurting, I'll be yours, I'll be yours again. I can feel that fire's burning, give me more. So tell me, would you feel my love? 'Cause I can't ever get enough. So tell me, would you feel my love? Yeah, I can never leave 'cause I need it, that feeling. Let me feel your love. Let me feel your love. So tell me, would you feel my love? 'Cause I can't ever get enough. So tell me, would you feel my love? Yeah, I can never leave 'cause I need it, that feeling. Let me feel your love.
I want you for the dirty and clean. When you're waking in your dreams, make me bite my tongue and make me scream. See, I got everything that you need. Ain't nobody gonna do it like me. We are burning at a high degree. And you make me feel like it burns and it hurts. Baby, this part of the rush. This is us. What is love? Baby, don't hurt me. Don't hurt me no more. What is love? Baby, don't hurt me. Don't hurt me body, he giving me kisses. I'm wet when I'm wet, I'm popping like Adderall. Baby, dive in my beach and go swimming. Let's go deep, cause you know there's no limits. Nothing stronger than you when I'm sipping. I'm still gonna finish, I'm drunk, I ain't had enough. One day you hit and you close, telling me lies and it's killing me slowly. Yeah, yeah. What is love? Baby, don't hurt me. Don't hurt me no more. What is love? Baby, don't hurt me. Don't hurt me no more. What is love? What is love? What is love? Baby, don't hurt me. Don't hurt me no more. What is love? Baby, don't hurt me. Don't hurt me no more. What is love? I feel it in my blood. I feel it in my veins. Now I cannot get you off my brain. Without you, there's no point to live on. I feel it in my head. I feel it in my heart. I never wanted us to drift apart. Without you, there's no point to live on. I feel you in my I feel it in my blood, I feel it in my veins, and now I cannot get you off my brain. Without you, there's no point to live on. I feel it in my head, I feel it in my heart. I never wanted us to drift apart. Without you, there's no point to live on. I feel you in my I feel you in my yeah, pull up in the rinse in my brand new whip and go. With a full eclipse and the moon lit like whoa. Everything blurred, mixing all that smoke with the gray goose. Fanny baguette on the bar top, both my hands on you. Take a picture of my figure. Catch a glimmer. Allow me to remind you, baby, I'm the keys to your car, babe. If you lose me, then baby, good luck. I'm the king to your checkmate. Still yours, though, baby, you've won. I'm the bubbles in your champagne. Grip me tight like you're holding your cup. you're coming. Whoa, know that you need me. I'm good, yeah, I'm feeling alright. Baby, I'ma have the best fucking night of my life. And wherever it takes me, I'm down for the ride. Baby, don't you know I'm good, yeah, I'm feeling alright. 'Cause I'm good, yeah, I'm feeling alright. Baby, I'ma have the best fucking night of my life. And wherever it takes me, I'm down for the ride. Baby, don't you know I'm good, yeah, I'm feeling alright. Don't you know I'm good, yeah, I'm feeling alright. You know I'm down for whatever tonight. I don't need the final things in life. No matter where I go, it's a good time, yeah. And I don't need to sit in VIP. Middle of the floor, that's where I'll be. Don't got a lot, but that's enough for me, yeah. 'Cause I'm good, yeah, I'm feeling alright. Baby, I'ma have the best fucking night of my life. And wherever it takes me, I'm down for the ride. Baby, don't you know I'm good, yeah, I'm feeling alright. Don't you know I'm good, yeah, I'm feeling alright. So I just let it go, let it go. Oh na 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 na, no, I don't care no more, care no more. Oh na 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 na, so come on, let me know, let me know. Put your hands up, na na na, no baby, nothing's gonna stop us tonight. 'Cause I'm good, yeah, I'm feeling alright. Baby, I'ma have the best fucking night of my life. And wherever it takes me, I'm down for the ride. Baby, don't you know I'm good, yeah, I'm feeling alright.
And I'm looking around, round, I'm in a ghost town. Feeling so alone, lone, where did you go now? I'm falling deep down, down, trying to hold on. I'm feeling so alone, lone, where did you go? And I'm looking around, round, I'm in a ghost town. Feeling so alone, lone, where did you go now? I'm falling deep down, down, trying to hold on. I'm feeling so alone, lone, where did you go? I'm feeling alone, feeling alone. I'm feeling alone. I'm feeling so alone, lone, where did you go?
And I'm looking around, round, I'm in the ghost town. I'm feeling so alone, lone, where did you go now? I'm falling deep down, down, trying to hold on. I'm feeling so alone, lone, where did you go? And I'm looking around, round, I'm in the ghost town. I'm feeling so alone, lone, where did you go now? I'm falling deep down, down, trying to hold on. I'm feeling so alone, lone, where did you go? I'm feeling alone, feeling alone. I'm feeling alone, feeling so alone, lone, where did you go?
never sound. I'm feeling so alone, alone. Where did you go now?
I'm falling deep down, down, trying to hold on. I'm feeling so alone, alone. Where did you go?
Let's start at the beginning about you and I. A story of two lovers that'll make you cry. You had me a hello and then you said bye-bye. Oh, oh. Your love is my love, but my love is breaking. Your touch is my touch, but my hands are shaking. I can't get high without you, I can't get high. My secret's coming out, now you're my shadow. I never knew you were a drug, now I'm OD. And now you got me coming back so easily. I love you, I hate you. You're my shadow, The kisses of the sun were sweet, I didn't think I let it in my eyes. Like an exotic dream, the radio playing songs that I have never heard. I don't know what to say. Oh, not another word, just la 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 la. It goes around the world, just la 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 la. It's all around the world, just la 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 la. It goes around the world, just la 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 la. It's all around the world, just la 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 la. La 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 la. La 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 la. La 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 la. It's all around the world, just la 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 la. It's all around the world, just la 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 la. It goes around the world, just la 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 la. It's all around the world, just la 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 la. It goes around the world, just la 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 la. It's all around the world, just la 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 la. La 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 la. La 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 la. La 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 la. It's all around the world, just la 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 la.
Lay low, hit the sun, everybody have a real good time, real good time.
I'm hearing voices in my head, there's no way to escape. Da 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 da, they got me. Anytime, anywhere, my mind in the air. Da 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 da, surround me. They surround me. Surround me. Anytime, anywhere, my mind in the air. They're waiting for me. They're calling on me.
Lay low, hit the sun, everybody have a real good time, real good time.
Surround me.
Yeah, we cool, yeah, we drunk, lost my mind, and baby, I feel high, I feel high.
They're calling on me.
Lay low, hit the sun, everybody have a real good time, real good time.
Surround me.
Yeah, we cool, yeah, we drunk, lost my mind, and baby, I feel high, I feel high.
They're calling on me. I'm hearing voices in my head, there's no way to escape. Da 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 da, they got me. Anytime, anywhere, my mind in the air. Da 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 da, surround me.
Lay low, hit the sun, everybody have a real good time, real good time. Yeah, we cool, yeah, we drunk, lost my mind, and baby, I feel high, I feel high.
They surround me. Surround me. Anytime, anywhere, my mind in the air. They're waiting for me. They're calling on me.
Lay low, hit the sun, everybody have a real good time, real good time.
Surround me.
Yeah, we cool, yeah, we drunk, lost my mind, and baby, I feel high, I feel high.
They're calling on me.
Lay low, hit the sun, everybody have a real good time, real good time.
Surround me.
Yeah, we cool, yeah, we drunk, lost my mind, and baby, I feel high, I feel high.
They're calling on me.
All I want is to dance with you now, is to dance with you once again. Da 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 da. All I want is to dance with you once again. All I want is to feel you so close, just to be with you till the end. We might be oceans apart, but maybe you can hear it's the sound of my heart. All I want is to dance with you now, to the beat of your love again. It feels like dum 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 da 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 da, da 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 dum 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 da 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 da, da 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 dum 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 da 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 da, da 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 dum 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 da 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 da, we might be oceans apart, but maybe you can hear it's the sound of my heart. All I want is to dance with you now, to the beat of your love again. It feels like dum 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 da 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 da, da 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 dum 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 da 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 da. It feels like
We're going back to the old school. Way back in the day. People came from miles around to hear the music play. We're going back to the old school. Back to the old school. Going back to the old school. 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 Back to the 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 old school. Drop it. Drop it. Drop it. Drop it.
The space between my body and my mind, where I just observe. I don't need anything when I'm here, because it feels like home. You can't control me.
Hi there, Ben. Okay, you're in the show. Can you hear me, Ben? Okay, I can't hear you at all, but good. Do you want me to talk? Do you want me to start the presentation? Okay. There's still background music for. Good. That's gone. Okay. Right. Fingers crossed. The technology is working. So, good afternoon, everybody. I'm very pleased to be with you virtually. I'm sorry I can't be with you in person, but I'm going to tell you about our cold water pipe joint industry project, design and model testing of large diameter deep cold seawater intake pipes for floating production, storage and offloading, floating liquefied natural gas and OTEC. And this is in conjunction with Joel and also CRN. So next slide. So just a little bit of background. I'm a naval architect with Ocean Energy Systems in Aberdeen, and I've got quite a background with moorings, risers, floating production. I was project manager for Noble Denton's mooring integrity joint industry projects, so I know a reasonable amount about them, and also was convener for the PT20 OTEC standard, and was one of the main authors for the IEA. Or was the main author for the IEA white paper. And then Joel, you've obviously already met, looks after the testing facilities in the University of Rio de Janeiro, and you will be seeing his facilities. And also he looked after the model testing of the Lockheed Martin semi-submersible. So just to explain what is a joint industry project. It's basically a collaborative effort between multiple organizations to address a common challenge. Quite often a project may be too expensive for a single organization to handle, so they allow you to share costs and resources. You have a steering committee of experts from the participating organizations who meet regularly to review progress, contribute their knowledge, and then the actual project itself is run by a specialist organization which develops the scope of work, promotes the JIP. And there, for example, you can see the JIP, the Mooring Integrity JIP steering committee, which was quite large. So what is the industry's problem? It was discussed earlier a little bit. There really is no existing experience of successful long-term deployment of large diameter cold water pipes, particularly in a vertical configuration. There is also a history of failures during cold water pipe installation and towage. That goes back to the days of Georges Claude, which you can see down on the bottom left-hand side, the steel cold water pipe buckled. And basically with a large diameter pipe, you have a large added mass, basically the pipe doesn't want to move around very much if the surface platform is moving. And then there's also factors such as creep over time for high density polyethylene that can be an issue. So basically we're trying to make use of model tests so that we can identify designs that work, and then hopefully we will be moving on to a phase where we can do offshore testing. So here you can see, for example, this wasn't for OTEC, but this was for a desalination project, but these HDP pipes that were being towed, they actually broke free, the tow line broke, and they ended up on the beach. There's also been issues during OTEC deployments, Georges Claude having issues, and then I think it's already been mentioned the challenges and difficulty with the Indian 1 megawatt program in the early 80s. So Gerard Nishus wrote in an OES publication that basically the greatest challenge left is the cold water pipe. How can it be deployed? How will it survive? And sadly, the history of OTEC is ripe with CWP failures. This was a technology readiness level. This isn't published, but it was some work done as part of the IEA OES white paper, and you can see that from an offshore perspective, there was concerns about the cold water pipe. So what we're trying to do with the JIP is develop confidence that for model testing, large diameter pipes can be long-term deployed from large monohulls in basically Brazilian and Guyanese metocean conditions. And our base case is a spread moored monohull, so it doesn't weather vane. And you can see down here on the bottom right-hand side, that's a big spread moored FPSO. So we are moving away from the somewhat complicated and expensive semi-sub that Lockheed Martin developed and come into a bog standard oil industry approach for a monohull. If we have the budget, we would like to test suitable OTEC cold water pipe diameters, and we will, as this work, understand the importance of where you hang the pipe off and develop recommendations for the best type of hull cold water pipe top joint, and have a suitable design we believe that could be offshore tested either from a new build or a late in life FPSO. So here's the organization. I'm the project director, and then working with CRN in Brazil to do most of the analysis work, and then tying in with Joel for all the model testing, but also with the university, a lot of experience with composites, which is obviously very important for materials such as high density polyethylene. This is a problem, this cold water pipe, that I discovered to my surprise that I've been involved in for some 35 years. This was a paper I did in 1989. So hopefully over time, some of the offshore experience has contributed to some of the thoughts in this JIP. Basically, the large US OTEC program, you did a screening study, looked at many types of hulls, spars, semis, monohulls, spheres, etc., tuned spheres, and they did quite a lot of work, but that was the 1980s technology. Since then, things have moved on a lot, and now we can do floating production in deep water, and there's many installed. We have much better analysis techniques, better metocean data. So we have much more confidence from actual live projects that have been installed and operated for many years that we can do this. This, for example, is Guyana, and these are a bunch of ExxonMobil spread moored FPSOs, all actually closely clustered around oil field accumulation. So we basically know in deep water, in the tropical oceans, we can spread more, particularly where the MEC conditions are quite good. So we are adopting the base case of a spread moored large monohull with the cold water pipe nominally around midships. And here, for example, here's Guyana, and then you've got Brazil further down. We know we have an excellent thermal resource and cold resource in this area. And we also know in the equatorial belt, there is an absence of hurricanes. The oil industry knows all about this as well. This is some work done in Brazil that's looking at the benefit of bringing in cool water for FPSOs. And that has many benefits that are summarized here: lower compressor power, elimination of a carbon dioxide compressor, etc. So it's a good way of reducing gas turbine emissions, reducing CO2. And indeed, this has been shown on Shell's Prelude floating liquefied natural gas unit, which is towards Australia. In this case, they went for water just at 150 meters water depth, and that water they bring in towards the stern of the vessel. But they went for a number of steel caissons, and then they went for a belt and braces approach with the connection to the hull. So they have a chain, and then they have a rubberized top connection. And the idea is if the chain should fail, the rubber can take the load for a while. And if the rubber fails, the chain could take the load for a while. But of course, you'd lose seawater containment. But it's interesting, what happened with Prelude was that the model testing was done to prove the concept before they went and installed it. And they used initially in Oceanides in the south of France a planar motion mechanism to actually drive the bundle of pipes prior to do some initial testing, prior to doing model testing with the actual hull attached. And we are planning a similar approach for our project. And as I mentioned, there's interest in this from operators and also contractors in Brazil. This is work that's been looked at by Shell and SBM. They're looking at going down to about 700 meters intake and about 1 meter diameter. This is an FPSO. They have limitations where the water can come in, so they're actually going out to the side shell. And then they're having 2 seawater intake risers, or CWPs, because they want to have redundancy. And then they're actually putting them on the starboard side opposite the riser balcony. So there is other issues that we need to take into account, for example, marine growth. Now, an interesting area is how significant is that for a deeper water? We know from Kumijima and Hawaii that it doesn't seem to be too much of an issue, but for the oil and gas facilities that have been used so far using shallower water, it's something that they have to monitor, and therefore they've had things like hypochlorite lines to try and keep the marine growth under control. So if we need to install that, we need to take that into account in the model testing. The US Department of Energy OTEC 1 is an interesting one, because that was a bundle of 3 pipes, 1.2 meters diameter, with a gimbal attached to allow some compliance at the hull. But they, again, on this one, they installed it midships center line. So right in the middle, where, for example, if there's a drill ship, you'd be drilling here. This is where they hung their cold water pipe off. And what is interesting is that the discharge line actually failed. That was towards the stern. They didn't particularly mind on that one because they just discharged, closer to the surface than they intended. but that's a significant matter. Also, there was some pump cavitation that they experienced, which is something that we need to take into account. And also on this one, which is single point moored, they actually knew from the design that the conditions could develop that they would have to disconnect to not overload the stops on the gimbal. So this is an example of a potential limitation of a gimbal design. But you can see it was a complex but well-designed system to allow the pipe to offset and therefore not overload the top joint, but it does have limited compliance in heave, and heave is a challenge for cold water pipe design. So we basically, the objectives is to understand the design issues, have with our analysis, the model testing, develop design guidance, and then calibrate our models with the model testing and understand better the how we'll connect it to the hull, and by doing so, advance the technology readiness level. We're basically looking at the first two phases at the moment. So that's all the numerical analysis, small scale flume testing, larger scale testing in the Ocean lab. And then hopefully with a successful design, we would move on to phase 3. So here, unfortunately, the video is lost on a PDF, but this is the Flume lab that you will be able to see, I hope, tomorrow. I would have liked to have been there to see it, but you will be able to see these this planar motion mechanism can move around. And then with that, you can, for example, see vortex-induced vibration that can develop on the riser pipe or the cold water pipe. And then, so the essence is that static and dynamic analysis can be done in an analysis package such as OrcaFlex. And then with computational fluid dynamics, we can do vortex-induced vibration. But we also want to look into the effect of internal flow within the cold water pipe, which does have an impact, and then also the design of hang-off connection to the hull. So there's the sort of classic current-induced deflection from a surface platform. Here, if I could play it, you'll be able to see how the cold water pipe is being excited and moving due to vortex-induced vibration. And then this slide is interesting because you can see they have been doing work on actual internal flow. So basically, there's a pump here that can suck water through the pipe so that we can take into account the effect of internal flow. This is the large-scale ocean technology lab, test lab in the university. You can see it's a huge facility, 40 meters by 30 meters with 50 meters depth. And then there is also, which is very useful for OTEC, there is a pit where you can actually you can get down to even deeper. So that's available for our use. And here, for example, you can see from the Lockheed model testing, the design that they had, a well-engineered design of gimbal for those model tests. And so we would be using something similar, but in our case, rather than the semi-sub, we would be going for the monohull spread moored. And with the instrumentation, we can compare the predictions of stresses and strains on the pipe that we've, for example, generated from OrcaFlex with what we are recording in the model tests. Base case is to look at high-density polyethylene, a single pipe, but if there is industry interest in a bundle, that is something that we could look into. So in our initial work, we've decided to discount some of the options, semi-sub, spar, barge, to go for the spread moored. There may be an option to look into weather vane systems, but that would probably be at a later phase and might well be dependent on results. But in particular, to look at the options for the connection to the hull. This is just showing some of the previous weather vaning options, and a similar vein to that one is one that has been used for oil and gas, which is the tri-catenary mooring system, where you can see that the risers are allowed. The vessel can rotate and the risers don't clash due to the system of guides. So in the early 80s, lots of options were put forward to. Some of this and this data is available to us in the literature, but the base case will be to be looking at high density polyethylene. Here there's various options to consider for hang-off. One is a gimbal design. The other is a 3-point support that has been developed when my son and I were looking at converting a drill ship into a OTEC production system, and that system seemed to work very well with the moon pool to decouple the motion of the hull from the pipe. So that's one we would like to investigate. And then there is also options for oil and gas type flexible joints. For example, the likes of Oil States seem to have stuff. Also, Plotec and Agru are about to test offshore this sort of corrugated system. So if data is available for that, we would be interested in finding out more about it. The essence of the 3-point support, just to clarify, is that there is a membrane up at the top, so that when you are pumping up, you still you contain the water. Hang-off location is important. Our preference is at midships from a motions point of view, but it may not always be the case depending on oil and gas challenges. Because, for example, quite often the port or starboard side has been selected for the smaller diameter seawater intake risers. And also coming in right on the center line also may be a challenge. But we would hope to have the option to compare, for example, midship versus aft, starboard, etc., and also midships versus midship centerline versus midship starboard. And here it just illustrates some of the oil and gas constraints. You can see all the risers and umbilicals on a spread moored unit. So it's not straightforward on a existing unit where you can come in with your cold water. It is more straightforward. It's easier if you're designing from scratch. And that also ties in with the danger of having clashes between your cold water pipe and the mooring lines or the risers, and also potentially the option of needing to optimize the makeup of your pipe depending on dynamic response. So with the JIP, we'll have, as is normal, a JIP contract that people who are interested in joining review, sign up, and then that has impact on intellectual property, etc. It's basically a nominally a multi-year program. These type of projects are normally mainly financed by the operators who potentially have quite a lot to gain from them. You can see the indicative prices. Certain companies that can provide contribution in kind. As long as the steering committee is happy, we can work out ways to incorporate them. And also because in Brazil there's the A&P tax break, so you can reinvest some of your revenue into a project like this. It qualifies as a tax break, so there is quite a lot to be said for it. And also, as you will appreciate, model testing is not a cheap activity. Therefore, we do need a good budget to progress. Here you get an idea of the schedule. So we're really looking at the, first of all, the numerical analysis, the flume testing to get our conceptual design done, and then move into the ocean basin to confirm that hopefully that it is matching, and then there may be there will likely to be a post-testing correlation with our model, such that once we've done the testing and made sure that it's working, then we can actually use that model for larger pipes and different locations, etc. So that's a fairly standard oil and gas technique. Just before finishing, I'd also wanted to give just a little bit of feedback from the FPSO forum that was held in November. I gave a talk at the forum on an OTEC power barge to supply electricity to locally clustered FPSOs. This is quite interesting in that we saw, for example, in Guyana, that there are a number of FPSOs around. They're big power users, but the actual cost per kilowatt hour from an oil and gas decarbonization point of view is quite different than from, for example, a commercial electricity generation. And for that oil and gas application, I dug out some work done by the Department of Energy, and this was looking at a very large 400 megawatt design. But that is interesting in that they deployed the cold water pipe midship center line. Such a large hull has less motions. It makes the spread mooring is cheaper, and cable export is easier from a spread moored unit. And this size is actually comparable to the multi-purpose floaters that are being used in Guyana and also off Brazil. So at the conclusion of that, there was an online poll for the audience of 100 odd people, oil and gas specialists, renewables, and the question was which technology is most likely to be developed for FPSO electrification. Floating wind was top, but I was pleased to see that there was sufficient confidence that 11% were looking at OTEC, well in the lead from wave energy, tidal, and floating solar. Clearly, if you're close to shore, there's advantages at looking for shore power. So that hopefully wraps it up. I hope I'm run over time. If you want any further details, please get in touch with myself or Joel or Cassiano. And thank you for the opportunity to present this. If the technology works so that I can hear questions and can take questions, I can take some if there's time. Thank you very much. Technology's not working.
I want it.
Come up and talk about deep OTEC.
Hi folks, good afternoon to all. My name is Vicente Faquina. I work in Petrobras for almost 20 years, and I plan to retire within a few years, okay? And I'm going to talk about deep OTEC. Yes. Deep OTEC, no pun intended, but I think I thought of this. No pun intended, but I thought of this as a deep synergy to the oil and gas industry. Okay, and you're going to see very soon that I stick very tightly with the OTEC acronym. It's Thermal Energy Conversion in Ocean. You shall see very soon why I'm speaking that way on OTEC. Okay, so let's go forward. Well, OTEC, the classical thing everybody knows, okay, as is like a heat pump, okay. We have a hot source and a cold source and a work fluid between them, okay. So this is a classical approach. There are other which are better than this, okay, several others. And the issue, one of the biggest issue is this here, the cold water pipe is a big issue, okay. There are some other issues, but that's the classical design, okay. And when I thought of doing this, this very year, when I got to know of this event, okay, something like a deep connection with the work I did in Petrobras for the last 5 years, which is in deep sea EOR, enhanced oil recovery, okay. So I searched in my mind, how can I possibly contribute with some idea, a spin-off, okay. So let's go forward. Well, these are the classical drawbacks of the classical OTEC concept, okay? So, installation, big water pipes in open sea, okay? Unstable offshore environment, waves, storms, like that, which happened in the 30s in Brazil coast, okay? Completely destroyed. Heat source dependent on latitude, okay? Biological impacts, you understand this by negative biological impacts, okay? Because there are positive biological impacts, okay? And here you read negative biological impacts, like ammonia leaking and a temperature difference and so on and on, okay? So, these are the basic kind of drawbacks in the classical designs, okay? Well, energy efficiency, that's a tough one, okay? It depends on latitude, okay? And we gotta have at minimum a 20 degrees temperature difference between top and down. And this happens in the in tropical waters, okay? Only in the tropical waters. So it's a limitation, okay? With this temperature difference, okay, you have a very low energy efficiency as to other assets, okay? Around 3%. It's 3% with the ammonia cycle, the classic one, but it can reach up to 4.5% with another cycles, and even more with other designs, okay? For instance, ray design, okay? So these are the drawbacks, the classical drawbacks. And so let's go forward. Now, the opposite of those drawbacks are those kind of advantage of deep OTEC concept, installation, okay? installation. No big water pipes in open sea. No big water pipes. Oh, great, it's magical. Moonshot, Mars shot. Okay, there. Okay, stable environment, no wave storms. No wave storms, okay. Heat source, independent on latitude. Oh, that's great. So some guys here are already thinking of this deep OTEC, okay? It's simple, 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 but away from the OTEC thing. Let's go think. Energy efficiency, okay? Well, with this luminous deep OTEC concept, okay, energy efficiency can be much more than with 20 degrees temperature, okay? We can reach temperature difference way higher than this. So the higher the temperature difference, the higher energy efficiency, okay? Much higher. So for those who didn't get this yet, the concept is this. This, okay? I thought of this because of deep synergy with the deep oil and gas business. So the heat source, okay, is not the surface ocean water, is the hot below the seabed. It's a geothermal. It's a deep sea geothermal, below seabed, okay? And this thing for the oil and gas business is pretty easy, okay? Not quite so in this region, okay? In deep sea, okay? Not on shore, okay? So for instance, it's the same engine, what changes? The heat source. Is this the heat source? Deep sea geothermal. I read a paper about this, on this about 10 years ago. That, oh, this is great. The problem is more non-technical than technical, okay? And so I hear the zero level, okay, is the seabed, okay? Seabed is the zero level. Down here, this depth here depends on what temperature I wish to get, okay? So L is dependent on temperature of the heat source, okay? The deeper I go, the higher this temperature. And the cold source, all around, and about 1,000 meter depth, all around 4 or 5 degrees. Great, okay? So the same engine, okay? And the hot source is this, okay? This is very kind of illustrative, okay? In between 4 billion years, the sun will explode, so I couldn't have, okay? But well before this, humankind will be off. 2 billion years. So that's the engine, okay? Deep geothermal, okay, and it fits quite well in the OTEC acronym. It's an Ocean Thermal Energy Conversion. The change is on the hot source, okay? So you see that no more cold water pipe, okay? Big, okay? And here is a question, an issue, a big issue of geothermal engineering, which is being around for more than a century, but applied deep sea, okay? The big challenge, but not impossible, okay? And the costs, okay? Like Ross said, okay, the cost is a simple thing of integrating the mines, and the cost, it goes out naturally, okay? Well, this is a famous scale, appraisal scale, TR, technical readiness level, okay? And when I thought of this, I think, oh, and we did some calculation. I did some calculation, okay? And then it fits quite well in 2, okay? TRL2, okay? And here is a figure for NASA. You just substitute water for space, okay? This, okay? Same thing. By the way, I'm working in enhanced biorecovery thing that is in the 5 stage, okay? It's a very good one, okay? Let's see. Whoops. Okay. No. Well, these are the calculations, okay? And here we have a unit dispatchable electricity as a function of the energy efficiency, okay? And so if I multiply those units dispatchable electricity, I get the nominal power, okay? I mean, if I multiply it by the mass flow of water, I got the nominal power of the exit, okay? Just this, okay? It's a power demand, okay? So my basic kind of calculation was a kind of thermodynamics one, okay? I set the cold source as 4 degrees Celsius, okay? And the heat source going from 300 Kelvin to 1000 Kelvin, and so on, okay? It is a unit available heat, is like heat exergy, okay? All the thermodynamic functions, okay? And this is a temperature enthalpy diagram. So for instance, by this number here, I work in the in this region here, which is superheated steam, okay? At 100 bar, 1,000 meter depth, okay? And that temperature ranges above 600 Kelvin. I work on that region here, which is superheated steam. Nevertheless, okay, if I get even deeper, let's say 2,500 meter deep down, I reach at that region here, which is supercritical water. But that is very, very expensive. It's a Mars shot, okay? Because it implies on installing those facilities at 2,500 meters down to get that condition here, supercritical water, okay? So that simulation here was for 100 bar superheated steam, okay? You see here is the temperature. Here is the unity dispatchable electricity or heat. Here is the input heat, okay? Here's the output electricity, okay? Here is just the kind of heat sink temperature variation, okay? The more temperature, the more the heat sink variation in temperature after the cycle. Right? Okay. Let's move forward. Well, this here is one more figure of many, okay, to appraise for risks. That figure here is usually done in several formats on the stage 1, IPA phase 1, which is a business problem or business opportunity, before concept design, way back, okay? So for instance, I put here 4 dimensions, technology, innovation, complexity, lead time, okay? And the larger those areas, the larger the risk. Okay, statistical risks, okay? So for instance, I put here a baseline, which is deep oil and gas subsea deployments, is this, okay? And I put here the deep OTEC risks, okay? So for instance, in this dimension here, innovation. 1 means it's a current product. 2, a product revision. 3, a new product, okay? And so on and on. So for instance, in technology, okay, 2 is complex, system integration, okay? And so on, okay? In terms of business, okay, these things are business for profits, okay? So I gotta have lead times. So it's 2. Business plan, okay? No critical, no crisis. It is a business plan, 2. Business plan is a business for profit, 2. Okay? And complexity is the same. Complexity, 3. Asset, network of systems, okay? Not a field. A field is if I have several assets. It comprises a field, but one asset is 3. A network of systems, okay? So for instance, an oil field, several kind of assets will be 4. Field, network of assets, okay? Not this case here. Maybe in 20 seconds, in the center 20 seconds, okay? Okay? Here, it's another format of displaying kind of deliverable, business deliverables, okay, interface. So I put in the diagonal, okay, a scope segmentation, okay, or the parts of the business, whatever, okay. So for instance, here, I put deep OTEC, and in the kind of horizontal line which every single segmentation delivers, okay? And the vertical lines is what each segmentation receives. It's symmetrical, okay? Symmetrical thing. So for instance, if I zoom in this cluster here, okay? This cluster here is what? It's comprised of a electronic unit, a hydrogen plant, and an oxygen plant. So what is needed? Electricity from deep OTEC, a potable water from a potable water plant, okay? Electricity, and it delivers what? Hydrogen and oxygen. Cool. Here, I put a scope segmentation, which is other demands, okay? Which can be electricity, heat, potable water, VSC cold source, okay? Ammonia. Another interesting cluster is this here, okay? Surface water air conditioning, okay? So it's another format of displaying interface between a scope segmentation, whatever they be, okay? Right? Next. And conclusions, okay? From the classical OTEC design from this, okay? It's just a matter of switching the hot source. And what's needed? Interface measurement across oil and gas and geothermal power sectors is crucial. This is crucial, okay? So for instance, I don't see anymore, because I start to think on this about 15 years ago, I don't see anymore some showstopper in technical stuff. No, the showstopper for me is non-technical. It's non-technical, okay? Integration between several areas, okay? Geothermal drilling, deep sea floor is innovative, okay? The technology of deep sea comprises integration of complex systems, okay? And eliminates drawbacks of the classic concept. Here, what is behind this, okay? I don't agree as well with event, with one route only. If you can manage sometimes to comprise several routes like this, like oil and gas, like offshore wind, the synergy begin to appear naturally, okay? Because it's a question of synergy, of communication, okay? So what I see in these 15 years, many technical drawbacks being overthrown, great, but not this, okay? Integrating big business in a single purpose is not trivial, okay? It's more a measurement challenge than a technical one, okay? Let's see what's more. And that's it. It was kind of provocative presentation, because I feel I can do this, okay? Since 2010, I went through many simulation networkings, okay? I simulate several engines, several OTEC engines, Kalina, O'Hara cycle, etc., cold water pipe, okay? And I came to the conclusion, oh, okay, this is going to be solved naturally around time, but the non-technical issues are the greatest one. Thank you very much.
Thank you for your presentation. Unfortunately, we don't have time for questions, so we don't have time for questions. Sorry. If you have questions, please ask during the break or another time. So our next presentation will be a video, combined cycle for offshore OTEC installation from Ahmed Baya from Morocco, former naval officer and graduate of the Royal Moroccan Navy.
Mesdames et messieurs, bonjour. C'est un grand honneur pour moi de prendre la parole aujourd'hui lors de ce symposium afin de vous présenter un nouveau cycle thermodynamique qui promet de révolutionner la technologie de conversion de l'énergie thermique des mers, connue sous l'acronyme ETM, redéfinissant notre manière de concevoir et d'envisager cette technologie. Grâce à ce cycle thermodynamique combiné que j'ai développée et brevetée, cette technologie ETM, autrefois limitée aux régions équatoriales, devient accessible à tous les pays dotés d'un accès maritime. Ce cycle combiné ouvre des perspectives inédites pour l'exploitation de l'énergie thermique des océans à une échelle mondiale, transformant de manière significative le paysage énergétique global. Avant d'aborder les détails techniques, permettez-moi de poser le contexte. La technologie ETM, malgré son immense potentiel, n'a pas connu le progrès significatif qu'elle devrait avoir à cause des défis techniques et économiques, en particulier par l'efficacité limitée des cycles thermodynamiques traditionnels, directement liés au faible écart de température entre les eaux chaudes de surface et les eaux froides de profondeur. Les spécialistes dans ce domaine suggèrent d'améliorer l'efficacité énergétique par le biais de recherche et d'économie d'échelle. Les grandes installations offshore pourraient devenir rentables et compétitives tout en réduisant les émissions du dioxyde de carbone. C'est dans ce cadre que ce cycle combiné s'inscrit, apportant une solution innovante qui non seulement améliore l'efficacité énergétique, mais respecte aussi les directives des conférences des parties pour le changement climatique. Solution apportée par l'invention. L'invention du cycle combiné pour équiper et améliorer l'efficacité des installations offshore utilisant la technologie ETM constitue une avancée technologique majeure vers une relance accélérée de cette technologie. Ce cycle combiné diffère des cycles connus à ce jour et plus performant. Afin d'éviter les problèmes de raccordement des stations offshore en réseau public, de résoudre le problème de pompage d'eau froide sur de longues distances pour alimenter les stations côtières et de généraliser l'exploitation de la technologie ETM à tous les pays du monde, l'invention propose de procéder en deux étapes, une étape offshore et une étape côtière. L'étape offshore consiste à déployer plusieurs plateformes ETM flottantes de grande puissance dans les régions équatoriales, de manière à ce que chaque plateforme soit entourée d'eau chaude en surface et l'eau froide se trouve en dessous à une profondeur de 1000 mètres. L'approvisionnement en eau froide de chaque plateforme serait assuré par pompage à travers la conduite d'eau froide de diamètre suffisamment large pour limiter les pertes de charge. Chaque plateforme serait équipée des dispositifs nécessaires répondant aux exigences du nouveau cycle thermodynamique développé par cette invention. Au cours de l'étape offshore, l'énergie thermique sensible stockée dans les océans est transformée en énergie thermique latente stockée dans de grands conteneurs isothermes embarqués à bord de bateaux pour faciliter leur transport vers les stations côtières. Le stockage de l'énergie thermique est assuré par la congélation de matériaux à changement de phase à des températures négatives très basses. L'étape côtière se déroule dans les stations ETM côtières équipées d'infrastructures pour accueillir les bateaux isothermes. Elle n'utilise pas forcément le cycle combiné, elle fonctionne selon le cycle de Rankine traditionnel. Elle consiste à produire de l'énergie électrique en exploitant l'écart entre la très basse température de fusion du matériau à changement de phase contenu dans le conteneur isotherme embarqué à bord de bateau et la température de l'eau du littoral local. L'étape côtière ne se limite pas à la zone intertropicale. Il s'applique à tous les pays ayant un accès à la mer. La construction de stations côtières capables d'accueillir les bateaux isothermes est cruciale pour pouvoir profiter de nombreux avantages de la technologie ETN. En plus de la production d'électricité, de nombreuses activités parallèles peuvent être développées pour valoriser le froid résiduel, maximisant ainsi l'utilisation des ressources disponibles et créant des opportunités économiques et des emplois. Parmi ces activités, on peut citer le dessalement de l'eau de mer par la méthode de congélation, fournissant de l'eau douce de bonne qualité à bas prix. L'utilisation du froid résiduel pour des systèmes de climatisation offre une solution durable pour le refroidissement des bâtiments et des infrastructures. De plus, l'aquaculture, notamment l'élevage de poissons et de fruits de mer, pourrait tirer parti des conditions favorables créées par le terrain. Prenons par exemple un pays situé à l'extérieur de la zone intertropicale tel que le Maroc. Le Maroc est un pays bordé par l'océan Atlantique où la température moyenne au cours de l'année de l'eau le long du littoral atlantique marocain est de 19 degrés Celsius, ce qui laisse à penser que le Maroc ne puisse pas bénéficier de la technologie ETN. Cependant, grâce à l'innovation du cycle combiné, le Maroc pourrait tirer profit de cette technologie à condition qu'une infrastructure appropriée soit mise en place, notamment la construction de stations côtières capables de recevoir les bateaux isothermes. Dans cette nouvelle configuration, les paramètres sont modifiés, sachant que la température de l'eau de surface de local est de 19 degrés Celsius, et supposant que la température de fusion du matériau congelé soit de moins 35 degrés Celsius, alors la différence de température entre les deux sources devient 54 degrés Celsius. Cette augmentation significative de la différence de température entraînerait une amélioration importante de l'efficacité des installations côtières, la portant à plus de 18%. Cette performance représente une nette amélioration par rapport au rendement précédent qui était inférieur à 2%. Ces résultats suggèrent que plus la température de fusion du matériau congelé est basse, meilleur est le rendement. Ainsi, il est crucial de choisir un matériau ayant une température de congélation négative très basse pour stocker l'énergie thermique sous forme latente. Description de la technologie du cycle combiné. Le cycle combiné que j'ai développé se compose de deux cycles distincts. Un premier cycle représenté en rouge sur le schéma à gauche de l'écran et un deuxième cycle représenté en bleu sur le même schéma. Le premier cycle est le cycle organique de Rankine fermé. Il comprend les équipements suivants, numérotés de 1 à 6, reliés entre eux par des conduites formant un circuit fermé. Une pompe haute pression, un évaporateur haute pression, un surchauffeur de vapeur haute pression, une turbine haute pression, un condenseur moyenne pression et un réservoir moyenne pression. Le cycle de Rankine exploite la détente de la vapeur dans la turbine entre la haute pression de l'évaporateur et la moyenne pression du condenseur pour produire de l'énergie électrique. À cause du léger écart de température qui, dans les meilleures conditions, ne dépasse pas 25 degrés, entre l'eau chaude de surface qui chauffe l'évaporateur haute pression et l'eau froide des profondeurs qui refroidit le condenseur moyenne pression, ce cycle atteint à peine un rendement brut d'environ 7%. Le deuxième cycle est un cycle flash trilatéral comprenant dans l'ordre les équipements suivants, numérotés de 7 et 12, en plus de réservoirs moyenne pression, reliés entre eux par des conduites formant un circuit fermé. un détendeur diphasique, un évaporateur basse pression monté à bord d'un bateau isotherme, un surchauffeur de vapeur basse pression, un compresseur, un désurchauffeur, un condenseur moyenne pression et un réservoir moyenne pression contenant le fluide de travail. Ce cycle utilise la détente flash du fluide de travail à l'état de liquide saturé ou un mélange liquide-vapeur dont le détendeur diphasique entre la pression de saturation du réservoir moyenne pression et la pression de l'évaporateur basse pression pour produire de l'énergie électrique. Chers invités, votre expertise et votre influence sont essentielles pour transformer cette vision en réalité. Je vous invite à vous engager dans ce projet révolutionnaire pour explorer les nombreuses opportunités qu'il offre pour l'avenir énergétique du monde. Ensemble, nous pouvons établir un modèle durable qui non seulement répond aux besoins énergétiques actuels, mais qui prépare également un avenir plus prospère et indépendant pour les générations futures. Soutenez cette innovation et devenez les pionniers d'une nouvelle ère d'exploitation de l'énergie thermique des mers. Mesdames et messieurs, pour conclure mon intervention, je dirais que l'invention du cycle combiné est une avancée technologique majeure pour exploiter pleinement l'immense réserve naturelle d'énergie renouvelable et gratuite qui est l'énergie thermique des mers, offrant une opportunité incroyable pour diversifier notre mix énergétique et réduire notre dépendance aux combustibles fossiles tout en limitant les émissions des gaz à effet de serre. Je vous remercie de votre attention avec toutes mes salutations les plus sincères.
Okay, thank you very much. Merci beaucoup. Yeah. Our next presenter, I believe, is here in person. So we'll have 100 kilowatt OTEC pilot plant using CO2 as working fluid in a novel triple phase thermodynamic cycle in Santa Cruz, Oaxaca, Mexico. So the speaker is Eduardo Perez Casas. Please come forward.
Hello, good afternoon. Okay. Okay, too much. My name is Edgardo Perez. I am representing this project that we have been working in Oaxaca, Mexico since 2017. Okay, so as a background for the project, Ansegre is a cooperative that was founded in 2017, and we have been looking for implementing OTEC technology since then. In 2019, we designed a community development model because we are aiming to bring this technology to the communities back in Oaxaca, Mexico. And we already executed in 2018 with public funds pre-feasibility studies for installing an OTEC plant back in Oaxaca, in the coast of Oaxaca. We have a partnership with another company in Mexico, which is DTMI from Querétaro. And they have been working with the carbon dioxide as working fluid since 2016. They actually got funds from the World Bank for making a prototype, but for working for a gas turbine above 100 degrees. So we met in 2019, and between 2019 and 2020, we proposed to combine what we were doing in OTEC and what DTMI was doing with carbon dioxide. And we primarily were trying to make a carbon dioxide triple phase thermodynamic cycle maturation program, what we have been working the last years. And of course, one of the goals is to build a pilot plant using this thermodynamic cycle. And at the same time, we are trying to bring this technology to a sustainable growth pole, which is an industrial park that we will try to install in the next coming years, so we can bring this to the communities, as I said. Okay, so this presentation won't be focused on the thermodynamic cycle, of course. This is something that we are working, and some people from here actually already signed a DNA to see what is behind this. But as a summary, this is a new thermodynamic cycle, right? We are not using Rankine cycle. So, and what are the advantages compared to regular OTEC Rankine cycle is that we can get efficiencies above 10%, at least from simulations. And we don't, the most important one for us is we don't require the cold water pipe. We just use surface water. And we have, besides the cooling aspect of OTEC, we have freezing, so we can go below 0 degrees centigrades, and we can also make an improved desalination process, because we can desalinate through freezing, like the icebergs, for example, 1%, and of course, LTTD, it's better because we have even lower temperature, right, from the cold water. We also reduce the amount of water pumped, and we need, at least from our simulations, of course, and our design, for 100 kilowatt pilot plant, only 8 liters per second, right? And of course, because of this, we have all of this, right? We have low tonnage, of course. The pilot plant is very small, actually it's mobile. It can be towed. It has a very low capex and opex, of course, because you remove everything complex from naval engineering, big pipes, of course, deep sea water pumping. It has higher scalability onshore. We don't need to go offshore. And we need even less area to implement our technology. And this is translated into a lower LCOE, a levelized cost of energy, which we can begin to have it since 5 megawatts instead of going up to 50 or 100 megawatts, right? The process, the another important aspect about OTEC, of course, is the is the subproduct extraction, right? We have slight differences, of course, regarding regular OTEC. As we don't pump from deep sea water, we don't have as much of nutrients, of course. We don't have metals, minerals, but in the process of generating the energy and through adding the desalination process, we can get pretty much everything that is useful, at least for industry. We still have agriculture and aquaculture because we are extracting seawater, which has, of course, nutrients that are useful for these industries. And we are also adding warm air because back in Oaxaca, we have a lot of industries that use warm air so, for desacidification, right? Or pasteurization, for example. No? So this is just numbers based on what we have been simulating. Of course, we are adding tonnage of refrigeration, which is something that we add besides the air conditioning. Okay. Yeah. And we prepare this for the government of Oaxaca, of course, because as we are closing a public and private partnership with them, they are interested in knowing what are the benefits, right, for what industries. So we pretty much have most of regular OTEC subproducts has, of course, and you are adding the freezing. And these industries in particular, we will see further in the presentation what are of interest in this case. Okay. Just continuing with the background of the project, back in the 2021, we presented actually this thermodynamic cycle proposal in the Cancun Symposium, the 8th Symposium. And we also presented the implementation program for OTEC in Oaxaca. We have 2 presentations back in that symposium. In 2022, we got another grant from the state of Oaxaca, the government of the state of Oaxaca. And we moved, and we did the fabrication plans, the philosophy operational, the global simulation of our design. And in that time for the 35 kilowatts, of course, it is useful for another amount of energy. And in last year, we consolidated locally, a local cluster, just to reinforce what we are trying to do for the subproducts industry. And we began to look for a private association, especially with another companies or another efforts globally, internationally, abroad. One of them was an MOU that we are working with Value Park, which is working in SWAC back in France. They are going to bring their technology to Oaxaca, and they are interested, of course, in working together for the carbon dioxide triple phase thermodynamic cycle. And we got evaluation through DNB by Shell to the thermodynamic cycle, which led to, they say that we needed to build make a test bench of a critical component, of course, because the models in the simulators were not prepared, or they are not usually used for what the use we want to make it. So there are no coherence between different mathematical models. So they asked to us to build actually this particular critical component before they go into the investment, right? Okay. So currently, well, we can say that we are moving to the TRL3. We already have the fabrication plans, the simulations. We already have actually the fabrication drawings to actually build our prototype. This year, we gathered since last year and this year, because we don't have any investor, private or public, except what we do with the state of Oaxaca. But we didn't receive anything these 2 years, so we moved from our own money, and we are actually this month constructing the proof of concept of this critical component. So in January and February, we will have the test bench with the results, right? We moved forward actually because we found documentation from another researchers around the world that gave us the confidence about what this critical component we were trying to do had the coherence we were looking for. And so what's coming next, of course, is the 100 kilowatts pilot plant. As you can see, it is not real scale, of course, but this is some of the numbers that we are expecting to get from this pilot plant. This will be confirmed once we build it and have it. And we are having pretty much every single pilot plant OTEC will have. And we are also adding, of course, the agriculture and aquaculture, the freezing and cooling aspect. And that's, well, we can see better in the next slides. Okay. So what are some of the implications about our technological core? Of course, is that we are aiming to have optimized applications in the real world, in the real industry, of course, same as every single OTEC design. And for desalination, we have, of course, the possibility to have extra energy. Why? Because when we produce the energy, we produce from different technologies probably a slight better desalination process, right? So we are going to test in our pilot plant. We have a module for desalination, seeing how much we can get from freezing desalination, and also how much we will improve the LTTD already know technology, because we will have freezing temperatures. So we expect to have higher efficiency than regular LTTD, which is around 10 degrees of a delta, temperature delta. We will have even more. And as we will have extra energy, we are thinking on producing, we will see this further. I think I have a slide. I can explain this later better. But for the agriculture and aquaculture, even if we don't have so much nutrients from the deep seawater, we still have nutrients from the deep seawater. And also, as we are adding the freezing aspect, we can make a mix of with the food industry, right? Because we can have the freezing aspect of the food industry. And these three industries, like the data centers, of course, are one of the most interesting applications of our thermodynamical core, because we will be producing the energy, and the effect to produce our energy is to produce the freezing air or water. So we will save to data centers, of course, almost half of the energy they today use to produce the freezing, right? Most of the data centers use almost up to the 50% of their energy just to have a cooling system, right? A chiller. So we will have the chiller while we produce the energy, right? So we will reduce the cost for data centers to work. The green hydrogen, of course, is another interesting application, because in the process of having the energy, we can produce a small amount of desalination water through condensation, just from the environment. We will see another slide where I have an explanation of this. But this is, of course, something interesting. Also because we have the freezing aspect, right? The freezing aspect for storaging the hydrogen will make that you need less space to storage the same amount of hydrogen. And for SOAC, we will add the freezing industry. And of course, we will increase the already good application of SOAC from OTEC, because we will have more, even more low temperatures, right? So we can have extra energy to pump this air conditioning to the inland, like several kilometers, because of the extra energy, and also because we produce even lower temperature in the air. So it will be easier to move, away from the coast. Here is a quick explanation why we have an optimized application of green hydrogen, as we only need a very low percentage of the seawater to produce 1 kilogram of hydrogen. I mean, to produce the 50 kilowatts, I mean, we are using like standard numbers, of course. We need 9 liters, and to produce that 50 kilowatts, let's say that we only need less than 0.1% of the water we are pumping, and we can easily get it through the environment condensation, right? Because as we are in the coast, we have great temperatures, especially in Oaxaca. We have even above 40 degrees centigrade in the air. So you can imagine that we can easily get that water without any extra infrastructure and extra investment. We will just get a desalination unit within the OTEC plant, just by air condensation, right? So we, freely, and as we already know, OTEC doesn't require a lot of space, right? Inland, you need a lot of space in the ocean, but inland, you won't need it. And especially our technology, which is even smaller. This is an application that we did with the help from the government in Oaxaca, because they are actually trying to build this these days. They gave us these numbers so we can compare what are the benefits of using OTEC, compare what they already have approved for a big company, Helax, which it's already set up, right? They are going to use 30,000 hectares to make this amount of energy, 9 terawatts per year. This installed capacity, and that they expect to produce this amount of tons of green hydrogen. This is, as I already said, it's already settled up. And this is our proposal. If you can see it correctly, we just need a very small amount of space. Of course, as we have base load, we need even less installed capacity, which is makes cheaper the line transmissions, for example. And we produce even a little bit more of tonnage. This is something interesting that it is related with the technological core, because this OTEC, I haven't mentioned it, but can produce a little bit more energy during the daylight. We have the base load production, same as OTEC, but during the daylight hours, we have concentrated panels that are heating up the carbon dioxide, not the water, because the carbon dioxide improved a little bit, like a small percentage during the day. So we even have intermittent energy during the daylight, which gives us a slight production of energy, right? We are trying to use this. Of course, this is for green hydrogen, but for our project back in Oaxaca, we will use this extra intermittent energy for the subproducts industry, right? We will use this as a freely energy that we will get, so we can make industry that don't work exactly like with a base load, but can work with this extra during the day, right? And of course, for massive green hydrogen projects, we are expecting, according to our simulations numbers, to have these benefits compared, of course, with solar and aeolic energy, which is already matured and applied in Oaxaca, especially in the isthmus of Tehuantepec, which is the best places, at least for aeolic, is one of the best 10 places around the globe. Oaxaca is very well known for this. Well, it is going to be well known also for OTEC, of course, eventually. But we are comparing this to an actual project that has been approved. And for future projects, we are trying to make the government of Oaxaca and every single company, of course, to see the difference between applying this. The most important aspect for us, I mean, this is very interesting and important, is that we don't remove the land from the people, right? One of the biggest problems that Oaxaca has now, because of these kind of problems, is imagine to remove that kind of land to the people, to the environmental. You have to remove every single tree, no animals for that amount of hectares, right? If we have something like this, all the anthropological, social, and cultural, and the entire ecosystem, right? Not just the environmental, like the trees, the animals, the plants, but also the activity from the people won't be affected. Even better, they will be benefit because applying this will bring also some of the subproducts industry, right? So they will be powered also because of the subproducts industry economy project. This is the desalination, of course. As we mentioned, we are trying to apply pretty much two technologies that are already working right now. This is just how icebergs work, right? At 0 degrees, fresh water is transformed into ice, but seawater, as we know, won't be ice. So we will be separating the fresh water through the icing, right? And the LTTD improved because we have a large temperature delta between the cold and the warm water. And we are already using this. In our cooperative, we have designs for the water waste treatment in some municipes and even the state. And we use electroflocculation, which is another emerging technology which accelerates the process of removing some big particles within the water to clean it, of course. And we will use it to remove some of the salt. So this is very important because this is the environmental aspect we need, so we don't contaminate the water with brine, right? Which is the biggest problem for desalination in the entire world. So we are going to implement that, and we can implement it because we have extra energy, right? So we don't need to invest more in this technology, except of course, the plates, you know, to electroflocculation. And as a summary, we don't have brine. We also, of course, have the subproducts industries, especially the salts, minerals, and fertilizers, compost that we will get from gathering the, you know, converting every single cubic meter into fresh water, or not every single, the percentage we are going to get. And we will have extra energy to even pump this water inland, right? So we can supply cities that are not close to the coast with fresh water, right? This is another example that we have already been working with the state of Oaxaca, because they will have this need. They will need 265 millions of meters of cubic meters of fresh water every year for the growth poles that they are going to, they are already approved, but they will be working next in the incoming 2 or 3 years. But they are their projection is that they are going to have in 2030 this need, right? Right now there is a big problem because they don't know where they are going to get that amount of water, right? They can have desalination plants, but they will be very costly. And if they remove that fresh water from the, you know, the subground, it will be a social problem because people won't have water for them. And just some estimations about the cost of the cube meter of water. And one of the advantages that we are presenting is that eventually, at least with the partnership with the government of Oaxaca, the maintenance operation will be covered by the subproducts that we will bring with this plant. So the water will be free after some years of operation. This is what we are going to do in the incoming years. We begin with the thermoelectric core, which is of course the one that has the heat exchangers, the expansion, as I mentioned, the solar concentration, just to give a little bonus of energy, intermittent energy, pumping and seawater pipe, you know, everything related with the thermodynamic electric aspect, of course, of this thermodynamic cycle. But the project is bigger than that. We are aiming to have actually sustainable growth pole. Why? Because if we add, of course, this part, which is important, to the pilot plant, we need to have an ecosystem technology, electric core integrity. We need to look at, we need to take care of the ecosystem and, of course, the pilot plant itself. And the monitoring, controlling, everything we need for the discharge, the safely discharge, of course, of the waste. If it is water with an amount of brine, at least on the first stages of the pilot plant. And eventually we will have the subproducts, the facilities. This is how we are going to use our budget. We are estimating a total cost of $3 million. We already have this from the government. No, we are asking only 30% to the state of Oaxaca. And Our idea is to move forward to the pre-commercial and commercial plant once we have the pilot plant. No? And we can do it even in the same pilot plant because it is a very small pilot plant. The thermoelectric core, for example, it is pretty much like the size of this area where I am, like 2 cubic meters, like 1 by 1 by 2 meters. We will tow it, actually, so we can have a demonstration OTEC pilot plant using this triple phase carbon dioxide design, and we will move it through the coast of Oaxaca, right? And what is our business model? Well, we're proposing to have, of course, we will be moving from the OTEC plant to the OTEC Technological Park, where we already have, the applied research, the subproducts extraction and separation, the environmental protection unit. Then, if we involve the industry, we will have the industrial park and eventually the sustainable OTEC microgrowth pole. Why is important this project and why now? Because Mexico is having, I don't know if you know it, the interoceanic corridor Isthmus of Tehuantepec project, which is a huge project that is going to compete with Panama's canal, for example. These are some numbers. This is official. You can look for them in the internet, of course. This is what federal government is doing. It is a huge problem. This is an example of a growth pole. They will have a lot of needs for energy, water, sub-industries, and that is how we have a chance to put into this context our OTEC design, right? And finally, okay. Just, I think there are only two another slides. Today, we have this agreement with a cooperative, agricultural cooperative. They are gathering, they have this, they have 1,200 sesame farmers, and we already have, the partnership with them once we have the pilot plant, so we can have the agricultural aspect of it. And we are also finishing or closing a public-private partnership with the government of Oaxaca in the context of the interoceanic corridor, as I mentioned it, and they will finance the 30%. We are looking for the rest of the investment. We are fabricating and testing the critical component through the test bench that we will have next year, probably in January, February. And we already began the academy vinculation with the universities and research institutes that are in Mexico, and I think you know very well. The Unicaribe, the UMAR, right? They are also with us working with this academic vinculation. We already have also the land. We have an agreement to use part of this land because it is too much. It's 500 hectares, but it's perfect for the project to long term because we will fit any industry we want for the pilot plant. You can grow the pilot plant beginning at 100 kilowatts to any megawatts we want. And finally, what's next? As I already said, we are installing the pilot plant. We will eventually in 2026 and 28, we are aiming. This is going to be very fast because, as you can see, our pilot plant is very small. We don't need cold water pipe. This can be done for us. We think that easily in 2 years, right? And from that, in 2026 and 28, we will have the construction of a pre-commercial 5 megawatts, of course. And beyond that, well, the most interesting part of this is that we have tons of application of this thermodynamic cycle. Why? Because we can use it to low gradient geothermal. We already have studies in Oaxaca for doing that, same as OTEC. We can have green ships, of course, using the same thermodynamic cycle. We have, of course, as I mentioned it, desalination optimized, dedicated growth poles, these only growth poles, and the data centers, and we are looking to even have a feasible less than half a megawatt OTEC CO2 triple phase design, which we are thinking we can bring to the communities in every world, not only Oaxaca, right? This would be sufficient for most islands, small islands, and small communities that are not connected to the grid, or they don't have the fresh water, right? So this is something that we will be working later on. So a small amount of investment can make a huge difference to people that need it more. And just to end, what are we looking for? Of course, technological partnerships. We need a lot of experience that actual technological companies right here have in your countries, of course. Just to follow up methodologies, know-how, pretty much what OTEC is trying to standardize, and this symposium is trying to do. That's why we always attend the symposiums. I was here in the first symposium I attended was the Okinawa symposium. I didn't present anything. I was just met some of the guys that are actually now working in our project. And of course, investment, right? We are looking for this investment. We are looking for several options, but we are also, of course, receiving help if anyone wants to help on this. We only need $2 million. We have already one. And with this $2 million, we will build what already said, the 100 kilowatts pilot plant. And from that, we will probably won't need more investment or help to get investment because the results will be sufficient to get the finance, even from banks. We won't need investors or equity investors, right? We will probably be sufficient to get money from the banks, and the same pilot plant will generate money. That's the idea, will be sustainable. And for the academic research institutes, we need to work back in Mexico and national islands and internationally with the Saga University, you know, the university that are already working the Brazilian one. We have been talking separately with each one of you. Some of you already know about the project, but of course we need to move forward with this academic or applied research aspect because we are, even if we are a private company, I mean, we are a cooperative, that's a private company, even if we are a private company, the TMI is a private company, we're very interested to put Mexico into the global map, right? And the academy aspect is very important and we are supporting it. Thank you.
Okay, we will move right along. We are running out of time. So next up is Mr. Jim Anderson, President of Sea Solar Power. I'll let him introduce himself further. His presentation is an economical 20 megawatt OTEC plant can be built today.
This one? Is it turned on? Good. Good afternoon. Thank you for the Ocean Thermal Energy Association for having this conference and allowing me to give a little presentation. I'll go fast. If you have questions, you may ask while I'm going. Okay, the presentation is about our technology, and the presentation is about our ability to be able to present and build a 25 megawatt floating ocean thermal energy plant today. Let's see if this works. I won't bear on this slide. We've all seen it. The ocean is filled with thermal energy all over the world. And in fact, we can probably supply 80 to 90% of the world's population with ocean thermal energy technology directly and indirectly to Europe. Again, this slide is familiar to everybody. We have warm water at the surface and we have deep water down deep. There's always a question is how deep do we go? 1,000 meters is not necessarily the optimum. We may go a little deeper, we may go a little shallower depending on the conditions. But in general, this is what we have, where we have warm water on the surface and deep cold water. Simple Rankine cycle. Our cycle is more complex than this, but it is what we call a tapered heat source. That means the heat source changes temperature. And in this case, the heat source and the heat sink both change temperature. So this is a difficult situation. We have to work with heat exchangers, as you've all talked about. And we're accustomed to doing that. We built the first hot water geothermal power plant, the first commercial plant in the world some years ago, and it's not an easy problem. This is our cycle, or the simple cycle. Warm water heats the boiler, cold water through the cold water pipe condenses the fluid. We are using propylene. We are not using ammonia in our cycle. Again, it's a more complex cycle than what I'm showing here. Nevertheless, it is a simple Rankine cycle. The structure that we have come up with, now remember, I've been working on this longer than anybody in this room, is a floating, call it a semi-submersible, call it a spar. It's deep. At the surface, right in, is where the warm water is pulled in. It's skimmed off the top. We want the top surface layer because it's the warmest. Warm water, can you hear me? Warm water goes in and comes down to the boilers that are deep. These are approximately 120 meters deep. Here are the boilers. Cold water comes up the cold water pipe into the condensers. Now notice, so here's all the heat exchangers here and here. The effluent from the heat exchangers, the warmed cold water goes out here. The cooled warm water comes out here. They merge, and this is, when they merge, they're about at the temperature level that is associated with the layer in this mixed layer. So we're not disturbing that layer. It also prevents recirculation of warm water back to the surface. So it is a preferred method of flowing the water through a floating plant. The cold water pipe, of course, is a long pipe. You might see it over to the right. Is a long pipe suspended. We do not use a gimbal. It is suspended flexibly. The entire structure in the water is well beneath the water. The only parts above the water are possibly the crane and helicopter deck, but all the working system, here are the turbines, the pumps are in the pipes, and the turbine section and valve sections are in this section around the condensers. So basically all the machinery is well below the surface of the ocean. In particular, we're here in Brazil, and as other people have noted, when you look at Fernando de Noronha and the East Coast, you have wonderful conditions for warm and cold water. Now, I realize that I'm talking about a 25 megawatt plant. There are various reasons for that. So it's a little large for the island situation here. It's not too large for the main coast of Brazil. But you have ideal temperature conditions in this area, and you have high diesel prices. Now I'm going to give you some tables. You can take pictures of these. You can look at them closely. But this is the data on this plant. So basically it's conditions of 26, 27 to 4 degrees Celsius. And you can see the water flows. Principally, you should look at these numbers, the warm water flow per net kilowatt hour and the cold water flow per net kilowatt hour, because these are the kinds of numbers we have to optimize in order to get the cost of the plant down. We're really talking about designing a plant. It is a water management problem. You can take in more water and the plant gets bigger, or you can take in less water, but managing the water flow helps determine the size of the plant. So if you look at the size and the plant weight, you get an idea of the cost of the plant, because most of this plant is in material. It's either in heat exchangers or in, of course, the pipes that bring water down to the boilers, and the cold water pipe that brings cold water up. So it is really a cost of material problem. We want the material cost, we want the size of the plant, the weight of the plant to be as small as possible. This is the cost. And this is very, very important, obviously, to make a possible plant and make the levelized cost low enough. This is based on 25 megawatts net. It's probably about 32 megawatts gross. All of the costs are listed here for the individual items: the heat exchangers, biofouling, turbo generators, the water pumps, the cold water pipe is in here, installed, and all of the individual elements add up to about 293 million US. And I have installation legal and then a $20 million contingency, which totals $325 million for a first plant. A later plant of this size, maybe a second plant, would cost less. Later plants and larger plants would cost less. Okay, how does that affect the levelized cost? Well, we figure this is on a 6% interest rate, assuming all of this money is to be borrowed. The interest payments, and of course coming on down, it works out to be a levelized cost of about 13.8 cents per kilowatt hour for a first plant, about 11 cents per kilowatt hour for a second plant. And but you can see all the itemized costs here, including, I'm putting in about $2 million a year. This is an unmanned plant, so it's remotely operated, but about $2 million per year for annual maintenance or repairs or any kind of work. This slide is important if you compare OTEC to every other kind of natural or unnatural power. And OTEC, to the left, you can see has many, many advantages. The chief advantage that OTEC has, as a number of you have pointed out, is it is base load. It runs all the time. Solar, wind, waves, current do not run all the time consistently, whereas this would run consistently. And the way we've designed our plant, I can clean a heat exchanger, and we will be cleaning heat exchangers. We can clean a heat exchanger. We can take a heat exchanger out of service and replace it while the plant is operating. I can take a turbine offline, put another turbine in its place. Everything is replaceable. Everything is spared, so it runs continuously. If you take one piece of machinery out, you can replace it quickly with a second piece of machinery, and the power may dip a little bit, but very little. But compared to all of the other forms of power, this has tremendous advantage, even compared to fossil and to nuclear, because they have conditions of outages. Now, I've looked at diesel oil prices around the world. This is a smattering. Right in here is Brazil, and you can comment on that or not, but about $3.91 a gallon, a US gallon, which equates to a production cost for electricity of about 30 cents per kilowatt hour. And what I've just shown in the earlier slide is today, on a first plant, this would produce power at about 14 cents a kilowatt hour. So right now, today, if I can build this plant, it produces cheaper electricity than what you are currently paying for with diesel-generated power. If it were to be used as a carbon reduction method on a petrogas platform or anybody's platform, if that price is applicable or acceptable or reasonable or desirable, then it could be used merely to provide power to another floating production platform. But you can get an idea when you look at these diesel oil prices around the world. You can look at almost any island around the world that lives on diesel. So this would be an advantage in any place that has deep water near it. This is the same thing, bar graph, shows that a sea solar power plant would be cheaper than all of these places, and of course there could be many more on that map. But it would be a great advantage to any of these locations. All right. This just states what I said a little earlier. If you look at the number of kilowatt hours, because the capacity factor on OTEC is about 1, so it obviously would save roughly $35 million per year based on that production level. And of course, it produces power continually. Clearly, we could add the production of hydrogen. We could do data or crypto mining with it. Of course, the CO2 reduction effect is not listed here, but could be used. Again, this is just kind of a repeat. If the price per gallon is this much any place, then these are the equivalent electricity costs. And again, showing what our design plant would be is clearly better than using diesel oil. It's the largest natural energy source, and of course can be used for all of these functions, and it is perfectly green. It's the greenest and the only base source green power source in the world. So if we use our technology, we can go forward in all of these aspects today. We have the technology. We've been working on this for over 60 years. We've worked on the pipe. We've developed our own heat exchangers, our own turbine. I have a 4 megawatt propylene turbine in our shop right now. That's us. We're in York, Pennsylvania. That's one of our plants. We do make things. We haven't sold a sea solar power plant yet. We do make other things that pay the bills, and we do sell to power companies and petrochems all over the world. So we do have other businesses. We are a private company. We are not supported by the government. Are there any questions? Good.
For the population of the LCOE, what do you consider the lifetime?
I had that on 30 years.
30 years.
30 years was on the table.
So, for instance, a cluster of 4 assets like this will cost less than one asset of 100 megawatts. A cluster of 4 of those assets will cost less than one asset of 100 megawatts?
No, if we were to build a 100 megawatt plant, the levelized cost would be less than this. 25 megawatt is not a magic number. A larger plant would cost less, but for a first plant, the cost would be higher. Remember, I had engineering costs, I've got naval architecture costs, I had a lot of contingency in that first plant. Now, is 25 megawatt the right size? No, I could make a smaller plant, but a lot of the engineering costs, the naval architecture, the testing, goes into whatever size plant that we would make. If you wanted to say I wanted to be a 100 megawatt plant, the levelized cost would be cheaper than what I'm showing here. It would be one plant.
Okay.
Good afternoon. Thank you. That was very objective. I was just wondering about the concept itself. Why to place all the machinery, like not on the sea bottom, not on the surface, in this intermediate position? And how would such a... I understood that's about 100 meters structure, but how is planned to be installed?
Okay.
Why to place in that region and how to be installed?
Yes. Okay, well, if you recognize the pressures, you will see that the pressures associated with the water are approximately the pressure, in fact, a little higher than the pressure in the heat exchangers for propylene. So the depth of the heat exchangers is such that the heat exchangers can be a very, very thin wall. We're using aluminum, we're not using titanium. And so it's a thin wall technology on the heat exchange. Leaks will be inward, that is water leaking in. I want the pressure of the water to be a little higher than the pressure of the propylene. So I can take the water out. There will be leaks. And the turbine position, there's static head penalty in the heat exchangers, there's static head penalty, you can call static head penalty of the vapor leg between the boilers and the turbines. All those things are figured in. But the fact that the machinery actually is an airspace. It's a submarine. It's a physical airspace that retains pressure. It can be manned. It's accessed. And all those parts can come out through the hole. You have to get in the details of the drawing. But the purpose for having that structure is to be very, very stable. And we're talking naval architects. We have to get detailed drawings into their hands. But this would be a very stable structure. It's even in a 100-year storm, the waves are smaller. A 100-foot wave is smaller than the depth of this plant. In fact, it's smaller than the depth where that turbine room is. So there has to be a location of the proper ballast, proper flotation, so that the center of buoyancy and the center of gravity are the right place. The pipe actually comes up to near the condenser region. The pipe we're using is a pultruded fiberglass pipe. It's in sections that would be put together somewhat like the picture you saw with Lockheed. Actually, they got that idea from us. We call it a stockade pipe. It is made with pultruded fiberglass. It's made in a factory and shipped to the location on shore near where the plant would be built, and then it's put into the round sections with steel called steel flanges, and then actually lowered through the center of the platform during construction, much like a drill pipe is lowered on a floating platform, piece by piece by piece. And we figure about 100 hours to install the pipe, section by section. Now, and it would be flexibly connected. We probably will end up, again, this is naval architecture work, with the pipe itself can be self-floating. So it doesn't put any strain on the platform. The opening on the pipe, of course, is a large flared opening, so that that's all part of the pipe system. We expect, and I have the cable cost in there as well. So the cable is attached probably to the pipe as it extends from the platform down to make its catenary to shore. The, let's see, what have I missed? Have I missed anything there?
Jim, I'm going to cut you off. We're out of time. We're out of time. So any further questions or discussions, please take on. We do have one more presentation in the session. We're going to take a short break, come back, and then do that. So we're going to have a short break. Again, we have coffee and some snacks, I guess, in the back room again. And then we're going to come back in about 10 minutes for the last session. And so please come join us again. We'll call you back. Please start heading back. We're going to start in just another minute and a half. Okay, our next and final of the session 6 technology is structural evaluation of process components for Kavarati's ocean thermal energy conversion plant by Analuka Majumdar, a mechanical engineer and scientist D at the National Institute of Ocean Technology. It's a video we'll play now.
Hey everyone, my name is Anulekha Majumdar and I work as a scientist in the National Institute of Ocean Technology. I'm going to present my work on the structural evaluation of some of the key components that will be used for Kavarati's ocean thermal energy conversion plant. This work is carried out in the Energy and Freshwater Group at the National Institute of Ocean Technology and is being funded by the Ministry of Earth Sciences. I'll be sharing my screen. I'll switch off the camera for better bandwidth. So as we all know that ocean thermal energy conversion leverages the natural temperature gradient between warm surface seawater and cold deep sea water. This temperature difference ranging between 20 to 22 degrees centigrade is used to generate potable water and power. Our study here revolves mostly around the structural integrity of the critical components. Here you can see the thermal gradient that is available around India, and we work around at around 20 to 22 degree centigrade difference, temperature difference. Currently, India has already put up 6 desalination plants that are based on low temperature thermal desalination plants. These are offshoots of the ocean thermal energy conversion process, but they need a lower temperature difference compared to OTEC process. Right now, these plants are powered by diesel generators. So our aim is to displace the use of the diesel generators by making the plants self-sustainable using OTEC. So we are attempting to power the new desalination plant using open cycle OTEC process, which will reduce the carbon footprint and as well as improve the air quality as well. So why structural analysis? While most of us focus on the process part of the OTEC system, structural integrity is equally critical. These components operate in extreme conditions such as vacuum and external pressure, and sometimes drastic environmental conditions such as earthquakes. So failure to assess these the adequacy of the components can result in issues like implosion, or buckling of the legs of these supporting structures, or corrosion of the material, or degradation. And if we take a lot of cushion and we design, it will increase the cost of the plant by huge margin. And as we all know, at this point of time, OTEC is a bit, it's not economically viable yet. So this plays a very important role to bring down the economics as well. One of the our primary aim in this work, as I said, is to understand the structural integrity, how to make it strong and optimize the structure as well. So we have evaluated the condenser, flash chamber, as well as the turbine components for these plants. And we have understood the stress and the deformation of the plant, as well as buckling and vibrational behavior of some of the components. Our aim was to keep the factor of safety at more than 1.5 at any point of time during operation or during failure. So this is one of the components. This is a shell and tube condenser. On the left, you can see the initial model that was obtained after the baseline calculations from ASME boiler and pressure vessel code, section 8, division 1. So we basically get the one standard design from these these standards, and after that we modify the design using any commercial software. Here we have used ANSYS, and on the right hand side you can see how it was modified. So our aim, as I said, is to check the substructural integrity of the low pressure vessel as well as the turbine, which will be used in this OTEC system, and it is done during the operation, testing, and for any other conditions. So this is the methodology that is followed. First, do the baseline calculations for the pressure vessels. We use ASME codes, and for the turbines we use mainline design codes, design calculations. And after that, after getting an initial design, we make the solid model using any geometry modeling software. Here we have used Autodesk Inventor, as well as we have the geometry modeler of ANSYS commercial software. After getting the model, we import it into the structural module of the commercial software ANSYS, and we assign the material data. After assigning the material data, we go for the meshing, which is a key part of the finite element analysis. We assign the loading and the boundary condition, and we check for the, we carry out the structural analysis. Here we check whether the stress that is obtained is lesser than the allowable stress. Here the allowable stress is the yield stress of the material. If the allowable stress is lesser than the actual stress which we are getting after carrying out the finite element analysis, we have to modify the geometry again, where we are getting higher stresses, and carry out the steps again. If it is lesser, if the actual stress is lesser than the allowable, we go for the buckling and the modal analysis. And if we find that the analysis is safe, we stop. So as I said, we have made the 3D geometry and the mesh. This is the mesh. The shell and the saddle, these are the different components of the condenser. So this is the overall dimension of the condenser. As you can see, it is quite a long condenser. It's about 9 meters long and 2 meters of diameter. And empty weight is around 20 tons, but the fully flooded weight can go up to 55 tons. We have used SS316L material, which is high in corrosion resistance, which has high corrosion resistance. This ensures that the component meets the operational demands, and we have carried out quite a few load cases. One of them is when we have only atmospheric pressure and wind load acting outside while maintaining vacuum inside the pressure vessel. Second is the operating condition where atmospheric pressure and wind are acting outside, but the water boxes are filled with water and the tubes inside will also be filled with water. One is the fully flooded condition where the inside component will be fully flooded with water and atmospheric pressure and wind load will act from outside. This is done in case if the plant experiences any malfunction, and such cases happen. We also carried out cases for seismic load in case there was any seismic load, as according to IS 1893, it lies in this plant location lies in zone 3. So we have to carry out seismic analysis as well. So from the seismic analysis, loads were obtained, and these loads were applied on the this component, flash chamber and condenser. And hydro test is performed for any pressure vessel to check the integrity of the welds. So in hydro test condition, what is done is the area inside it is filled with water, and 1.5 times of the pressure extra is applied inside. So here 1.5 bar gauge pressure is also applied over the fully flooded condition. And following this, eigenvalue buckling analysis and modal analysis was carried out. I'll just discuss the results. So this is the atmospheric pressure and wind load case acting outside and vacuum inside. This is how we apply the boundary conditions. The red one shows the pressure that is applied. The standard Earth gravity considers the weight of the components. Here the weight of the tubes were modeled as a distributed weight inside. And a fixity was given at the locations where it will be supported. These are the results. We got about 77 megapascal at the nozzle outlet, and the maximum deformation was obtained at around 2 mm, as you can see in the picture below, showing the red contours. This is for the second case where the operating condition is shown, and inside the water boxes and the at extreme two sides are filled with water, and the water weight inside is also considered inside the tubes. So in this case we were getting around 88 megapascal, and maximum deformation was around 2.4 mm. So for the fully flooded condition, inside hydrostatic pressure was taken to consider the water. Other than that, atmospheric pressure and wind loads are also considered, and the maximum stress of about 73 megapascal was obtained around the stiffener ring, which is connected to the nozzle, vapor inlet nozzle, and maximum deformation was obtained at around 1.82 mm. This is for the seismic condition. Here we have put the seismic load on one side of the pressure vessel, and other than that, atmospheric pressure was considered and weight was considered. And we were getting around 89 megapascal of the stress, 1 Mises stress. And for the hydro test, we were getting a maximum stress of around 152 megapascal. This was obtained near the saddle. So after seeing that for the SS316L material, the allowable yield stress is 170 megapascal, and for all the cases we obtained a stress value lesser than the allowable limit. So we went ahead and did the eigenvalue buckling analysis, and buckling factor we obtained was 18 for the first mode. Generally, this buckling analysis, this buckling factor should be more than 1. If it is less than 1, means the material is buckling. So in this case, it is safer. We also carried out modal analysis for the device to check whether the frequency of the condenser is matching the frequency of the building to ensure there is no resonance condition. So this is the summary of the condenser. Similarly, the flash chamber model was also analyzed for different conditions, such as mentioned in for the condenser. And as you can see, this also it was a huge flash chamber. It is a length of 7 meters with a diameter of 4 meters. In this case, however, the leg supports are considered to be of mild steel. And these are the load cases that were carried out. And similarly, boundary conditions and load conditions were applied on the flash chamber. This is the flash chamber model and how we are applying the loads. So these are the various results for the flash chamber. And Here also we obtained a maximum stress of 154 megapascal for the hydro test, and other than that we were getting lesser than 100 megapascal for all the other cases, around 100 and less than 100 megapascal. And the buckling factor we got the first for the first mode was 14. So it was seen that all the stresses were within the limit. So one of the critical components in the plant is the turbine. And since the turbine rotor is subjected to low pressure and it rotates at a very high speed of 3000 RPM, so we need to check whether the turbine will run smoothly and whether there is any damage to the turbine blade or when any stress concentrations are there. And generally, we consider we model it according to the last stage low pressure conventional turbine, and we follow API 611 standards for that. After obtaining this CFD, from the CFD analysis, we obtain the profile of the turbine, and using that we create a 3D model for the turbine blade. Here the analysis was carried out for the single turbine rotor blade as well as for the complete rotor. On the left you can see how the hub looks and how the single turbine blade looks. The pressure values were obtained from the CFD analysis, and design speed of 3800 RPM was considered. Fixity was provided on the sides of the supporting roots. And the material that we used is a very high quality steel, a high alloy martensitic steel, X20CR13, which is having a very high amount of chromium, that is for higher mechanical strength. It also has higher corrosion resistance, which is required for these kind of marine kind of applications. So this is how the complete blade looks after this manufacturing. It will look like this, and this is how it is. It was modeled in AutoCAD Inventor, Autodesk Inventor, and this is the mesh generated in ANSYS, commercial software ANSYS. And for the condition mentioned in the left hand side, that the pressure and the rotational velocities of 3800 RPM, maximum stress we obtained was 329 megapascal. For the material X20CR13, the allowable limit is 500 megapascal. So this value is well within the limit. After carrying out the stress analysis, we also carried out modal analysis and pre-stress modal analysis. This was carried out to find the natural frequency of the turbine and to find the critical speed and the shape, both shapes as well. It helps to understand whether more pre-stress analysis was carried out to understand how the stress stiffening affects the critical speed, and whether according to API 611, the critical speed, first critical speed should be beyond 120% of the maximum continuous speed. So in general, it is a norm that the critical speed should be beyond 25% of the working speed of any turbine. And in case if it is falling within the operational speed, it should be passed very quickly so that the turbine blades don't get damaged. So these are the critical two we carried out this critical speed analysis, and for the speeds up to 12,000 RPM, and we obtained the first critical speed at 5,277 RPM, and the second one at 6,883. And both of them lie beyond the range of 120% of the maximum operating speed. So basically, I would like to say in conclusion is that all the components which are being used in this plant were found to be structurally sound under the evaluated load conditions. The design adhered to the ASME safety standards with factors of safety above 1.5 in most cases. Only in cases for hydro test, it was found to be 1.1 times of the allowable stress, According to ASME B31.4, allowable hoop stress can be within 1.9 times of the yield stress for piping systems when performing hydro test. So, and even the turbine was safe, and we got a factor of safety of around 1.5, and the critical speed was also beyond 120% of the maximum continuous speed. This ensures that the OTEC plant can operate efficiently and safely over its intended lifespan. Thank you.
Six, technology. We're going to go straight into session 7, which is offshore research. Our first speaker is speaking on OTEC-powered green energy hub for cost-effective long subsea tieback. The speaker will be Peter Simpson from H2. 2H, sorry, yeah. Please give yourself a little bit more of an introduction as well.
Hello. Good afternoon. My name is Pete Simpson. This is a presentation in conjunction with Global OTEC. They presented yesterday as well. But we have a partnership with them for this green energy hub that I'll present today. So my name is Pete Simpson, as I mentioned. I'm the director of 2H Offshore here in Brazil. I'm from the UK originally. I studied mechanical engineering in Cardiff. And I came to Brazil for 6 months in 2005 and somehow forgot to go back. It happened. So 2H is a consultant engineering company. We specialize in engineering for subsea systems in the offshore energy market. Historically, we started with the design of riser systems. So these are the pipes that take oil from the bottom of the sea to the top of the sea. And that extended into foundations, platforms, drilling systems, all kinds of technologies that are required in the renewables space as well. That need cables, foundations, structures, intake risers. And so there's a lot of crossover in the technology between what's needed for oil and gas and what's needed for renewables as well, at least in the subsea infrastructure. So as Joel mentioned yesterday, the oil and gas companies aren't the bad guys. There's a lot of synergy, and we need to work together to make a lot of this renewable future happen. So we've been doing that. We've been working on a number of OTEC projects already, or studies looking at intake water pipe routing. So from a given point, there's a number of routes down to 700 meters or 800 meters to get to the cold water. You see in this image on the left, the seabed is not always completely flat. There's quite a lot of ridges and valleys that need to be traversed, and the pipe needs to be installed in a safe way where the ground is stable and it's not going to have any sliding effects. And you need to install the pipe using an installation vessel without overstressing the pipe. So plastic pipes have some flexibility, but not that much. You need to be careful in the installation process to make sure that the pipe is flooded in a controlled manner. We've also been looking at seawater intake risers. So this is a technology of bringing in cold water from the very deep levels of the sea. So very cold water coming into the FPSO to cool the processes on the FPSO. So it's not OTEC specifically, but it's using a lot of technology, the intake pipe technology that OTEC requires. So talking specifically about subsea tiebacks, I'm guessing a lot of you are not from an oil and gas background. So an FPSO, as mentioned yesterday, it's basically a floating oil refinery that sits above an oil field. We don't need to go into too much of the details, but basically it sits above the field, and there are wells, subsea wells, bringing oil back to the FPSO, and water being injected back into other wells to maintain the pressure in the reservoir. And so what often happens, to the next slide, geologists may find some more oil somewhere slightly away from the original field, but there's another pocket which is kind of just in reach. It's not close, but it's also not far enough away to require putting an entire new FPSO and field in place. So that has the concept of a tieback. So this is additional lines tying this oil deposit back to the FPSO without having to put all the additional infrastructure of a new field in place. But there's limitations to how you can do that, because the longer you make that pipe, there's more resistance to the flow, more friction. The temperature, the hot oil is losing temperature every kilometer it goes. It becomes thicker. You can have waxes and hydrates form in the oil. The flow rate drops off. And so generally for long distances, you need mitigation measures by chemical injection, pumps, compressors, water injection wells to maintain the pressure. And all of that has a cost associated to it. So you just get to a point where technically it may be feasible, but economically it just doesn't make any sense because you just need to have so much infrastructure. And then additionally to that, the FPSO was probably never designed to accept these new wells. They're a new thing, and as you saw the picture at the start, there's not much space for additional infrastructure and power systems on the FPSO. How do I go back? So there's a number of concepts that have been proposed to remove some of that infrastructure from the FPSO, have floating buoys above these additional tieback wells, providing energy and injection. This one here, for example, was being looked at by Petronas, has a wind turbine, which is fine if it's windy, but as you know, it's not always windy. You need a constant source of energy, and you're all here at an OTEC conference, so you know what's coming next, and I've shown it already as well. So, come on. We have the OTEC cycle that you're aware of, and you probably almost certainly know more about it than I do. But from my point of view, as a subsea engineer, more interested in what's going on below the waterline, what we can do is put that system on a barge. So these are cheap vessels that are readily available. We can use that energy to run pumps and compressors on the seabed, run flexible lines doing chemical injection into the well, and the intake risers that I've mentioned previously, pulling in the cold water. So, although it's still at the sort of a concept stage, it's not, doesn't exist in reality yet. It's not a stretch technologically beyond what we can do already. Well, most of this already exists. It's just a case of packaging it all together and using it for long subsea tiebacks. So going back to the water intake riser, we've been looking at intake lines over a number of years now, mainly for FPSO seawater intake cooling systems, looking at different materials, and as you go deeper, you need to start using lighter materials. There's other effects that need to be considered in terms of creep and fatigue and towing, but it's a maturing technology in the very deep waters. In the shallow waters, it's mature already, but in deeper waters, it's still in the process. So the Green Energy Hub is kind of like I mentioned, it's a global OTEC concept. 2H are partners doing the subsea engineering together with KBR. We have Agro Piping Systems and Energias also involved in the group. And so basically it looks something like this, a floating barge, a cheap unmanned system, and this would sit above the wells, providing energy, chemical injection, and removing those demands from the FPSO to make the system more economically viable. This is just a quick video put together showing what the system looks like in practice. Bringing in water, and this barge sits above the tieback wells. So, as we all know, OTEC systems are very expensive, and it still needs to make financial sense. So we've done some studies here based on an asset in Brazil. We know the Brazilian market very well. We know flow lines. We know the costs of doing OTEC. And we did a study looking at how long does that flow line have to be before it makes economic sense. So the red line here shows the cost of flow lines of increasing length. And as you get longer, obviously, it gets more expensive. With the global OTEC system, you have less costs because you have less requirement for umbilicals and the length of umbilical, the injection lines, but you have the upfront capital cost of installing the barge and buying the system. So for very short pipes, it's cheaper just to make a standard tieback. But when you get to about 27 miles, which I think is 43 kilometers, then you start to get to a break-even point where having an OTEC system starts to make sense. Obviously, for very long lines, it's still really expensive. But there's kind of a sweet spot around here where potentially it makes economic sense to use an OTEC system to power those tieback wells rather than just putting in additional infrastructure. So this is the concept. It's a facilitator for long subsea tieback wells. Because you're making something economically viable, a lot of the issues with cost regarding OTEC kind of go away. It's expensive, but you're facilitating producing more oil and making more money. So a lot of those issues go away. It allows additional production without additional infrastructure on the FPSO. And it's not for everywhere. Obviously, you've got to be in a tropical region with deep water. It's not going to work in the North Sea. It's for those marginal cases where a few additional wells can be connected back to the FPSO. So it's case by case, but we see that this is a viable technology for facilitating long sea tiebacks where you've got maybe small operators looking at just a bit of additional production. So it's got a design life of 25 years. The production system is quite modest. It's kind of 2 megawatts OTEC system with a 3 megawatt genset for peak production. So it's a total of 5, but two of that coming from OTEC. And it can store up to 6 months of chemical injection fluids before they need to be topped up again for continued use. So that's my presentation. Whoops. Finished a bit earlier.
Okay. Thank you very much. Any questions? Sure. Joel?
Thank you very much for the presentation. I was wondering, I don't know if I missed, but what is the sea condition where you can operate? Because it's a barge, so I was thinking that for instance, for some places in Brazil, you may have high motions. So
yes. Yeah, well, the barge concept is mainly because it's cheap. That's the cheapest solution. But the hull can be any shape, really. It could be an old tanker, for example, or a semi-submersible. It's just the barge is the cheapest configuration to use. We've also looked, we had some comments from an operator that having an unmanned system in Brazil can have issues with fishermen climbing on it and
stealing it,
doing things they shouldn't be doing. So there is also another concept which is like a closed buoy type shape, which is totally enclosed. Or you could have people on it, but the base system is just the barge and the manned thing. But the shape of the hull and what kind of hull you want to use it's just a platform for the OTEC system, really. So yeah,
okay,
that would need to be studied, obviously.
Okay. Well, thank you, Pete. That was very informative. I was just wondering because your sensitive case will be, very impacted in terms of what you consider over there. What was the range of power that you consider for that case? And if you can tell us, the oil flow associated with this tieback for that graph.
Yeah, I don't have that number on the top of my head. But it depends, case by case, depends on how much oil you're going to produce, the flow rates, where you are in the world. But this was specifically for Brazil. The flow rate, I don't know off the top of my head, but I can give you that later. If you come back to me, I've got all the details on that calculation.
The power level associated with the barge is designed for...
I believe it was this 2 megawatt OTEC barge. Yeah.
Okay, good presentation, thank you. So the Agru XXL piping systems, the simulation that you showed, all right, so I could see that is, of course, the simulation is moving, dynamic. What is the largest diameter that they have experience done? Any real work or project here?
So we've looked at 1.2 meters, 1.8 meters. Yeah, 1.8 meters diameter for FPSOs.
And the length, distance?
Well, it's because you're going vertically down. It's kind of 700 meters or 800 meters. So that's kind of...
I see. Okay, thank you.
Or were you mentioning the OTEC systems where you're going down over along the seabed? I think we were looking at 5 kilometers, something like that.
Okay, just another one. The Petronas, is some activities going on already or just a concept?
I think it's just a concept, yes.
All right.
Yes, just a
Got
concept
it.
stage.
Thank you.
Okay, we have 2 more presentations. One will be from yesterday. We did get the video. Unfortunately, we didn't get it in time, so we'll include that at the end. But first off, we have results of proof of concept study for enhanced ocean thermal energy conversion, (OTEC) by Roy Robinson. Please introduce yourself further and your company.
Hello, and I think everybody already heard my introduction, but if not, I'm Roy Robinson, marine engineer, MBA, been doing this for a long, long time. Been looking at offshore renewable energy and OTEC since, well, not quite as long as Mr. Anderson, but a long time. So let's get right into it. There we go. This is the cartoon version. You guys all know how OTEC works. And ours doesn't, we are still looking for the best cycle and still looking for the right combinations of fluids. That's our next step in our development. But what we've done that's different is we've moved the OTEC plant to the seabed. And instead of just using the OTEC plant with, if you bring the warm water down, that would actually make it worse than trying to bring the cold water up. You need an even bigger pipe, and it's not likely to be as warm when it gets there. Why did we go on to this? Because, as I mentioned before, the 2 things we identified that have been a problem with OTEC were the cost of that big pipe and the low thermal efficiency. And no matter how good your cycle is or how good your heat exchangers are, using it in this system will make it better because you end up with a much higher driving potential. We've only modeled it, what you're going to see, we've modeled it with CO2 for the heat transfer fluid. So we take the heat transfer fluid, bring it up to the surface, it picks up the heat from the ocean, comes out at the normal same temperature that the ammonia would if it was getting heated up. But it's a dense phase, in this case CO2, and then it goes down 1,000 meters. The Joule-Thomson effects raise that temperature at 1,000 meters to about 50 degrees. If it's 2,000 meters, it goes to 70. That gives you a much higher Carnot efficiency. You can go anywhere up to 30% if you really get pushing it. That's theoretical. Real life, like right now, I think we're at about 22, thereabouts. The other thing this does is the top sides that used to be huge, which means for like putting it on an FPSO, they want to power a FPSO or an oil and gas platform with OTEC, you'd have to build a separate facility beside it. With this system, you don't have to. The space claim on the surface for about the same power is almost identical to what they currently use with the gas turbines. So they can put this on there, and it does produce enough energy. Also, the platform, if I wanted to build a small platform, I could. I'll get into later why I wouldn't do that, but I could. And all of the technology that we're talking about here exists. It's proven, it's been built, it's been used in the applications that they have here, with the exception of subsea, they only have compressors, not turbines, but it's not a hard thing to get to. Which one is it, this one? Hello, my turn. This just because, I mean, it's about where we are. In 2023, Shell gave us some money to do a proof of concept. You guys, if anybody was at the last the OTEC Symposium in Houston last year, I presented our preliminary studies that we'd done with hand calculations and a few others. Shell gave us some money to do a proof of concept, and that's what we're talking about here. We ran it with a high-end software, and it works. Okay, now you got everything you need. No, sorry. For those of you who like numbers and geek stuff, we did it by, first we calibrated the model using the Lockheed. Now Lockheed and the DOE spent a lot of money from about 2010 to 2012 revisiting OTEC. And they've produced probably the most comprehensive design basis for an OTEC system. It's not one I would necessarily build. But I wanted to compare it to something that I could present to Shell and say, hey, this is what we did. So the first thing we did was copy the exact system that they were using and run it through our model and make sure that we had the differences within an acceptable range. And it's a little bit different, but that's not to be unexpected. If you look between the various Lockheed reports, the variation's bigger than that. That's the actual model. I'm not going to sit here and point to each one and tell you what the numbers are. But the point being, the main one that matters is that the Lockheed system that this was modeling kicks out 12.5 to 12.7 megawatts for the same water temperature. Just on a first pass and with no optimization, we got to 22.7. Our parasitic load is higher because of the heat pump, but our energy out is so much higher that we still make more power. And more importantly, we do it at a lower cost. We do want to continue on the CO2 right now. There's a reason why we're limited to 1,000 meters, why I moved it up from 1,000 from 2. There's some energy losses involved in going back up that I'm pretty sure we can fix, but right now we haven't. Oop. Now my turn. Red one. Hello. Is it the red button to go back, I assume? Top left. Got it. There we go. Nope. That's the one to go forward, yes. I was trying to go back, I thought. There we go. Either way. Yeah. The EOTEC, we're calling it ETEC instead of EOTEC, and there's lots of reasons for that I won't go into. It will always outperform an OTEC system in the same waters. There's no way it can't. In the design temperature that we modeled, as I mentioned, it's 22.6 versus 12.7. For those of you who know the Lockheed report this is based on, they say a 100 megawatt plant. That's because they have 8 of what they call remoras around. They were never going to build one bigger than a 12.7. And at the 32 surface water case, which we didn't run, 27 megawatts. All with the same system. So that's a quick summary of what it does, and this is what happens by moving that to the seabed, right? It's a combination of oil and gas technology that exists, basic heat pump concepts, and a little bit of subsea factory, which is also from oil and gas. Very small. Most equipment's on the seafloor. It also makes it almost impervious to tropical storms. All we have on the top, on the surface, is a heat exchanger and a big warm water pump. That's it. Everything else is going down. And the size of those 2 pipes that we have in this model were 1.2 meters in diameter. Okay, so that's large, but certainly within the realm of current technology. And we don't have to make it that big. We could make them a little bit smaller if that became a problem. Ammonia, the safety risks from using ammonia as your working fluid, if it turns out to be the best one, we have higher temperature now, so it may not be. It's totally safe. There's a little bit of environmental damage if it leaks out, but as it turns out, the external pressure is higher than the internal, so if any leaks, it's going to come in. And even if ammonia leaks out in the water, it'll only be dangerous from about here to where Ben's sitting, because it's very affinity to the water, and water is how you make it safe. Anything else? Yep, everything else is. These are the next steps that we need to do, and I'm not going to read through those in great detail. But you've got the heat pump cycle, because we know that we aren't at the most efficient cycle. We just modeled the one that Lockheed had in there because we want to replicate the results and see how it compared. I'm sure a lot of you out there have better heat cycles and better use of that heat that I can provide you. We're more than happy to talk to anybody about doing that. And then also the heat pump cycle with the heat pump fluid. Right now we're using CO2. Now CO2 does have some very unique properties, especially in the supercritical and dense phase that we're looking at. But I'm fairly convinced it'll be a mixed gas solution. And that'll allow me to get to the 2,000 meter depth. And in that instance, I then get to 70 degrees instead of 50. Those are degrees C, I should say. But it's to optimize the 2 fluids and the configuration. Right? Pretty straightforward. Don't get me wrong. If I needed to, I could go build one like we did and it would work and still make money. But before I do that, I want to optimize it. Just a couple of uses you could do for this. Sorry for the kind of bad graphics here, but because it's got such a small space claim, you can use it, as I said, on things like floating LNG. About 10% of the gas that goes into a floating LNG plant is used to power the LNG system. If you're using these, that's 10% more product you're producing. Plus you're doing it at a lower carbon load. And there's no technical limit about how many of those you could put on, but probably anywhere from 4 to 8 would be kind of a limit, just because you need to spread them out on the seabed. You guys have seen a lot of this about tiebacks. In fact, Captain Tuish was just mentioning that, using the tiebacks. You can also, besides powering the platform, once the platform's done, I mentioned this earlier, there's nothing stopping you from putting a bunch of them on there and turning it into a hydrogen plant or green fuel or anything else you want to do. You can repurpose offshore assets. Data centers was also mentioned today. Even though we would be 100% reliable on power, data centers will not consider a system that doesn't have a backup. So you make some hydrogen. If you're going to make hydrogen offshore, you put it on the seabed and it comes off already pressurized, because pressurizing hydrogen is both expensive and kind of difficult. But if you produce it on the seabed at 1,000 meters, it comes off at 100 bar. You're all set to go. Because you're storing it subsea, you can store it and the oxygen, which means when you put it back into your fuel cell for pulling power, you get a very, very high efficiency. And as somebody was, I think it was the one from Mexico mentioned, as far as the cooling aspects, we can pick up the waste heat. And on top of that, the CO2 can act as your fire suppression system because it doesn't hurt the electronics. SIDS, you guys have heard about the SIDS, the small island developing states. One of our plants could power just about any one of them. I would actually provide them with extra power because if they have extra power, they can effectively create e-fuel so they go from being dirty energy importers to being clean energy exporters. Gives them a whole new revenue stream, right? Besides all the other benefits they're going to get by having all this excess power and things they can do with it, that becomes a revenue source for these countries that don't really have good income sources. I'm going to diverge a little bit from OTEC. I mentioned this before. This is the first thing I noticed when I went into renewables again in 2016. And I say again because I've always had my eye on this. These guys don't talk to each other. Right now we're at this meeting. And I'm helping write the standards for that one and this one. Right? They're all one industry. You're all part of the renewable energy industry. If you're going to build a floating system, onshore is different, but if you build a floating system, you want to put as much of that on there as you can, as long as it makes you money. It has to be profitable. If you have to be subsidized long term, not talking about for your prototype, you have to be subsidized long term, it's not the answer. This slide, one of the guys I was talking to complained. He says, why are the oil and gas companies pulling out of oil and gas and not going into floating wind like they promised? I said, this is why. These are based on the latest numbers from NREL. So, on a revenue basis, there's one of the later oil and gas projects in the Gulf of Mexico, about $9 million, making a certain amount of money. To equal it, I'd need 618 of the biggest floating wind turbines there are. It would have a huge cost and a negative NPV if I'm comparing it at a reasonable. I can raise the price to a really ridiculous cost, and then I might be able to make some money, but nobody's going to buy the power. If you integrate power onto the platform, and this was our first patent, this carries wind and wave and currents and OTEC, always had OTEC in it. In this case, using that big wind tower and the rest of it to start up the first OTEC. I would probably have 4 of my units on there. It was originally designed to have one of Guy Bardot's or Value Park. This wind turbine, by the way, is another guy I know who's developing that technology. This had, in the Gulf of Mexico, where you get a capacity factor of about 25% on an average 3-bladed wind turbine, that turbine gets one of 75%. If you're in a place like Noronha, it's 100%. North of Brazil, 100%. You don't need batteries. It'll be going all the time. Want to find out why? Ask me later and I'll tell you. So if I wanted to compare those with a multi-purpose platform, it doesn't have to be mine, but that's the one I happen to have the numbers for. It would take 40 of them, which is a lot, but it's reasonable. And more importantly, it actually at least has a positive NPV at a very low electricity price. Right? It was 8 cents a kilowatt hour is what they're using for the base price. It doesn't have to be mine, but if you have OTEC, wind, wave, currents, everything else combined together, that's how it works. And that's just for the power. An example of what it does, I actually have one from Brazil, but didn't have time to dig it up. That's what the Gulf of Mexico, and this is per NREL's resource values are the same for both. This is what NREL says is the wind resource in the Gulf of Mexico. You put an integrated platform with OTEC on it in the Gulf of Mexico, that's what it looks like. And these numbers are based on your conventional OTEC. You put the ETEC on there, and the numbers will at least double. Integration. And if you make that leap, you should make the leap of I'm going to put all kinds of toys on my big platform because it's not going to change the cost of the big platform. That's where the trick is. All of these things become possible. I'm not saying to put everything here on each one, but every one of these things you can put on any of those platforms and whatever is suitable for that area. And you also look for, if I've got this waste stream, what can I do with it to do it for this one? If I'm making hydrogen, I have oxygen. If I have oxygen, I can burn a biosource, get pure CO2, I can recombine it into e-fuel. Sell it at a profit. I'm making desal and I've got brine because I'm making H2. I need to desalinate the water. Rather than just dump the brine, because it's not going to do any harm, I can pull mineral extraction easier. And like I say, I haven't quite been doing this long, Mr. Anderson, but my mother sent me this when I started the company. And this is why I do have knowledge of all of those things, plus my 25 years of building stuff for offshore oil and gas. That's something I drew when I was 10, which would be just about the same year the first time I read about OTEC in Popular Science, which was 1973. Well, that's it. Any questions? It's either good or bad, I don't know.
Okay, thank you, Roy. We'll get you any further questions or discussions, then you can have time afterwards as well. We do have one more presentation. It's from Brett Strogan, making a century in the making, OTEC technology and the precipice of commercialization. This is a video.
Good afternoon, everyone. My name is Brett Strogan. I'm the Director of Defense and Commercial Partnerships for the Ocean Thermal Energy Corporation, which is based in Pennsylvania in the United States. I'd like to give you an overview of some information that's common knowledge in this community, but also attempt to tease out some of the real barriers and timely opportunities to commercialize this promising technology. So just a quick note about the company. It was founded in Hawaii originally and then acquired by the current CEO, Jeremy Feekins, back in 2010. The team consists of OTEC and SWAC experts, general energy technology and energy policy and management experts, and project legal expertise. So the company's done quite a bit of R&D over the last 10 plus years and are excited to see a lot of other players in the space and startups, universities, and national labs advancing technologies. Our specialty at this point in this ecosystem is really in developing financeable projects. So for the last few years, we've been targeting military installations as well as some potential commercial partners in the Caribbean and Pacific. So I realize a variant of this slide has probably shown up in a half dozen other presentations at this point, but bear with me. So in remote equatorial areas where military locations and their surrounding communities, as well as small island developing states, they suffer from insecure and expensive energy and water. And at least for a lot of these, they also coincide with a heavy need for economic development opportunities. And OTEC, as most of us know, can also bring support for aquaculture, agriculture, and potentially other industrial activities like making hydrogen and ammonia during off-peak times. Just to put in perspective, though, a lot of these side streams are a pretty small fraction of the overall value of a project, but are worth mentioning as they do help resonate with different stakeholders. Just put this slide in for kicks as a reminder that a lot of these value propositions for OTEC have been touted for decades. So this is an article from Kobayashi et al. From 2001, and certainly most of these points were made in years prior to that. So the orange strip here shows the addressable market that we see, that most folks in this community have seen. So there's a strong need for stable, resilient power in many parts of the world. It's worth noting that the population is growing, demand for energy and water is growing, and also until a few years ago, I think most energy economists thought that energy intensity was declining. As our industrial processes and transportation, everything became more energy efficient. We thought energy might be actually dropping or plateauing, but it looks like energy intensity is going to just continue increasing as our society takes on more demand for data and analysis throughout the course of our lives. So we've all heard of data centers and yeah. So just to put OTEC in perspective, wanted to show that OTEC is not a panacea. It's just generally the best among a few alternative options and some of which are undesirable. So most often we compare OTEC to fossil fuel or diesel generators for these remote islands. So diesel generators are great in terms of it's being a well understood technology. There are supply chains for it. Folks know how to service engines, but we all know the environmental drawbacks, public health drawbacks, supply uncertainty if oceanic shipments interrupted, and also price volatility associated with petroleum is a concern with fossil fuels. Wind and solar are fantastic. Prices have come down, but of course, everyone in this room knows how to spell intermittent, so they are not the solution without some kind of storage, which remains very expensive. Wave and tidal are familiar to a lot of folks in this audience, have really compelling value proposition, but also have some concerns for investability, just like a lot of other new technologies. The idea of putting something that's moving in a body of water that relies on consistent movement, draws some concerns about maintainability over the long run. But certainly worth continuing to pursue. Nuclear, I'll just call out as a more well-known competitor in this space. So it's getting a lot of attention these days, both large-scale commercial reactors being resurrected and also micro-scale micro-reactors, 50 megawatts and less, being advanced by startups and national labs. So I actually coordinated a study on this topic for the Defense Science Board about 8 years ago, and advised a startup in the microreactor space for a couple of years. I think interest is there to stay, but I don't expect to see any of these really tiny reactors deployable to small islands around the world for years to come. So excited to see that technology progress, but OTEC still serves a really great value in a lot of parts of the world. So another slide to help put OTEC in perspective of other competing options, mainly renewables. So this graph was created by Dr. Langer and his team, and also the statistic. The numbers that I pulled from a graph in a different paper was also from Dr. Langer and the same team. Just pointing out that OTEC, as it scales up, we expect it to compete with utility scale power. So it'll be competitive in a lot of the world with these other options. But right now, we're on the far left side of this. We have very, very small pilot facilities shown that work well, but not the small and medium that we see here. So sprinkle some money on there. We need to get some of these first of a kind capabilities built before we actually convince investors that their money will be put to good use, that we can invest in projects that have a return. Because right now, for decades, we've been stuck at the point where, sure, there's billions of dollars of money going into energy innovation, but investors are not generally tempted, even federal government investors, to put $100 million or so into a project that is not going to be cost effective during operations. So the big challenge here is we need projects that are in the $500 million order of magnitude, where it's actually going to be worthwhile, cost effective to continue operating and maintaining for decades to come. And once we have those projects in operation, we'll have the data that is needed to convince other project investors that more of these will make sense and we can scale up over time. So tricky thing is just getting those first one or two built, and that's the problem we're solving right now. All right, so just going back to our origin, so many attendees are aware that this technology was conceived almost 150 years ago and demonstrated about 100 years ago. Point being that OTEC's been around for a while. The technology existed back in the day to enable it to work. Obviously not as efficiently as today's technology, but it's nothing like fusion that requires great technology breakthroughs. I'd argue it's effectively a big plumbing project. But it still requires education to get folks comfortable with it. Further R&D certainly helps with the techno-economics. Yeah, we're getting there. So the 70s and 80s were a time with a lot of money going into OTEC and advancement and pilot scale facilities. and I always like to point out that in 1980, the U.S. President Carter signed a bill mandating or directing the Department of Energy to enable 10 gigawatts of OTEC on the U.S. grid by 1999. So the energy experts in the Department of Energy advising Congress and the President in the late 70s thought this was was achievable to see 10 gigawatts on the U.S. grid by 99. Of course, none of that ended up coming to fruition. Also point out, shortly after that, Kobayashi and his team published an article in 2001 where they expected Japan would see 1 gigawatt of new OTEC on their grid every year in the near future. So a lot of goals have been stated that were technically achievable, but it hasn't come to fruition, which just shows that we need to continue educating folks. Another anecdote I'll share is I was at the New York City Climate Week in September, and I went to a handful of blue economy, marine energy, innovation type meetups and workshops, and I don't think I met a single person who knew how to spell OTEC. Their first thought is this like using waves, wave energy? And obviously it's not. So we need to keep educating, especially the folks that would be our cheerleaders in the blue economy innovation space. Quick summary of lessons learned from decades past. So we've seen great success in a lot of these demonstrations, going back from George Cloud in the early part of last century through the demonstrations at the Natural Energy Lab in Hawaii, some great success in Japan, Korea, and India. So the reliability of the piping system has been shown to be 99.9% in most years. We've seen the biofouling problems solved pretty well. There were certainly some lessons learned with maintaining and replacing parts in some of the early facilities, but I'd argue a lot of that has been resolved through trial and error. We've developed protocols to make sure we know how to maintain these systems in the field. The oil and gas sector certainly has developed expertise to build, own, operate, maintain systems that are in harsh marine environments. So I'd argue none of these are major deal breakers. And I'd also say that some of the sad stories about pipes being lost in the ocean that are really expensive, certainly a bummer and killed some momentum, but not a problem that's too hard to overcome going forward. So I'll also mention that I'd say that those technical barriers are all manageable. Some of the things that really did hurt projects in the past was the evolution of other competing energy technologies. So hydroelectric became available in Africa in one of the early cloud projects. I'd say photovoltaic and offshore wind have taken up a lot of the conversation in small island states. The fluctuation in energy prices certainly killed some of the momentum from President Carter's declaration in 1980. So in the 1980s was a time where just the markets made the case for OTEC not as compelling. But I'll zoom out a little more broadly. So lessons learned from like the oil and gas sector and industry in general. Permitting is really posing a challenge for energy projects, from nuclear to photovoltaics, and also transmission. So permitting meaning environmental permitting, but also stakeholder engagement part of it. So that's hurt some projects in the past where there were ancestral remains in the area which was designated to be excavated for a project. Interruption of ocean coral is a concern that we need to always be ready to address. It's limited, but it is a fact of project execution. Also mentioned that subsea cabling is a great opportunity for OTEC. So if you have a facility that looks like it would just be 10 megawatts for the local community, if you can cable it a few miles to a nearby island or other community, that can really enable us to hit the economies of scale that make the levelized cost of electricity a lot cheaper. And subsea cabling has advanced quite a bit over the last 10 or so years with the advent of offshore wind projects being really really picking up a lot of steam in the US and internationally. So there's a lot of capability, costs have come down, but unfortunately permitting is still a challenge, and the companies with the capability to install the permitting generally have a backlog for a couple of years. Last but not least, price of materials has gone up. I can't be in Washington, D.C. without complaining about inflation. So materials, labor costs have gone up. Interest rates have also been a lot higher recently than they were years ago. So new challenges to work through, but none of this is a deal breaker. Also, some positive news. There's been some great advancements on the technical side that can bring costs down and improve performance of a project. So titanium and aluminum heat exchangers, improve performance of the heat exchangers. We see cold water pipes that can now be made up to 3.5 meters that are HDPE or plastic, so resistant to biofouling, also recyclable, so it's great for circular economy metrics. Ocean platform design, or whether it's land-based or floating, the oil and gas sector has improved quite a bit in their capabilities, so we can, as another presenter speaking, we can take some lessons from that space. Pumps and turbines continue to evolve, but those technologies have been around for a very long time, so we expect those components to last for decades under routine maintenance. And last but not least, I'd say there's insights from just how project finance has been done for first-of-a-kind facilities over the last few years that are making it a little more achievable to wrap together a project where you have performance guarantees, warranties from the component and subsystem providers, insurance products like reinsurance that enable the EPC to take on the risk of the overall project under a total wrap-up insurance product. So that enables them to really guarantee the performance, that enables a project to be financeable, and where you have a 20-year, for example, power purchase agreement. So a lot of this was a refresher for many in this audience, but hope some of it was thought-provoking, hoping for success for a lot of the folks at this event, and I'd be more than willing to take questions. If you'd like to keep in touch after the conversation, after the conference, please reach out. Our website and my contact info can be found on this last slide. Thank you very much.
An update about OTEC for you. This will act as our general meeting, but then we're going to have a panel discussion with everyone. So it's our final discussion to kind of bring everything together and give everyone a little bit to share and ask final questions, make final comments. But before that, I just have a few slides to run through for you, and then we'll wrap up for the day. So slides, please. Just grab the clicker. I'm going to sit back down over here, though. So this acts as our fourth general meeting. So just a couple basic things. First, I'd like to ask Professor Ikami just to give another set of remarks for the general meeting here.
Good afternoon. So, on behalf of the OTEC executive community, I will give the opening remarks. Now, I worried every participant now tired. Yeah, but from this meeting, general meeting of the OTEC is very important, because OTEC is a platform of the biggest regarding the OTEC researcher, governor, investor. So this platform is very important to the international cooperation. So after that, please discussion how to more accelerated OTEC. So we are gathered your proposal. So we want to implement these activities. Thank you for attention.
Thank you. So just a little bit more background. So we recently had elections for the next term of our OTEC leadership. Dr. Ikiyame remained as our executive committee chair. We do have two new vice chairs that were elected just this past month, and they're joining us now here today. Dr. Joel and Dr. Satyabama are representing kind of the leadership team to drive things forward. So if you have complaints, they're the people you should go to. If you have good comments, bring them to me. Okay, thank you. The executive committee, though, is a wide range of experts from around the world. So essentially the way we run things is that anyone can join OTEC. It's an open volunteer organization. And so then to make things a little less complicated, each country or region that has more than 3 members can elect a representative. And that representative joins the executive committee. We do have 3 representatives under combined regions to represent everyone else. Because, there might be 1 or 2 people from a country, but unless they get their friends together and, put in 3 people, then we're not going to add a delegate. So there are now about 26 people total from around the country. The starred ones are our new delegates who came in over the last year or so. We have Dr. Joel for Brazil. The previous delegate actually requested to hand over to Joel because of his great work on OTEC in the country. Dr. Estela in Mexico took over after Dr. Retired. And then Dan Gruk has joined us from the UK. So what we do, so again, volunteer organization, no funding. We're just trying to bring everyone together, okay? I don't want to deal with funding, so we're not looking for funding either. But we do have a website, we have news, we have otecsymposium.com. And so that's mainly to help spread the word about what you're all doing. So we can only do as much as you help us do. The more information you share with us, the more information we'll share with everyone else. And so that's our main goal. Connect everyone together and support everyone's activities. We are still growing. We're now up to about 600 members and observers from 53 countries and regions. So this year we added Morocco, Bulgaria, and Australia to our membership. Not as official countries, but from people from those countries. And so we continue to grow. We aren't actively recruiting or doing a lot of outreach per se, but just from word of mouth, finding us on the internet, we are continuing to grow and then trying to use that to share and create this kind of critical mass of people understanding of what, not just OTEC, but all ocean thermal energy, all ocean thermal technologies are. That gets broken down into about 43% academia, 47% industry, and 10% government. So we are mostly focused as an industry. Right? We're not an academic society. We are an industry-based society, but with a strong support from the academia as well, because there is no industry OTEC yet. So until we're commercial, seems about right. Hopefully this will grow over time, and hopefully we'll support that growth. Okay, so that's it for the work. So now I'd like to open it up for all of us to kind of speak together, join together. And so we've had 2 days of discussion on technology, research, oil, gas, Brazil. How do we go forward? Everyone has different ideas, different technologies. Some of us are competitors, some of us are researchers, some of us are government, and some of us are just here for fun or because we asked you to be here. So, are there any final thoughts? Maybe someone who didn't have a chance to speak but would like to put their 2 cents in. Again, this is a community time and we're not going to take up too much time for this, but this is your last chance. Any thoughts, comments, questions, concerns?
The only comment I'll make is going back to we're all in one business. Oddly enough, one of the only places that you're going to find wind and wave and currents and tidal and OTEC is in places like the OTC, whether it's the one here or the one in Houston, the OMAE that Joel's organizing is also a good one. And for those of you who don't know the difference between those two, those are both, OMAE is highly technical, usually very math-heavy papers. OTC is a little bit less rigorous in that, but it tends to be a broader range of topics. And both of them have a very large audience, and it's not just oil and gas. The very first OTC in 1969 was ocean mining, 1/3 offshore renewable energy, and 1/3 oil and gas. So it's always been something else. Look for conferences like that to present your papers, because that's how we can grow that 533 to 5,033. The more people that work in the industry, in the offshore industry, that know about this, the more interested they are. I have put out calls for papers for the OTC, and I've been met with crickets most of the time.
Mail me.
I will.
For your events, anything that might be OTEC related, share it with me.
And
I'll
I'm on
email
the
it to our
program
600
committee, so I
members.
can help the paper get in.
So we have 600 people on our mailing list. We'll use that. We share information. We don't charge you to share information with our community. So please use us as a resource. Any other comments, questions? Yes?
Actually, it's not a question, but it's a hope that the engineers here bring their friends from environment to join here and bring new ideas too.
Great, yeah. Bring your friends, because we need not just engineers, we need the business people, we need the marketers, we need the scientists, we need the suppliers. That's one thing we've had a challenge with, I think, in OTEC as well, is getting the suppliers into the room, because they don't want to show up unless we're going to buy from them. But they have a critical impact on a lot of these cost estimates or developing projects and things like that as well. It's a good comment. Bring your friends. Okay, shifting gears a little bit. What do you want to see from OTEA? So we're an organization for you, and we're limited in what we can do, but any suggestions, thoughts, processes for us?
It's possible to include more routes in this forum beyond OTEC, like, for instance, geothermal.
We aren't closed. It's a binary power generation system, but we are focused on, specific. I mean, if there's a specific paper that would work on it, of course we could consider it. But there's other forms for geothermal.
Yeah, because I'm buying from a synergy thing, okay? Very much like what Roy says, okay? To create synergy with other routes. That's my point, okay?
Ben, what I'll do, and I can send you can put it up on the OTEA website. I have a very extensive list of all the different conferences all over the world that if anybody wants to put a paper in, they can. And the more of those that happen, the broader the audience gets for OTEC and for the synergies that he's mentioning in terms. Because like there's OTC in Asia, there's a whole lot of them all over the place. There's too many, but I can send you the ones that actually have some traction and have large audiences, and you'd get your bang for your buck. And most of them, like the OTC, if you write a paper, you get in for free. Some of them, like Oceanic, they're still going to charge you. It depends on which ones you're going to.
That's a great suggestion, and one that's actionable. Dr. Shinohara?
Okay. From OTEA, one expectation that I have here about presentation, about how to improve the community perception about OTEC, and how we can improve in each country. There are many countries as a member, more than 50, right? So how can do to improve the public perception, kids, and is it? Okay, so maybe should be interesting.
Yeah, outreach and education is an important thing. Go.
So just a perspective, this is my first time participating at the symposium. I'm of course excited for next year, but if it's like, I'm being really honest here, if it's going to be the same format, it's not really interesting if we are going to hear the same things over and over again. So I think one way of doing that, which is very simple, is putting a theme. Every year you have a theme. So you can talk about the progress of OTEC, current projects, history of OTEC. You can focus on one thing or just heat exchangers, whatever it is. And then you have the presentations that are related to that, and you focus on one question or one theme, at least like one of the days. I think that there is a way for the association to kind of incentivize also people to think, okay, let's focus on this thing right now, and then make discussions about it. It's easier if you focus the attention on one topic or two topics than just like have everything spread. For example, I would say like in the first day we focused a lot in Brazil, which was interesting, but sometimes it gets too repetitive. And again, I'm saying this very honest, also from a communications perspective. If we want more people in the room next year, we need to change the approach a little bit and also modernize the way we communicate. So maybe the format of 20-minute presentation isn't the best. We can think about panels discussions. We can think of interactive sections. We can have questions from the audience. There are like lots of different ways that are not expensive. They're creative, and they can work to kind of also modernize the way we communicate OTEC.
To that point for a second. So the OTEC Symposium, opposed to just OTEA, the OTEC Symposium, OTEA's job is to select the local host. That's it. Then the local host takes over. So I'm here sitting up as a moderator, but I didn't run this event. So it's up to each local host, once selected, to make those decisions and that programming it. And so that can be done. It requires a little bit of consensus, because the reason why we had the program the way it was is those were the people who gave us the abstracts. And so that was the way it was developed. We gave 20 minutes because I knew we would go over if we didn't. From my last visit to Brazil. That's more of a cultural thing, I think, for this perspective. So that can be adjusted, and as you said, there's some better things we can do. Ideally, tying into a larger event like OTC. We did that last year. We tried to. We didn't actually connect with them, but it was around the same timing. Right. Ideally, we want to be, part of a bigger event to attract those, people in. The purpose of this event is to highlight OTEC to a specific country or community. So if we bring in people who have never heard about OTEC to hear about experts from around the world with differing perspectives, then it's done something unique and useful. Can we do it better? Yes, we're going to get better, and your advice and ideas will help us get better in the future as well. So, we're not an academic society. If we have more options to choose from, we can be more selective as well. And so we'll have to do a little bit more of that in the future as well. But yes, thank you for your comment.
Yes, I think I agree with, sorry, Jordan. Okay. Yes, I think that when I first met these OTEC symposiums back in 2018, I wasn't working at OTEC at all. I mean, that was my first impression that I believe OTEC symposiums have, it works for the people that are already in the OTEA and the OTEC world, but it's difficult coming from outside the original group. I don't know if I explain myself, to join and to feel part of the symposium or the OTEA, right? I think that, of course, you would need a lot of volunteering for helping, not just to make, it is not just to make OTEA and symposiums fun, but I think that it would be good. It would be great if we can also, especially now that a lot of companies, industry, people that were not aware of OTEC, that are getting close to OTEC, to make them feel that they can participate more. Maybe just have some. Back in Mexico, we used to have not just the presentations and the questions, but also like we call them mesas, which is you got a group of persons interested in something specific, and then you make them to work, discuss, like a group of them, like here, exchangers, for example, and you give them like 40 minutes, and they will discuss everything about it, and you don't make everyone to be involved exactly, specifically in that discussion. They can know about it because of the presentation, but I think it would be great if people interested in some specific aspects of OTEC can be gathered at some point, maybe the breaks or maybe some activities where they can just discuss specifically for that. And of course, if some of us who are not actually in the OTEA, you know, from Mexico, I believe it's Dr. Estela. I miss like the propositions for being part of the chamber, but we would volunteer to make, I mean, what we are trying to improve in the symposiums or the OTEA work, or just as volunteer to help with all the work you must have beside all the OTEC projects you are running. I think we are, I would sign up for that. I would just need to know if I have to go with Dr. Estela, who is from Mexico, or maybe directly, you know, with you.
Okay, we're gonna, okay, in the back here.
I just want to share something. Listen all the presentations, especially in my presentation, and see other works. I think about something to share with the community to make the more precise observations about the resource of OTEC, the thermal difference. Because we talk about of onshore systems, we talk about of offshore systems. But when we a continental layer, we have Brazil, we have continental, we have the internal shelf, and have offshore places. But we have some special battery future we don't investigate, but thinking in tomorrow, I think we need to investigate the slope of shelf, the inclination, the transition of the internal shelf from the offshore. This region have someone, if you was investigate, we can sure observe the difference temperature get higher because the surface flow or the seabed came to the up of the internal shelf with the slope. Because that I think about this in the symposium, we think a new frontier for see the behavior of the difference temperature, the slope of the continental shelf of the countries. We see that something we don't put the focus in that, but it's something all the countries who participate of the OTEA have to see the behavior of the slope of the internal shelf with the offshore. I say to you, you have onshore observations with Okinawa, Hawaii, but we need to observe a third possibility, not offshore or onshore. We have the slope of the transition of offshore and onshore. This is very a new observation of behavior of the temperature. I want to research that, because that I share with you, for all you did this research in your countries. It is that I want to know.
Yeah, research it, publish it, and bring it next year. Okay, any other?
I think you said pretty much all you need to say.
Okay, so we're going to continue trying to do better and do well, but we are coming to a close, so I'm going to ask the chair of the local committee, Joel, to give the final remarks.
Okay, thank you, Benjamin. Actually, before we do the closing, I have two announcements. The first one is about the van that will take you people to the visits tomorrow. The van, of course, we have to take into account the Brazilian culture, but they are supposed to be here at 9 a.m. tomorrow in front of the hotel, on the other side of the street. And our researcher, Rodrigo, please stand up, please. He will be waiting for you in there, okay? Maybe he can use some red. But anyway, maybe red to blue also. So please look for Rodrigo, and he will lead you to the van. Actually, he'll try to lead the van to our university. It's a small island close to the airport. It's an independent island from the airport. And the idea is that we're going to first go to the ocean basin, Oceano. We have a small presentation in there. You will be able to look and touch the Lockheed Martin model that we tested about 10 years ago. I never remember if it's 10 or 15 years. Anyway, something like more than 10 years ago. I used to have a hair at the time. 12, thank you. And also they are going to put the CWP model, just for you to take a look at it. It's a 1-to-50 model, and it already looks like a real riser. So, because at that time the concept was 10 meters of diameter, CWP. So in 1-to-20, it's like a 20 centimeter model, or 100. Well, you can ask Lockheed Martin, so it's there. Okay. And the second announcement, now please, from the board, can you show the website? Okay, so Rai mentioned it. We have this OMAI, which is the Offshore Mechanical Arctic Engineering Congress. It's a huge congress. A lot of researchers and players from industry, especially offshore industry, attend this congress. Not all of them know OTEC, okay? So myself, Professor Ikegami, and Professor Antonio Carlos, we are organizing this symposium inside the OMAI. It was already a victory for OTEC and OTIA, because we had to convince them to accept, because we are still on the others, right? Other ways of it. Yeah. So please, if you can show the symposium. Yeah, it will be held in Canada in June 2025, next year. So for me, it's hard to see here, but we have about 15 symposium, thousands of attendees. But if you go to the symposium number 13, I think I have to come down, or else I can't read. So we are there. Can you see? It's a special symposium on OTEC and correlated devices. Those correlated devices are mainly the intake risers, because I think it's something that represents our synergy with the oil industry. You have seen here in different presentations. The FPSOs, they need to pick up cold water as well. It's not the same premises, but it's something that we can talk about with them. Okay, so that's why we put. Oh, I could have read in here. So, and the idea is that we have different topics, but they all cover what we have seen here in those 2 days, and we have received one summary of what we have up to now. In terms of papers, and we have only one paper actually, but we extended the deadline for abstracts, and then we are inviting you to send abstracts so we can have a nice symposium, and it's a very nice opportunity for us to spread the word on OTEC, which I believe is one of our objectives. Okay, so and for you that do not know OMAI, it's a very nice congress. We have been participating for decades. We have organized 2 in Brazil so far, in 2001 and 2014, if I remember well. So please let's take the OTEC further. Okay. Okay. So that were the 2 announcements that I had to do, and now again on behalf of Sobina and Copy and Otia, okay, my three hats. I would like to thank you all for being here. Both the Brazilians and also the foreign people that come. Some of them came from the other side of the world, right? So we are very honored to have you here. It's very nice for us. I hope, I don't know if you had time, but I hope that you had some opportunity to know at least a small part of our city. But anyway, you are invited to come back in other opportunities. We are open to cooperate, okay? We are very open people, open-minded people. So please, if you have any idea, please tell us, and we'll be very happy to cooperate with you. And I would like also to thank our sponsors and supporters. For instance, CNPq, which is our national Institute for Research. CNPq is the main sponsor of Sobina now. And for those that cannot read here, Sobina is our Brazilian Society for Naval Architectures, okay? Which I am part of the director's board until December 31st, 31. So it's my last event here in Sobina. I think it's a gold key closing. And also, of course, OTIA, Liga Naval, which is a group of students from our university and also other partner universities that help Sobina with the organization, with our events. And our companies, the companies that have helped with the organization of this event. CRN, which is a Brazilian company. It's a very small company. Used to be one-man company. Now it's going up. I think they have now about 20 employees. They're very nice. They do a lot of analysis. They are together with the university, with us, on organizing the JP that Martin presented here. And we have other projects as well with the Innovation Agency in Brazil. Okay, so it's a very good-minded company. This is what we need to have more in Brazil, which are companies that are willing to invest in new technologies. It's not part of our culture, of course, excluding Petrobras and the big ones, Embraer, but they all have had some help on the beginning. But if you go to the small companies, they have very rough day by day. So they don't know if they have money to pay the employees at the end of the month. So they don't have much time to think about putting some money on new technologies and going to the university and talk with us. So it's a very nice thing to start to have those kind of companies in Brazil. We think that this is the way for us to become a more developed country. So thank you, CRN. And also, one of the stars of our symposium, Global OTEC. I think like 5 years ago, nobody knew you, but you did a very nice work. I think your tier has a lot to talk with them. Actually, they are part of our executive committee right now with one of the delegates from UK. So I like to thank. They also sponsored this event here with one of the coffee breaks, and the visit of tomorrow. We have, which used to be a very small company, 4 people, 4 naval architectures with an idea. Now they are a huge company. They work with a lot of subjects that are related to what we have been discussing here. The company is Ocean Pact. Okay? As I said, they started like 4 naval architecture, unemployed ones, and now they have like plenty, 20, almost 40 ships, installation ships and supplies and so on. So they are huge now, and they are about to inaugurate their building inside our university. They are going to have a research center inside our technological park. Maybe we'll be able to see it tomorrow because it's very close to Oceano. So thank you again for Ocean Pact. And now, on behalf of Sobina, I would like to close this event officially, but we still have some fun tomorrow, and I hope we will be having also very nice conversations and networking and so on. So thank you again, and have a nice evening for today. Thank you.